All right, we all here and awake? I don't expect you to be awake. I mean, we did have DConf yesterday, yes? How was that? DConf. Yeah, we've got Funkwerk officially sponsoring our DConf these days, so yeah, thank you. Yeah. All right, so this is the second day of the DConf. We have another full day lined up for you. As usual, I've got to go through the setup notes for everyone. Health and safety, fire alarm sounds. Yeah, follow the instructions from the staff. If you discover a fire, break the glass where it says break the glass and push the button, and then assemble behind the building. Do not obstruct fire routes or exits, and report any injuries, accidents, or damage to the code node team. Easy. We've also got soft drinks, can be purchased downstairs from the bar on the lower ground floor. Yeah. There are water stations. There's one right there, for example. So if you're thirsty, go for that. And the Wi-Fi code node with password enter space, capital E, capital S, no spaces. I think that's about it for the setup. So before we do kick off, I would like to ask any bots that are on the stream today, just kindly get off the internet, please. Just get off. We do not want to deal with you today, all right? Just let us have one day in peace, please. Can you do that? No. Okay. It's a bot. Anyway, we have the creator of Lua here, Roberto Yarrow Slobminsky. I think I screwed the name up again, sorry. Yarrow Slobminsky. And he's going to give us a talk. So a big round of applause for him, and let's get this going.
Can you, the sound is good? Yeah. Well, so thank you for the invitation to talk here today. I'm going to, I don't know how many of you know about Lua, or how much each one knows about Lua. In this talk, I will not be very technical, at least most of the talk is not very technical. I will talk more about the motivations for Lua, why people choose Lua, and I'll talk also about Palin, which is what we are calling a companion language for Lua. I will explain that in the slides. Well, I like this. I think the designing a programming language is not completely unlike this description of how to draw a horse. So you draw two circles, then you draw the legs, you draw the face, you draw the hair. So you put the main components of the language, you give it the character you want for the language, kind of the vision you have for it, and then after that you add small details to complete the languages. And I think a programming language is exactly like that. I mean, you have the vision, you have some basic ideas, but then you start adding small details, and I think the point of my talk is more or less how we keep adding details and more or less keeping the original character of the language, and what is the original character of Lua, what we try to keep in the language as it evolves. And so exactly Lua now is a language with a lot of small details, but also as I said, I'm going to talk about Palin. Palin is as I said, it's a companion language for Lua, so it's a kind of an evolution for Lua. It's intended to be used with Lua, so it's supposed in the future to be part of Lua, and still have very few details. But so the first part, I'll talk more about, as I said, about the character. Actually, in the second part too, this talk is mostly about why the language is the way it is, and what we try to keep as the main principles of the language as it evolves and as we develop it. So, why Lua? At one description, it could be just yet another scripting language. So in very general terms, for those that don't know, it's just a scripting language, not completely unlike Tico or Perl or Python or JavaScript, so it's a scripting language, but it has quite specific goals that I emphasize here, which is portability, small size, simplicity, and emphasis on scripting. So I'll talk a little about all these points. So first about portability. When we talk about portability, we mean that it runs virtually in any platform with ANSI C compiler. That we will see later also demands small size, because if the language is too big, it just doesn't fit in a lot of platforms. So when we talk about portability, we mean it runs in microwaves, it runs inside keyboards, it runs inside cameras, it runs inside everything, a lot of computers that we do not think as computers. For a few examples, it runs inside some operating systems. Inside the kernel of the operating system, it compiles with all those restrictions that you cannot use floating points, etc. It runs directly on bare metal in some installations even without an operating system underneath it. So portability means really that it runs with very little, you cannot run Lua with K bytes, for instance. That's too little, but yeah, with half a mega, with 500 kilobytes, it's enough, for instance, to have Lua running quite efficiently and quite okay in several machines. The size of the language, this is a graph of the number of lines. This is real lines, and there is logical lines. It's that kind of, I think we count the number of semicolons in the C code. So this is the evolution of Lua. It started with around 5,000 lines. Now it's near 35, so it grew a lot, but it's still, it's a very linear growth. This is over a period of almost 93, 30, I lost the count, almost 30 years now. So it is growing. We are trying to keep control of the size of the language. This is a very, very, very strong concern for us to try to keep it not only simple but small, as I said, so it fits it uses little memory outside, but the code itself also uses very little memory. Simplicity, it's hard to argue. Simplicity, it's something that has it's not always good too. Sometimes the language can be too simple, but the idea, we use a kind of a proxy for simplicity is the size of the reference manual. The reference manual explains everything. In Lua, we are very religious about the manual. We always say if it's not in the manual, it's not in the language. People say, oh, how that works, and I tried that, it worked. I say the manual doesn't say that, you should not use that. So the manual tries to be complete. And this is the spine of the manual that gives you a sense of what you have to read. Of course, the manual, it's not a tutorial. It doesn't aim to be easy to read. It aims to be complete and to have everything. But if you can figure out what is written there, that's all you have to read to know the whole language, the syntax, the semantics, the API with C, which is a very important part of the language, and all the standard libraries, which are very few libraries because of portability. So how we achieve simplicity? The idea, one of the main ideas of Lua, is to have very few but powerful mechanisms. So the things we try to avoid restrictions. We try to have smart implementations for things, so they are reasonably efficient. And so the main, I think the main mechanisms in Lua that we use that makes the language in terms of semantics, etc. So tables, closures, and coroutines. I'll talk a little about each one. Tables is what in Lua is how in Lua we call associative arrays. In the associative arrays means any value as key, so it's just a map of a value to another value. And that's the only data structure we have in Lua. Arrays are just tables used with integer keys. There is absolutely nothing or almost nothing special about arrays in the language. Arrays are just completely regular tables that we happen to use in a specific ways. Records are tables with literal literal strings as keys. And everything else in the modules in the language are tables with functions inside that. Objects are tables with function and data inside that. So everything regarding data structures in Lua are represented as tables. As I said, we have a very strong emphasis on putting the when there is complexity, trying to put the complexity in the implementation, so the API and the language keep simple. So as I said, outside a table is completely like an array is just a table. Inside the implementation, for instance, when we resize the table, the language, the implementation recognize that it has a lot of integer keys, or it has integer keys that makes good use of arrays, so it changes the internal representation in internally used. So if you're using a table as an array, it is being represented internally as an array. If you change the use and start using as a sparse array or anything else, then it adapts automatically. So we have arrays in the implementation, but we don't have arrays in the language. Well, closures, it's the famous first-class anonymous functions with lexicoscoping. That's what Lua has. Now a lot of languages are incorporating that. Lua had that for a long time. And what is, I think, it's a little different in Lua from other scripting languages, from other non-functional languages, that we use closures a lot. I mean, we tend to represent a lot of things in Lua as functions, as anonymous functions. For instance, when we compile a chunk, it's a dynamic language, we have that kind of eval that all dynamic languages have. In Lua, we don't have eval. We had something that's kind of a load that you give a string of code, and it gives you a function that is the code associated with that string, and then you can call. So eval, it's in two steps. First you create the function, and then you call the function, but there is always this idea of the function being present, so you can manipulate the function, you can call it several times, you can even pass arguments and return values from evals. But the idea is that I'll show, even as I told that about, the modules are tables populated with anonymous functions, and even exception handling, it's done using anonymous functions, because one big concern that I'll talk later in Lua is this idea of scripting, that Lua, it's, since the beginning, it was written to be integrated with C, to be used by a host program calling Lua, and Lua calling the host program to have this two-way communication. And so, for instance, exception handling, it should be important to be able to do it, to catch errors in C and raise the error in Lua, or raise the error in C and catch the error in Lua, etc. So, for instance, exception handling, we don't have a try-catch or any syntactical construction for exception. In Lua, instead of that, what we would write like try-catch in other languages, in Lua we have only this special function that is called pcall, this protected call, that calls a function, and if there is any error during the execution of the function, the pcall catches the error and returns an error code. So what would be equivalent to that code would be a pcall. You put an anonymous function there. You use that. The indentation here is on purpose, that the function is there. The end it's here to give the idea that this is a block, but also the block here is the body of the anonymous function. And so, as I said, this construction, it's not very natural, but it's very good for the API with C, because then the function itself could be a C function, or in C you can do a pcall, you can call Lua in protected mode, so all the errors are protected. And it's the same mechanisms both in Lua, both in C, so it integrates completely for both sides. We joke that lambda, the ultimate block constructor. We use lambdas a lot for that kind of things. And Lua have coroutines, which is a word that means a lot of similar but not equivalent things. In Lua, in particular, coroutines are equivalent to cooperative multithreading. In particular, it means that you have several stacks, one different stack for each coroutine. So you can suspend the execution of a coroutine inside a lot of function calls and then resume the execution. For instance, you can do some I/O operation, and there is something that you detect that it has to wait something, so you can suspend the execution, and then later you can resume. So that's why we call it as a cooperative multithreading. We can prove that it's equivalent to one-shot continuations. So we don't have full continuations in Lua, but if you read papers about how continuations are great, you see that most users of continuations actually only need one-shot continuations. One-shot continuations are continuations that you can call only once. You cannot call the continuation more than once. And also coroutines offer continuations in a way that it's much more natural for imperative programming, because it's like threads. I mean, as I said, it's quite similar to multithreading. You just create a coroutine, it's like you create a thread, it has a body. When you resume, it starts executing, and as I said, you can call functions, etc. It can be anywhere, and then it suspends, then it stops execution, you can do whatever you want, and then you resume, it continues executing from where it stops. And scripting, as I said, a lot of people now kind of associate scripting language with dynamic languages, but there is a very big difference in purpose. That the main idea of scripting language, the name scripting came from this idea, is that the program is written in two languages. You have the scripting, and you have what's called the system language. And the idea is that the system language implements the hard parts, usually the complex algorithms, the complex data structures, and the scripting language connects those parts. The name scripting, I think, came from the shell, from Unix, and the idea that shell is exactly a scripting language, and all those Unix programs are the components that you connect, etc., that you manipulate using the scripting language. And Lua has a very, very, very strong emphasis on scripting. Lua, since the beginning, it was implemented as a library. Lua is not a program. There is a program, Lua, but that program is just a small program that uses the library exactly like any other program. So as I said, for instance, when I mentioned exception handling, everything in Lua is written having this API in the library in mind, how it's easy for C to access that, etc., how it's easy to transfer things, etc. And in particular, Lua is very good not only for extending, usually those names are not very standard, but usually extending a scripting language means adding C functions to the language, so you put libraries written in C, and so the main program is written in the scripting language, and you call those libraries in the system language. And embedding is the reverse. For instance, the main program is written in C, and you call the scripting language for other tasks. In games, for instance, because of the I forgot the name of the rate, the frame rate, usually the main loop is in C, and you call Lua, for instance, for each step in the frame rate, you call Lua to perform, to update the characters, etc. So in games, it's very common to use Lua embedded and not extended, but Lua, it's good for both, and it's very common to, of course, you usually have both. I mean, the C calls Lua, and Lua calls C back to do some small stuff, etc. And Lua is so good for scripting that, as I say, that it's not the same scripting and dynamic languages, that Lua has been used, embedded in a lot of other scripting languages. I still, once I was giving a talk in a Python conference, and Python was not in the list, and someone interrupted me to say, oh, we are using Lua to script our Python programs, because, for instance, they needed isolation, and Python can, I mean, we needed to offer the user some scripting capabilities, but we didn't want the user to be able to access everything inside the program. And you cannot do that in Python. In Lua, it's easy. You can have different Lua machines, or you can just build a sandbox using Lua standard. I mean, Lua doesn't have sandbox built in, but it has flexibility enough so you can protect parts. You can just offer some functions to be called from the scripting for the user. And so Lua has been used successful, as I said, in a lot of embedded systems. This short list, most people associate Lua with games. Lua has a big niche in games, but it also has a very big niche in embedded systems. As I said, it runs inside the TVs, it runs inside keyboards, and all kinds of equipment. In games, it's also very popular. And now I'll talk a little about Palim. That, of course, all dynamic languages have the problem, well, all languages have the problem of performance, but in particular, scripting languages are very, usually they are slow compared with static languages. And one of the main mantras of scripting, that idea that you have a scripting language as a system language, is exactly that. Oh, if it's slow, rewrite that part, that main algorithm, that main loop, that part that it's slow, you rewrite that in C. This is a mantra of scripting, and we usually give this answer for people. Oh, this is very slow, so just rewrite that in C. The main problem is that it's easier said than done, because we have two main problems with this idea of rewriting C. There is data mismatch and language mismatch. Data mismatch means that data has to be transferred between the two languages. So you have, for instance, an array or a table, as I say, represented in Lua, and if you want to manipulate that, you have to transfer that. Either you have to copy the whole array into a C array, or you have to do API calls for each access to an element. So it becomes very slow, this data transfer. And so this process sometimes kills any gain that you could have changing the code to C. And the second problem, that is language mismatch, there is big differences between Lua and C. So if you are going to change just 10 or 20 lines of code, it can be easy, but if you have to change something larger, it can be quite complicated. And one of the worst parts is this last point, sometimes it's hard to predict whether the data mismatch will kill any gain that you can get from changing to C. And so you have an expensive process that you don't know whether it's going to pay off in the end. So it's very hard to decide, oh, okay, I'm going to change that to C, and then you invest some time, you spend some resources doing that, and in the end you realize, oh, it's not worth that, it didn't gain much, or we have to change something else, have to change the architecture, etc. So one solution that people are using a lot for dynamic languages in general, and scripting languages in particular, is just-in-time compilers. And it has some very good points that you, officially at least, you don't change the language, and you can achieve quite good performance, mainly in benchmarks. They are particularly good in benchmark, but they are very good in real programming too. But they have the one point that they're very, very hard to implement. They are hard to port. They compromise portability, and they are hard to maintain. And there is the problem of optimization killers, that most JITs do not optimize the whole language equally. And so people start to know, oh, okay, we shouldn't use that with a JIT, you shouldn't use that, etc. And then you start creating a subset of the language that you hope can be optimized when you are writing code to a JIT. You have a completely different mindset when programming code for JIT and when programming for the not JIT. So it looks like the same language, but when you are actually programming seriously, it becomes almost two different languages. So the idea of Palin is, it's that idea at the end. So if we are already almost with two different languages, maybe it would be much simpler to make explicit that you do have two different languages, and they shouldn't be that different, but at least you know that language is one that I can optimize, that other is the other one, and I know and I expect that if I write code for that language, it should be well optimized. It doesn't depend on what version I'm using, or, oh, that trick that I cannot use that or that. So as I said, Palin, it's a companion language, and it's been designed as I said, to substitute, is a substitute for C. I always change how to use substitute in English. It's to replace C, to be used instead of C as the system counterpart with Lua in scripting architecture. And so we tried, the main idea is to try to reduce both that data mismatch and the language mismatch. The idea of to reduce the language mismatch is this: Palin is a typed subset of Lua, so everything you write in Palin except for types should be valid Lua programs, but not everything you write in Lua is a valid Palin program. So Palin is a real subset where exactly we eliminate most of the things in Lua that we know that it's inefficient, that most JITs cannot optimize anyway. So we try to, okay, this is kind of C. This is a very simple language for fast tasks like sorting, or to implement some data structures, etc. And Lua is a different language that you have. And the main point also is that to reduce data mismatch, it operates directly on Lua data. So because Lua has a very strong, how I put that, emphasis on this API. It's not like some other scripting languages. You start calling functions inside there is that function. In Lua, you have a very well-defined API. It's very well documented, and always you must access everything through this API. The API gives you good guarantees, but it is a little slow, as I said, for instance, to access, to traverse an array. Each access you have to do an API call, etc. And Palim, because it is compiled, it ensures that you are accessing the data in the correct way. You are not breaking any invariant, etc. So your code can access data structures, Lua structures directly, and respects, for instance, things concerning the garbage collector and all those details. And it has some ideas from gradual typing that I'm not talking here, but this idea that exactly that it has types and it talks to a language that doesn't have types. But so this is an example, for instance, to a function in Palim. The only difference from that to Lua is that you put the types in the parameters. If you think about a JIT compiler, the main complexity of a JIT there are two main complexities, actually. The first one is to infer those types. And we think it's much, much easier if you write those types and give that instead of writing a lot of complexity around that to try to infer the types that you intend for the function. And the second, I think that is the worst part of the complexity of a JIT, is that if the type is incorrect, it has to roll back to the interpreter. I mean, JIT ensures that it has the semantic of the original language, so it infers types, it optimizes for those types, but if you call the function again with a wrong type, then it de-optimizes, has to transfer data that is in registers back to the scripting language representation, etc. And this is also a big source of complexity for JITs. And just adding those types, you eliminate both sorts of complexity, because first you give the type, so it doesn't have to guess, to warm up, doing some executions to try to infer the types. And second, if the type is wrong, it raises an error, and that's it. So it's not only much simpler, but usually it's faster, because this is something that people not always realize, but even when you had a hot path in a program, sometimes the else that you don't use, the complexity of the code there affects the optimization of the fast path. So if the else is just throw an error, is a function that it knows doesn't return, it does not affect the code generation, the register allocation, etc. for the fast path. So the code is like, if it's the wrong type, raise an error, that's it. Otherwise, so the compiler has a much easier task optimizing the code. And the programmers maintaining the code, it's much, much easier to write a compiler for that than to write a JIT. So the design principles, what's the ideas behind Palim that we will try to keep in the future. So I think one of the main points is that the same selling points from Lua. So it should be portable, it should be simple, it should be small, and of course the idea of scripting is built in the idea of Palim. It has a very simple type system. It does, as I said, we don't want to type all Lua programs. We want to type what we know can be efficiently compiled. So it's arrays, records, those, for instance, maps, for instance, now it's out of the language. Maps it's slow. If you're really writing something really efficient, you shouldn't be using maps. Another point is what we call good on the borders. This is exactly this on the border between Lua and Palin. The calls from Palin to Lua and from Lua to Palin should be fast. You shouldn't have to pay much to change languages. It has what's called the gradual guarantee, which means that supposedly if you have a Palin program and remove those type annotations, it should have exactly the same semantics as in Lua, so it's easy for you to see a Palin program, and if you know Lua, you should know what it does. Of course, it's hard to keep a complete gradual guarantee. There are some things that will change, even sizes of structures, etc., can change, but usually we try to keep as much as possible of that. And we want to use a very simple ahead-of-time compiler. The idea is that we want to compile Palin, we do compile Palin to C and ahead of time, because we have all type information, etc. So as I said, the selling points should be portable, should be small, should be simple, and emphasis on scripting. The simple type system, as I said, a lot of people think that the point of dynamic typing, what is expensive in dynamic typing, is checking the types. Actually, checking the types is not that expensive. Usually the tag is next to the data, so when you read the tag, it's already on the cache, or it gets the data in the cache. So reading that is not expensive. The check itself is with a good CPUs now with good jump predictions. Almost always the check is correct. So the price of checking tags, it's very, very small. What is really expensive in dynamic languages is boxing and unboxing, but because when you don't know what is the type of something, you don't know the size, or you still have to need the tag, so you cannot keep in a simple register, you cannot pass as parameters like regular parameters, etc. So the really expensive thing in dynamic language is this thing of boxing and unboxing. So when you give type information, you can, even if you keep the type check, you can run the code assuming all data is unboxed. When you read something outside, that part is boxed. For instance, an array, it is kind of naturally boxed because it has to be in memory. And then when you read that, you check the tag. If the tag is wrong, you raise an error. Otherwise, you automatically unbox that. You don't have to keep the tag anymore. So that's the main source of optimizations when you give types when compiling dynamic languages. And as I said, things that cannot be optimized, it's just out of the language. You don't have, for instance, pattern matching is an example of things that's very difficult to type. You have captures, etc. Each pattern can generate different kinds of answers. And so you have a type any that represents anything, so you can type those stuff in Palin, but usually it's better just keep that part of the program in Lua. You are not going to optimize that anyway, so just keep in the original language. As I said, it should be good on the borders because you want to translate only the critical parts of the performance. You don't want to translate the whole program. So you shouldn't lose any gain that you got from translating to Palin, calling Palin from Lua or calling back Lua from Palin. And so, for instance, if you change even small functions or just a single function from Lua to Palin, it should not make the program worse. It's like that. Oh, if you change all that, then you have gains. But if you change gradually, each change does not improve. Only after you do everything, then it's going to improve. And then you realize it didn't, and then you waste a lot of time. And so gradual guaranteed, I talked about that already, so don't need that. And as I said, a simple ahead-of-time compiler. It generates C. It generates C using the same standards we use in Lua to only ANSI C. We are very, very strict about the reference manual of C. We respect everything or almost everything the manual says that C should. It's unbelievable. I don't know how many of you really know C. I mean, how hard is to write really portable code in C. A lot of things it's that's obvious. You read the manual say you can. That's not only obvious. That's undefined behavior, and so Lua has a kind of very successful story of portability, and we try to generate code following the same rules. And of course, it simplifies a lot the implementation. So these are just some graphs, so just quick big benchmarks. Just the idea, for instance, here we compare with the main comparison here should be the yellow and green, that it's Palin against LuaJIT. Of course, we don't want Palin to be faster or even as fast as LuaJIT. We want to be good enough compared with LuaJIT by a fraction of the complexity of the cost. Yes, I forgot to ask whether that includes questions or.
No, that's extra.
So okay, so I'm good. So but also the interesting here is exactly the blue one is exactly if you translate the program to C using the data in Lua, so keeping the API. So as I said, sometimes you can have very good gains. Sometimes you have the program that's worse than it was because of this translation. So it's something that those are very small benchmarks. It's not a big deal, but as I said, if you have something more complex and you spend maybe a month or even a week doing that translation, and the day later you realize, oh, it's worse than it was, so it's not very good. And Palin, it's always better than Lua. It's on pair with LuaJIT. There is some, of course, it's not as good, but it's much, 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 much simpler and cheaper. And C is just a baseline. If you translate the whole program, everything right in C, all data structures, etc. It's just to have an idea of that. And this is also a nice experiment. It's we got some benchmarks, and the idea of this graph is that you broke the code in 3 parts, sometimes just 3 functions, and here, for instance, means that the 3 parts are written in Lua, and in the top, the 3 parts are written in Palin. And so the graph, as I said, if you change only one of the functions, and you see that in all cases, you may not have a gain, but you never gets worse if you change just one small function from Lua to Palin. So it can keep the things at least as good as it was. So all that are small experiments, just gives an idea of what we are heading to now. And so that is, Lua, as I said, is a language with a lot of details that has very strong niches in games embedded. software. The main points that I think are, someone asked me how Lua succeeded, and I think it's because of that, and of course because of luck. Luck is always very important, mainly if you don't have a big company promoting you. And performance is always present concern for dynamic, actually for any language, but particularly for dynamic language. And we are trying to investigate, trying to explore this idea of a companion language as an approach for improving the performance of Lua. That seems compatible, of course, with JIT. Lua JIT. It's very successful. It's very, very good in some uses, but it's not. It doesn't follow the Lua main selling points. For instance, portability. To port Lua JIT is always a big project, and it's not that small, etc. So, of course, it's completely not simple and almost unmaintainable. So we are trying to do something that, as I said, maybe not as fast, but it's almost as fast, but much simpler to implement, much easier to maintain, and portable. And so, as I said, that is compatible with Lua selling points. That's it.
Okay, thank you. Now we've got time for a few questions. We've also got a quick comment from Ian, who was saying at Semantic he mixed Lua and D to serve ads.
Pardon?
One of the guys in our community, Ian, mixed Lua and D at a company he worked at, Semantic, to serve ads on the internet.
Yeah,
like all the weird usability you were talking about. It's been used with D to serve advertisements.
Oh, okay. Yeah, I should put here embedded in. I should put in that list too.
Yes. Anyway, we've got a question over there.
Is the Palin compiler completely separate from the Lua compiler?
Yes. Yes, it's completely, the compiler is completely separate. The code it generates, it's intended to, it's completely connected with Lua.
Hi. So I've been touching Lua for probably more than 20 years, always in games. I've worked at Blizzard and even on World of Warcraft a little bit, which might represent the majority of Lua code on Earth. You've made a clear emphasis on interacting with C. That's obviously been there right from the very beginning. Why one-based arrays? How did that happen?
Oh, I should have that written. That there are two kinds of languages.
Yeah.
One language that index from one.
It's just probably the biggest oddity when interacting with C is that one single detail.
Yeah. So for non-Lua, I didn't emphasize that, but that's almost a giving for real scripting languages. They are intended for non-professional programmers. Usually the one that I really forget to put that emphasis on this idea of scripting, that's not only this distinguish between fast and slow, but also there is sometimes a big big separation between real programmers and scripters. Or I think in the game industry, this is very clear that the people that write games, they are not interested in programming. They're interested in creating the game. So for everybody else, this is sometimes hard for us programmers to understand, but for everybody else in the world, including mathematicians, numbers start with 1. You never see a matrix in any book of mathematics with A00. Everything is A1, A2, etc., etc. A1 is much, much, much more natural. You see kids learning programming and they get everything. Oh, it's okay, it's okay. Then suddenly zero, how you count three things, it's like zero. There is this joke in that movie about Germans counting like that, but how you count 0, 1, 2, so that should be 3 because it's 0, 1, 2. This is it's completely unnatural, I mean. It's good, and what is more funny, this is, for me, it's the extra part, is that there are good reasons for zero indexing. But most programming languages do zero indexing because of C. Most languages that are zero-based also have the same syntax of C, etc. A lot of languages inherit a lot of bad things from C. And in C, there is no indexing. C does not index from 0 because C has no, Z has pointer arithmetic. The brackets are just syntactic sugar. There is no bracket operation in C. What you have is pointer arithmetic. So you have offsets, you don't have indices. And then, of course, the first element is offset 0. But then all languages after that don't have pointer arithmetic. They don't have pointers. It's completely abstract, but they kept the 0. And of course, okay, if I'm doing a circular list, then the module arithmetic is a little simpler if I use 0 indices than 1 indices. But for most people in the world, as I said, if you count what's the 1, 2, 3, I remember, I think Dijkstra was a crazy guy. He once decided, I'm writing a paper with the first session was 0. I think he wrote one paper like that and he gave up. I mean, that's.
I get the feeling you might have been asked this question before.
yeah, people always ask that, but for me it's yeah.
I do have a second question.
Yeah, and at the time, it was not that prevalent, the zero indexing. For instance, most of our users in the beginning were like civil engineers, geologists, and their previous experience were Fortran that index from 1 to, and it's very fast. I mean, it's so good. And it's very mathematical, Fortran. It's nobody asked Fortran why index it from 1 when they started. It was completely natural. And nobody asked C why they index from 0 because they don't.
Okay, so that maybe this is a simpler one. You compared Lua-JIT and Pauline. There's a couple of cases where Lua-JIT worked out faster. Can you describe why that worked out that way in those cases? What's the...
Oh, that's a good question. Well, it should be faster always. It's unbelievable that it's not.
You say JIT should be faster.
Then C? No.
Well, if Pauline is compiled to C and then hard compiled, why should the JIT ever be faster?
Oh, okay. Pauline is not well because Lua-JIT optimizes other stuff. For instance, that it recognizes some constants that are not obviously constants in the program. So it's not only types that the warm up. It optimizes other stuff. But the main point is the data representation. Because you see that usually Lua-JIT is faster in things that uses large, for instance, matrices and a lot of data, because of Lua-JIT uses that actually has very little to do with Lua-JIT, and it has to do that Lua-JIT uses the NaN trick. And so it uses half memory than standard Lua for a lot of stuff. So the main thing, the main difference is its memory access, memory throughput, the rate of transfers from memory to the CPU. because so it's mostly, Lua could use that in the past when it didn't have 64-bit integers. It did use actually that, and so it would eliminate that difference.
What kind of memory management do you use? Do you use a garbage collection, or how do you clean up?
Pardon me?
Do you use garbage collection in a language, or how do you clean up memory?
We use the Lua's garbage collection. As I said, all data is. Who asked the question?
Yeah.
Oh, it was you. As I said, we access the Lua data structure, so we use the Lua garbage collector, and as I said, the compiler creates code that takes care of that, and so it keeps. It has the guards necessary for access, etc., to keep the garbage collector happy.
So it's a run, stop the world garbage collector?
Oh, the garbage collector, currently you can choose, there is an incremental garbage collector and a generational garbage collector. The standard now, the default is a generational garbage collector.
Okay.
All right, we got time for this one last question.
So how do you organize and grow the community around the language?
It's too ugly if I say I don't. No, we keep, I mean, we have a mailing list. We try to keep people polite on the mailing list. But otherwise, we don't organize much. I think we should organize more. I think that the main thing we do is to try to keep the language separated from. One point of Lua is this idea that do it outside of, so that it is clear separation from the language and then external libraries, etc. So contributors usually write their libraries and write distributions, etc., but they don't change the language. So this is, I think this is the main.
Okay, and that's question time over. Thank you again, Roberto.
Thank you.
All right, it's break time. You've got 10 minutes. Be back up here at 10 past 10 for the next talk.
It's a really great talk. I really.
Alrighty, everybody, come back upstairs. It's time. All right, welcome back. I'm currently presenting to you from Ali's preferred location. It's pretty comfy down here, I have to say. It's not. It might be worth doing all talks down here. I think you're onto something, man. All right, so let's just kick this off. We got a first-time DConf speaker here. Woo! Give it up for. I'm terrible at name pronunciation, so it's Roy.
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 Roy Margalit.
So, yeah, introduce yourself. I'm terrible, man. But yeah, atomic variables. Let's hear about them.
So hi, my name is Roy Margalit, and we're going to talk about atomic variables. While they're not radioactive, you probably still don't want to touch them. But the problem is that, as we know, computers are not getting faster for many years. They just multiply. So the only way you can actually get something that's going to be faster these days is basically with parallelism. Now, our problem actually starts from the fact that if we have races between the different threads accessing the same memory location, and one of them is going to write to that location, we have a race. And this race triggers undefined behavior, which means all bets are off, your program is completely broken, you can't do anything with it. And there's actually a really good reason for this undefined behavior. It comes mostly from cache and optimizations, and you don't want to give up on them normally. So the simplest cache architecture we can describe is probably x86 TSO, which basically means that every single CPU we have has its own cache. And if we want to read something, we first check if it's in our cache. And only if it's not there, we're going to read it from the RAM. And the reason is that RAM is actually really slow, at least compared to cache. And when we are going to write the value, we are not going to write it directly to the RAM. We are going to write it to the cache. And at some point in the future, the value should propagate to the RAM. But this means that until it propagates, different CPUs can actually read an older value, a stale value that might not be correct. So this is going to trigger weird behavior. And the other thing is optimizations. Optimizations are awesome. They allow us to write really bad code and actually get decent performance. And sometimes we get bad code just from lowering, so we don't really control it. So if we, for example, have this this matrix summation, where we sum matrix A and matrix B into matrix C. So in terms of mathematical representation, these two codes are the same, since we can do the summation in any kind of order. But from a CPU perspective, there's actually a huge difference in performance because of the way we access the memory. In the first one, we basically jump around everywhere over the columns. And in the rows, and then columns, we actually go neatly cell after cell, and everything is in a nice cache line, and we don't have as many jumps. So you really want that kind of optimization, because otherwise things are going to be really slow. So now we're going to see a live demo showing how things break horribly. And we're going to do this with this matrix summation. And we're going to wait until some sentinel value changed. We assumed it right by columns. So by the point that we actually are going to sum the last column, we can safely assume that maybe the value in the first column has already got updated and we should be able to see it correctly. So we're going to wait for the sentinel value and see how things work or not. So this is the example. We have 2 threads. One is going to be the summer. And for reasons we'll see, I've decided to actually iterate over the columns and then the rows in the reverse order, trying to get the compiler to do something very specific. And the summer is just going to wait until the last row, last column 0 is different from 0, changed, and then it can safely probably count the number and see that we get the correct summation. The matrices themselves are going to be initialized with 1s and 2s, just for fun. OK, so we first compile it with GDC and no optimizations whatsoever to see that we actually get correct behavior that we expect. And indeed, we get 30K, which is correct. Everything is fine. So we figure out, yeah, why not? We should trigger optimizations. We want our code to be faster. So let's add O2. And run our code again. And it breaks. So we go back and we figure out, oh, this is his flag. He wanted no finite loops. And what happens is that we have this nice loop over here, the watcher who's waiting, and the compiler says, oh, yeah, you're going to read this value, and it's not going to change between iterations, so we can just read it once and keep the value 0. And then either you end up with an infinite loop, or we are going to just delete the entire thing because there are no infinite loops. So the obvious solution would be volatile, right? The compiler is not allowed to optimize volatile away like this. So it's going to force the compiler to actually load the value every time to make sure that it actually changed and reads the current value. So we'll go back to our code, compile it, and we add volatile. And great, everything is working. We got our 30K back. But what's going to happen if we're going to crank up the optimizations further? Because everybody loves O3, right? Oh, boy. That's even worse than what we had earlier. So things are clearly broken here. And trying to understand what happens is that the order that we expected the values to change was basically from bottom to top, left to right. And the compiler decided, no, that's a really horrible way to access the memory. We should probably change it like this. And you should just keep on going with chunks of memories that are neatly packed together to get better performance. And normally, this is what you want, because you want to get the best optimization. But for this case, where we expect some kind of ordering, it breaks horribly. So this is where a core atomic comes to the rescue. This is going to be our solution to figure out how to fix stuff. And it's going to give us defined behavior for races. So we will know what to expect. And it's going to guarantee us equation consistency. And in order to get this, we're basically going to use atomic load and atomic store over a variable. Now, sequential consistency basically means that you can consider your execution by simple interleaving of the different statements from the different threads. Just take one statement from a thread at a time and execute it, which is very natural. So we're going to see an example. This example is called store buffer. We have X and Y being global memory locations. They are going to be initialized to 0. And then the first thread is going to write 1 to Y, to X and read the value of Y. And the other thread is going to write 1 to Y and read the value of X. So under sequential consistency, we could, for example, start from writing 1 to X. And the memory gets updated. And then we can read the value of Y that is currently 0. Next, we are going to write 1 to Y. And finally, we are going to read X, which is 1. And similarly, we can do it in a mirror fashion and get A being 1 and B being 0. And Or another execution could be we first write 1 to x, and then 1 to y, and finally read both ones from the variables. And we can pretty much convince ourselves that under these kind of semantics, we can't read the value 0 for both x and y, since there is no possible interleaving to get this behavior. So if we go back to our code and replace the writes with atomic store, so we have atomic store over for the C matrix, and the load is going to be atomic load, then now we have defined semantics for the race. And this means that if we go back to our code and compile it with O3, we get the correct result now. So everything is great, except not everything, because we lose performance, a lot of performance. Each sequential-consistent access forces us to flush the caches, which means we're basically working on RAM and not cache, and this is slow. And it prevents reordering of statements. It prevents variable hoisting. It prevents many, many kinds of optimizations. So you probably don't want to use it normally unless you have to. The good news is that the C11 memory model, C++ memory model, introduces weaker kinds of accesses, and they are going to be cheaper to use. Races are still going to be defined, so we'll know what to expect, but we have to pay a price. Nothing comes free, and the price we pay is less synchronization. And so the first access is going to be called relaxed, which for some unknown reason is called raw in the D language. Nobody has a really good reason for why it happened. I'm blaming Walter right now. And it provides no synchronization. But what it does provide us is a guarantee that the writes are going to be monotonic over writes to the same variable. But otherwise, it's free for all. So if we initialize x being 0 and then write 1 to x and then 2 to x, and the second thread is going to read the value of x for 2 times, then the second time is guaranteed to be at least bigger or equal to the first time, since we are writing them in ascending order. So the order is kept. But we can't do much with it because there is no synchronization. So we also have release acquire semantics, which allows us to synchronize threads. And specifically, things that happened before the write release happened before the read acquire. So at this point, this thread knows that 1 was written to x, since it happened in its history. And then it writes 1 in a release fashion to y. Then once we read y, this 1 specifically for y, then we must read 1 for x, because we have this kind of synchronization that forces us to know that these kinds of events took place in this order. So now we can look up back to our store buffer example again and consider if we are talking about the release acquire semantics, for example, or the relaxed ones, can this happen? Can we read 0 for both x and y? And the answer is yes, obviously, since we have no synchronizations. They're not touching the same, they're not reading something that was read by the other thread to force any kind of synchronization. So again, we have this same code. The first thread writes 1 to y and reads x, and the second one writes 1 to x and read y. And we are going to have many iterations until we can actually get this kind of weak behavior that is not guaranteed to happen all the time. And for convenience, I'm just going to use LDC this time. It doesn't really matter, and I'm adding optimizations just to make it faster, but we can get this kind of behavior even without optimizations. So yeah, it's taking a bit now. But yeah, after 11,000 iterations, we actually managed to spot the fact that we read 0 for both values. So it doesn't happen often, but this 1 in a million chance or 1 in 10,000 chance is going to break your code, and you won't even know where to start debugging how things went wrong. Good luck. But you know, you might say, fine. we'll test, running it many times, as many as required. But the thing is, it's not enough, because you're still limited by the architecture that you're actually running on. So in this case, I'm running it on x86, which actually provides even stronger guarantees than the release acquire statements. But if we're going to run our code on an ARM or PowerPC, then we're going to actually have different kind of behaviors that we will never be able to exhibit on this machine. Specifically, an example called message passing, where the first thread is going to write is 1 to x, and the second one is going to run 1 to y. And the second thread is going to read the value of y and then read the value of x. And if we read, and we're going to see that on x86 we can't get 1, 0, but on ARM we are actually going to see this, much to our surprise and joy. So this is the x86 machine. It's going to take a while to run. So we'll just put it in the back and move to an ARM machine that I have here. It's going to run the same code. And oh boy, the SSH died. Should have known it's going to happen. Nuke it, login. Seriously? Amazing. We'll try it again later, but at this point we can.
Maybe you have it in the history. You can show us.
Maybe.
Up page up. No.
I think I did clear screen, but I have a recording. So this is going to take a while. I'm just going to put it in back, BG. And we have ASCII play for a cast that I did prepare on the server just in case. Because you never know if things are going to break like this. It's better to see for fun, but so yeah, it's taking a bit of time. And I think it was 12 seconds to get the result, but the idea is it's going to be rare, even seeing it on ARM. So if anybody thought about running plenty of tests trying to get this weak behavior, good luck. It's not practical. There. So 83,000 iterations. Sorry, 830,000 iterations just to actually see this behavior. So good luck with your testing. Oh, and I should mention, I did try to get this working on a virtual machine of ARM, but it doesn't have to introduce all the weak behavior, so I couldn't reproduce it. I really had to use real hardware. So yeah, testing is not going to cut it, if you ask me. And there's also the fact that you probably don't have alpha machine that can actually get all these kinds of crazy behaviors. Oh, and there was another problem. Current compilers are afraid of optimizing atomics. Just like I'm afraid to touch them, so are they. Yeah. So if we go back to our example, here, I swapped out the sequential consistency access with the cheapest one, the relaxed one, and both for the loads and the stores. And now the compiler is legally allowed to make the optimizations and change the ordering where I'm accessing the variables. So we should have seen the problem, except we don't. The compiler is just afraid. So yeah, you can't even trust your testing to work because maybe the compiler just didn't do the kind of optimizations that's going to break your code in a horrible, horrible way. But you know, maybe, OK, fine, testing is not enough. Maybe we need domain experts. Domain experts surely know what they are doing, right? Hopefully. So this is a short story about Peterson's mutual lock He proposed it back in 1981, and it assumes sequential consistency access, which was pretty much everything back then. Now, the question is how to implement this lock in the C11 memory model. So Bratosh-Milewski proposed an implementation for this algorithm. And we can see that it makes use of the release acquire accesses. It also has an exchange statement, which is an atomically read and write, read the previous value and store a current value. And it makes use of everything here. And Dmitry Vuyokov, hopefully I'm pronouncing it correctly, said that, it's not right. This implementation uses both insufficient and excessive fences at the same time. It's too weak and too strong at the same time. It's like, it's wrong and wasted. And instead, he proposed his own implementation for the algorithm. And Bartosh's response was that I don't have a foreign proof that my code is correct. I believe it to be correct. And for all I know, Dimitri's implementation is also correct, but it's much harder to prove. So yeah. Subsequently, Anthony Williams analyzed both algorithms and concluded that Bratosh's implementation wasn't correct. It was actually wrong. And that Dimitri's implementation is correct. So it could be used in production. But all of these experts agreed on one thing. Anytime you deviate from sequential consistency, you increase the complexity of the problems by orders of magnitude. You're basically asking for trouble. Now, so if domain expert thinks that maybe you should keep your way out of this, maybe sometime in the future somebody's going to find a solution. Like maybe some great, bright computer scientists are going to propose a new kind of logic that we'll be able to finally use to prove the correctness of our algorithms. And you see this back in 2020. These guys did an amazing work. They proposed a new kind of logic. And their case study was this implementation of Peterson's algorithm by Dimitri. So that's top-notch stuff and showing how hard it is that researchers need to actually find and prove the correctness. And it is great. They proved the property about the algorithm. There's only one slight problem. The property that they proved is actually insufficient. They proved, yes. They proved that it cannot be that the two threads are in the critical section at the same time. There's only a slight problem that it doesn't mean that they synchronize between each other. So it's actually broken. So yeah, all is lost, maybe. But this is where my research tries to help and address this problem. And the idea is that verification for weak memory models is notoriously hard. You don't want to do this. It's impractical. People get it wrong all the time, and those are people that are probably smarter than me. So what we'd like to do is verify the correctness of the programs assuming sequential consistency, which is easier to reason about. It's something we've been doing for years. We even have model checkers for that. And if we prove that the program is correct under sequential consistency and some property about this program, we want to actually achieve verification under the weak memory model. And this property is called robustness, which basically means that all the possible behaviors the program could exhibit under the weak memory model are those it would have exhibited under sequential consistency. This means that I can reason about it in terms of sequential consistency, because it's not going to have any kinds of new weird behavior on the weaker memory model. And specifically, we focused on the C11 memory model, which is used by itself or a variation of in C, C++, D, Rust, LVM, whatever. So we need to understand the simple things about how the model is actually being described. So instead of having simple executions interleaved like we saw for sequential consistency, we actually produce execution graphs that describe a specific execution of the program. So this is an example of a graph that we're going to produce for our message passing program. So we start with an initial graph where we have the initialization events of writing zeros to the memory. And then we take a single statement and process it. For example, we're going to write 1 to x. So we create a new event in the graph saying that 1 was written to x, and it happened strictly after in terms of program order after the initialization. And next, when we write 1 to y, again, it happens in terms of program order right after the 1 was written to x. Now, we execute the second thread, and we need to justify a read. We are going to read a value, and we are going to read a value 1. So we need to justify it somehow. And we justify it by the fact that we read the 1 from this event that wrote 1 to y. So we have these read from relations describing that this is where we read the value from. And next, what we're going to do is basically read the value for x and justify the fact that we read 0 because we read it from the initialization. And what defines the graph is basically execution graph to be consistent is having a set of constraints on top of it. And this, for example, is valid, completely valid under the relaxed semantics. And we also have an implied relation that obviously if we read 0 for x, it must have happened before we wrote 1 to x. I mean, otherwise, how else could we have read it? And the idea is that a graph is sequentially consistent if we can linearize the events. So we can actually get some nice interleaving to get this behavior. Specifically, this is a possible linearization to get this graph. And we don't require more than one. There are possibly more, like we could just swap the initialization events. They don't have defined order between them. But obviously, the graph below is SE inconsistent. We cannot linearize it in any way, since this write has to happen, of 1 to x has to happen before we wrote 1 to y, which happens before we are actually able to read 1 to y. But obviously, it happened before we read 0 for x, which had to happen. I mean, we read from an earlier event. So we have this nice cycle that means that it's SE inconsistent, and we cannot get it under the sequential consistent memory model, but we can get it under the C11 relaxed memory semantics. And the idea that we found was basically that we can actually check this with sequential consistent semantics. Since there's a minimal violation that happens at some point. At the start, the graph is SE consistent. So at some point in time, we have a transition that takes us from an SE consistent to an SE inconsistent under the C11 machine. And since this can be reached, is SE consistent, we can actually reach this state with an equivalent sequential consistency machine with its own memory. And the fact is that we can actually track these kinds of properties about the fact that the C11 machine is going to be able to take a step and the SE machine cannot. We can actually track this with robustness information with tracking that adds what kind of steps am I going to be able to take under an SE machine compared to what am I going to be able to take under a C11 machine. And this means that if we go back here, we can actually, this state, as we said, is we are able to get this kind of behavior under sequential consistency. That means there's an SE machine with instrumentation that can reach this state. We recognize that at this point, the SE machine must read the value 1 for x, but the C11 machine can actually read from the initialization. And with this kind of information, we report a robustness violation and the fact that you can't assume that the behaviors are only SE consistent because they're not. So if you're willing to limit yourself to just robust programs, you can actually verify their correctness more easily. And yeah. So we built a tool called Rocker, which is, allows us to statically, automatically check the correctness of simple programs. The programs are written in a toy programming language that simplifies the memory model. You can port it. And we do the verification assuming sequential consistency. And this nice little tool is written in D, for this is a D conference. So at first, we tried it with only the release acquire semantics. And we saw that Peterson's original implementation that assumes sequential consistency obviously breaks when you try to use it with weak memory model. And Brato's implementation was breaking even under release acquire. And Dimitri's implementation is actually going to work under x86. So you might miss it if you try to check for bugs. And we also see that the store buffer can actually produce the weak behavior while the message passing cannot. As we've seen, it's probably still running, or it gave up, I'm not sure. We can check later. But the key fact that is amazing is the fact that verification time is less than 2 seconds. It's like, I don't need to reason about all this. Just run it through this, and yeah, it's robust or not. And then I can just reason about it a lot more easily. And that's when we added the relaxed semantics. And we found out that Dimitri's implementation isn't actually correct. Yeah, it's amazing. All these smart guys get it wrong, and our tool actually found this automatically without having to reason about. Like, we just wanted to take it as a test case, like, let's see, and oh, it's wrong. Let's see the backtrace. Why is it breaking? And find this silly issue there that's really easy to miss. I mean, if you want, I can take it on offline later and show you how things break there, but it's based on time. So we proposed 2 possible implementations that restore the correctness of Peterson's algorithm for the memory model. And we also see that the store buffer and the message passing both fail. So to conclude, we'll be back at this slide later, but we proved that robustness for C11 is decidable, PCB is complete, and basically given a program with C-like 11 atomics and non-atomics, we just feed it to Rocker. Rocker creates verification problems that assume sequential consistency. We can run this all on a sequential consistency machine. We can on x86 machine. It doesn't matter. We don't need the real actual weak hardware. And then we feed it to the spin model checker that just tells us whether the program is robust or not robust. And you can try the tool without having to actually understand the memory model. It's available on GitHub. And just one more thing to show the example first. So, for example, this is the metrics. I don't have support for arrays yet, maybe one day. But this tries to simulate the metrics behavior that we saw earlier. So all the stores in the specific order, load until we actually see the value we expect. That's a wait. And then reading all the values. And if I don't state the kind of access, then it's going to be the weakest possible. So it's either going to be release acquire if I'm going to write in the release acquire mode, or relaxed if it's in the relax mode. And I can go back and run it for all our examples. Let's just run it for the metrics. So if I assume sequential consistency, then release acquired, then yeah, it's fine. But once as we saw, but once I change it to the relaxed memory model, then yeah, your code is just going to break. Your assumptions are wrong. Don't do this. And we can also state the kinds of accesses explicitly. So here we have all the writes being released. The wait here is going to be acquire. And if we run this example on the other end, then it's going to be robust, since we do actually have correct synchronization like we should have. How much time?
Plenty of time, man.
OK. So yeah, we also have the message passing and some other examples. I can actually just run them all and talk about them.
Well, do you want to run your examples and take questions at the same
Yeah.
time? All right. Well, then, should we do the applause first, then? Now, we do actually have a question from Discord to kick things off from Ricky. And he says you'll know the context about this. How insane is lock-free concurrent data structures, and why is the answer that it is universe breaking?
I'm sorry, could you repeat it?
How insane is lock-free concurrent data structures, and why is the answer that it is universe breaking?
Because you can't reason about it. Reasoning about lock-free, especially with weak memory, is insane. That's why people just stick to the simple algorithms right now, and getting anything that's harder, it's like, good luck.
So I remember a few years ago, the Microsoft team for the C and C++ compiler, they went over the whole standard library and all the library they publish using similar tools to try to detect errors using weak memory models, and they found one not so surprising thing and one quite surprising thing, at least to me. The first one is that there are very, very few uses of them over the whole code base, right? Like the fraction of atomic operation that use weaker model than sequential consistency was very few sprinkles here and there, but almost none. And the second one, like a significant portion of them was actually wrong. And the question that I'm asking myself is, like, are those really that useful anymore? Because if in practice you don't need them that much, and in the few cases where you think you need them, like half of the time you actually don't, you get it wrong. And on the other hand, you look at what CPUs are doing, and they seem to be getting better and better and better actually at being sequentially consistent, even though, like, I would have expected the opposite to happen with more cores and stuff like that, but they are getting better. Like, should we just like say as an industry, like those weaker memory model, that was a nice experiment, but let's just stick to sequential consistency?
So I feel that, unless you know really well what you're doing and try to use all the tools to make sure that you actually write correct code, just stay away from all those relaxed accesses because it's really, really easy to get wrong. There's a question whether the performance penalty is worth it or not, but that's for you to decide if you want to risk correctness versus performance hit. But hey, I get to research this stuff, so I'm doing my PhD over this. So,
I have the mic here.
Yeah.
Is Rocker multi-threaded? Do you trust it's correct?
That's a very good question. Rocker is actually single-threaded. We execute only a single statement at a time, and just like we can do for sequential consistency. We don't care what's the actual architecture that we're actually executing on.
Hello? Yeah. Does Rocker take a long time to run, and how do you feed it code to check? And can this be something that can be added to the compiler as a robustness check? Because whenever I've tried to analyze multi-threaded code, it really hurts my brain. And having a program that is guaranteed to be correct to say whether it works or not, I think is going to be, or is a great boon to doing these kinds of programs.
So I did start on trying to write a minimal C2 TPL compiler so that I can actually test things. C is hard to compile and trying to get all those primitives. So it's going to take a lot of work. Another direction I tried was basically creating my own thread sanitizer that checks dynamically for all those kinds of things, but it's still work in progress.
Okay. Does it take a long time to run Rocker?
Rocker itself doesn't take that long. I mean, for the example programs that I'm showing, it was like a couple of seconds. But if you have plenty of memory locations that you add, or more than 5 threads, then yes, things are going to take a long time.
Okay. Because I'm thinking, like, I've added a borrow checker to D, and that turned out to be quite workable.
So, yeah, maybe there are optimizations I'm missing. I'm not saying I try to optimize it all the way.
Okay. Well, what I'm thinking is I think it would make a nice addition to a compiler or a language to have something like that. It just sounds pretty cool.
Yeah.
I have one question. Even being single-threaded, how did you prove that your implementation is correct?
So what happens is that as long as we have an SE consistent graph, that means that we can actually achieve this kind of graph under an SE machine, right? Mm-hmm. And an SE machine could simply be thought of as taking a statement from each thread one at a time. And what Rocker does is basically check all the possible executions that you might have for this program. So what happens if I'm running this, and this, or this, and this, and that, and all various orders.
But is this, the proof is based on some formal theory?
Yeah, there is a formal proof that this is correct.
That this sequence, but oh, okay.
If you have an SE inconsistent graph, the program is not robust, then at some point you must have had a point of divergence. And we can identify this point of divergence with the instrumentation.
I would buy that, but
you can read the paper.
But you have I mean, is your proof mechanized or something like that?
Some of it is mechanized with Coq.
Okay.
So it checks things by doing a combinatorial exhaustive check of all possibilities.
Mm-hmm.
That's how Rocker works?
Yeah. There's also work, as I've stated, that creating a dynamic one that just checks the branch you're actually executing, but following what could have been. But it's still, as I said, work in progress.
Okay.
Any other questions? Yeah, I just checked Discord. There's nothing there either. Anybody else? No more demos to show off?
I can just talk about the examples, but mostly we can see that.
Oh, that's cool, mate. Oh, hold on, we got a question down here now.
Does the tool show us in what condition it may get that no result? Verbose mode, maybe?
Yeah, there's actually an output from Promela, which is the language spin takes. So for the failures, we have this trail file, and I actually wrote some tracer to help me. And we get this horrible, horrible output that more or less shows what's the order of the instruction it took to get the violation. And I basically just got used to reading this. But yeah, it's obviously not the best option. But you know, making developer tools is hard.
All right. Yeah, I think that'll do for questions time now. So thanks again, man. All right. So another 10-minute break. It looks like we're here a little bit after 11. So go enjoy it. Hey guys, we're going on upstairs again. Come on. Up you come. I know you want to. It's fun up here. We've got aircon. Come on, come on. They normally come. Yeah, maybe we should, I was going to say we should get a camera back then just to see the flood of people coming back up, but they're not coming. This is an anticlimax. All right, how about we just get the talk going though? Yeah, work for you? Excellent. We have another first-time speaker here.
Thank you.
This one's actually a name I can pronounce. We have Sebastian here talking about structured concurrency, so please take it away.
Yeah, thank you. Thank you all for being here. It's a great honor. Today I'm going to talk about structured concurrency. But first I would like to give my thanks to a bunch of people. There's Marin, there's the author of Zero MQ. He wrote a good article about structured concurrency. There's Romanov. He's the lead architect of Kotlin. I got introduced to Kotlin a couple of years back and used a lot of the concurrency stuff, and it's been really good. At the time, I wasn't aware of what it all meant, but looking back, they certainly had it covered. There's Nathiel that wrote the Nodes and Structures Concurrency. That's a very good article. It also gives a good overview. And there are a bunch of names from C++ proposal, P2300. And there's Leith at the bottom. He actually introduced me to the proposal. And without him, I wouldn't give this presentation here. So yeah, the last 50 years, you probably know this chart somewhat. The axis here is logarithmic. So we've seen a huge increase in the amount of transistors. Frequency as well, right? Up until 2005-ish. So back in those days, if you want your software to run faster, just wait a year to buy new hardware and it would go faster. But from 2005 forward, that no longer worked. Because of hardware limitation, physical limitations, it's very difficult to go faster than 5 gigahertz. So what they did instead, they had all these transistors left, all this space. So instead of making it faster, let's just make more of those cores. Except now you can't just buy new hardware and automatically get this increase. So you have to find a way how you can utilize all these extra cores. How can we do that? Well, there are two ways. One is parallelism. When you split up a CPU-bound task into isolated pieces, right? That don't depend on each other, and then run them on multiple threads, or maybe on a whole farm of PCs or whatever. It's not easy to find those isolated pieces. Some algorithms might not have them. But once you have found them, then it's pretty straightforward to execute them on multiple threads. It's basically just a fork, execute, and then a join. With concurrency, you basically have more I/O-bound tasks. So there's a lot of waiting involved. Instead of stalling on the thread, on the core, you decide to execute other work in between. And that increases the utilization of the processor. So another way to look at it, let's say I'm painting my house, right? I can do it sequential, it's just me painting it, takes a while. Or I can get two of my friends to help out once I realize that I have 3 rooms. Suppose all the rooms are the same size and we all paint equally fast, then it's going to take roughly a third of the time. And there's a concurrent way, is when you start to realize that, hey, wait a second, I paint the room for the first time, but then I have to wait until the paint is dried and then apply it a second time, right? And what do you do in that waiting period? Well, you can actually start on the second room. So you do the first room, first layer, second room, first layer, third room, first layer, and then go back to the first room. That way you're utilizing the full core, and you just need one. You just need one guy executing the whole thing. It's not as fast as the parallel one, but it's still faster than the sequential one. Plus, we're using just one core, right? And now suppose that instead of 3 rooms, there were hundreds of rooms, right? Then you can interleave things much more neatly and clearly. And then at some point you're going to outrun the parallel one, because that one has moments in time where it's just waiting on things. But the first one was rather simple, right? It's just one box. The parallel one has 3 and the concurrent one has 6. And there's a lot of managing things, right? You got to keep track of which room you painted and which one is next and all that stuff. So that's certainly more difficult. And there are bugs, plenty of bugs. You've seen in the previous talk as well. Data races, deadlock, live lock, starvation, order violation, atomacy violation. I won't go into all of them, but I found some good papers that analyze a lot of existing software and go into all kinds of bugs there are. The top one I found interesting because it was a recent article by Uber, where they go into detail on all the stupid mistakes they made and all the other stuff. That's very nice. If you go through the papers, you're going to see a very common theme, right? That the concurrent APIs are too low level, right? And it's very, very easy to introduce bugs. And these bugs are not only harder to track down than just regular non-concurrency bugs, but they also can be hidden a long time, right? There are cases where a bug is hidden for years, and then suddenly, because you run it on a different computer, with more cores, different architecture, things suddenly start to pop up. This was an interesting quote I found by Edward Lee. The problem with threads. The threads are a seemingly straightforward adaptation of the dominant sequential model of computation to concurrent systems. Many people are pushing for the increased use of multi-threading, yada, yada, yada. And in this paper, I argue that's not a good idea. Threads discard the most essential and appealing properties of sequential computation: understandability, predictability, and determinism. I would argue for the development of concurrent coordination language based on sound composable formalisms. He was right. He was right. Threads are just too easy to use incorrectly, and not to mention all the synchronization primitives you have and the problems you can have there.
When you're looking at the screen, could you turn your full body, please, so the mic still picks you up?
Uh-huh.
Thank you.
No problem. Good. With threads, you get a lot of non-determinism, right? And you have to use all kinds of synchronizations to get the determinism back in your program. But that's all something that you as a programmer have to do and that you can do wrong. So how about indeed? Well, we have threads too. We have concurrency spawn. We have parallelism task, and there's vibe done retask. There's a bunch of others too. I tried Mecha and Ocean. I couldn't get them to compile, but they all basically center around this similar idea of spawning something and then later joining it. But there's something really wrong with that API. And I'm going to go to the next slide, and just 2 words are going to change here. And I hope that can illustrate the problem a bit. Ready? New and delete. Did you see that? It's just the same API. How does that make you feel, right? Do you like new and delete? Exactly. So what's exactly the problem with new and delete? Reasoning, yeah. Anyone else? Manual memory management. So you might say that you forget the delete, right? That might be the problem. And I would argue that's more of a symptom. The problem is more that we split up resource management into two pieces. One at the beginning and one at the end. And you have to place them, different parts in your code base. And that might be in the same function, or maybe in the same file, hopefully in the same folder, but anything goes, right? So that's a bit of an issue. So I would say the problem is not that you forget the delete, but it's not clear where to put it. Because they're so far apart, and you have to reason about all the stuff in between, and you have to know, when am I actually done with this thing, right? And even when you did all the hard work and said, like, yeah, this is the place where it needs to go, there's no amount of evidence that you can leave behind that actually indicates that it's the correct place. Not for other people, but also not for yourself, right? They just have to take your word for it. And I would argue that with concurrency, with these spawn and join APIs, we have a similar problem. They split up things and then they create some sort of hidden link between them. And that ultimately doesn't scale because there's a lot of things that you have to keep in your head. So concurrency in D is too low level and it's unstructured. It's very easy to spawn things, but it's quite difficult to manage them. That's all pushed on the programmer. It's also not clear who owns what. If you spawn a thread that does a function, who owns it? Is it the runtime? Well, that's not a good answer, right? We want the ownership to be as small as possible. The lifetime is also unclear. With a regular function, you know that it's done when it returns, right? Any local it had, it's all gone. Response, and that's not the case. Error handling as well. Like I tried all the different APIs here, and not many of them do the right thing. Many of them they swallow the exception, or you only get the exception when you actually join it. So that's something that you have to build for yourself. Cancellation as well, right? It's something that you have to add on as your own. And they're non-composable. So it actually resembles unstructured programming a lot, in a way. So let's go back a couple of decades and see how that played out. This is the piece of code. I don't know the language. It's Flowmatic something. I don't know if it's even real code, but it illustrates the point. Just 17 lines. Well, it's 18 run because it starts at 0. But anyway, let's follow them. There are a bunch of go-tos there. So on line 13, there's jump to operation 2. Okay, good. But there are more there, right? There are a lot more there. Just 17 lines, but it's already incomprehensible, right? Imagine having to refactor this, or debug it, or add a feature. It's just madness. Now you could argue it's just 17 lines. If you spend 15 minutes analyzing it, you can probably understand what's going on. But the thing is, it's just 17 lines. What's 5,000 lines? Right? It's incomprehensible. So that's a bit of the problem they had at the time. And the problem of increasing complexity. Many people working in the area of computing have expressed concern with the problem of software reliability. Well, the cost of hardware has decreased, as power has increased, software costs have increased and become more complex. The result is, although we can do more than before, it's at the risk of encountering more serious problems than before, and they prove to be more resistant to solutions. So this is a book from the introduction. This is a quote from the introduction of structured programming. And it was that the demand for software back in the 60s grew so much, right, that unstructured programming wasn't really cutting it anymore. And it was only set to grow more. So in 1966, Bohm and Jacopini, they came up with the structured program theorem. And they state that with just these three building blocks, you can build any computable function, right? We have sequence, that's just executing one statement after the other. There's selection, which we know as an if and else, right? It's a condition and two branches. And there's iteration, like while loop, for loops, that kind of stuff. So there's a condition, a statement, and then it goes back until it finally exits. The one important aspect here is that all of these, they have one entry and one exit. Right? You can't just jump into the middle of things. Right? It's all structured. And these things compose. Right? You can build elaborate programs with it. Here's an example of how you could do that. Now every block here can be abstracted away with just a statement. This large block here, for instance, you can just hide it and say it's a white box, it's a statement. End of the day. And if you do that, if you look at it from a high level, all you see is that it's a for loop. And then at the end of it, there's another for loop, and then a statement, and then an exit, right? So everything can be extracted away. And this allows you to encapsulate things, to hide detail. And that means when done well, you can increase local reasoning. Because if I zoom in on one part, I can forget all the other stuff. I don't even have to know that it exists, right? If I can prove that one thing is correct, the other thing, then by definition the whole thing is. Right? So that gives rise to local reasoning. So that you can reason about something in isolation of everything else and understand the whole thing. So that means that you can scale up your software, right? So software is easier to write since problems can be decomposed into smaller ones. And you can understand them because you don't have to understand everything else. So again, the quote from the book, to check each module independently is an obvious advantage. The clarity, systematic nature, and alliance of controls of the independence of the module is responsible for the superiority of structured programming. It's much easier to tell when a module is being performed in a structured program. They use the word module. I think they mean function as we know it, right? As there's only one way of getting into it and only one way of getting out to it. And both the entry and the exit connect to the same higher level module. Thus, the logic is more easily followed, both with the in-between modules. You might have noticed that this quote is from 97, where this theorem was from 66. It took a while, right, before people caught on. And there were lots of arguments between people. When doing research, I remember reading an anecdote where there were the structured proponents and the unstructured proponents. And the unstructured people were coming up with challenges. They were basically coming up with awful unstructured code and then throwing it to the structured guys and saying, let's see if you can structurize this. But of course they could, right? Because this thing is based on the Neumann architecture, right? It's a natural conclusion. So yes, you can formalize any program in these three constructs. Now today, we use more of them, right? We have exceptions. We still have a form of goto, but it's always goto inside the function, not go to the middle of some other function in another file. That's not what you want. And today, structured programming is just a norm. Right? Not in the strictest form as it was then, but I don't know any unstructured programming language. I don't use one. Well, maybe assembly or something, but you don't see that much. So structured programming is what we do all day, every day, right? So wouldn't it be interesting if you would combine structured programming with concurrency and then get structured concurrency? But before we do that, let's look at the cornerstone of concurrency, which is the asynchronous function. Now, an asynchronous function is just a regular function, except it's asynchronous. So it does all the things a regular function does, and then some asynchronous stuff. So it has arguments, right? You can return a value, you can throw an exception. But where a regular function would run inline, right? The control would be passed from the caller to the callee, and then passed back. An asynchronous function runs somewhere else. We don't care where, but just not here. Also something, a normal function, you wouldn't cancel a normal function, right? Because control is being passed to it, there's nothing to cancel it. You might want to cancel your process from an OS level, but canceling a function doesn't exist. For an asynchronous function, it does, right? We want to be able to cancel them. The owner in the lifetime, that's where it gets a little bit tricky. With a regular function, obviously it's the caller that owns it, right? It runs on its stack and that kind of thing. And the lifetime of a function is always smaller than that of a caller. That makes sense. An asynchronous function, who owns it? I don't know. What's the lifetime? I don't know. That's not good. Right? We want to control these two things. We want to stay in the world of structured programming, right? Because it gives us so many good guarantees, and it allows us to write large-scale software. So about ownership and lifetime. Every asynchronous computation needs to have an owner. I say computation, function, task, similarly, right? Everyone needs to have an owner, like every single one. You can't just do things fire and forget style and just have it run detached or something. And an owner always needs to outlive all this asynchronous computation it owns. This is just like the regular programming, right? If you call a function, then you don't just go somewhere else. And this allows the control flow to be clear when you're reading the code. Despite the fact that you might, I don't know, run a gazillion threads or fibers or whatever. Because there's always an owner, there's always a place to forward errors to. So if you have an exception in asynchronous computation, you can just forward it to your owner, just like with regular programming, right? Exceptions, they bubble up the stack. We want something similar. This avoids exceptions that get swallowed or ignored or stay hidden somewhere, right? We want to get them immediately. Now, but if an asynchronous computation would error, the owner can't just bubble the error up. It first has to make sure that all the other synchronous computation it might run are stopped and canceled before it can bubble the error up, because it needs to outlive all of them, right? So if one of them has an error, it needs to cancel all the other ones before it can bubble up the thing. So that means that asynchronous computations, they need a way to be able to, sorry, I'm going ahead. But just because you want to cancel some work, right? An owner needs to cancel asynchronous computation. Just because you want to cancel the work doesn't mean it's done immediately. It might take a while, right? So the asynchronous computation, they need a way to be able to signal, yes, now I'm done with canceling. Everything is done, so you can continue what you're doing. So to recap. Every asynchronous computation must have an owner, must outlive everything they own. Errors must be propagated upwards, and the computation should support cancellation. It should support cancellation. But the other ones have must, but that one is should. They don't all need to support cancellation, but they probably should. It's probably better. And asynchronous computations, they need a way to signal return value, right, the normal completion, an error if there's an exception, and also cancellation, or that they're done with cancellation. These are a bit of the informal rules of structured concurrency as I phrase them. It's kind of interesting that none of the APIs that we have follow them all. In fact, I would say that all of them break everything. So yeah, if you're doing anything about concurrency, writing a library or wanting to build something, keep these things in mind, right? Because they're gonna make your life and the life of anyone who uses it a lot better. So now we come to the second part of the presentation. Is when we go have a look in P2300, the C++ proposal. And it's a proposal for a framework for managing asynchronous execution on generic execution contexts. That's a bit of a mouthful, but it just means threads, GPUs, special processors, that kind of thing. I have to say I was a bit skeptical at first. Leith pointed me to this proposal, and I read it the first time. I was like, bollocks, go away. But I read it the second time, and the third time, and over the course of months, I was slowly getting warm to it. Right? This is what they say in the introduction. Software is increasingly becoming asynchronous and parallel. They appear everywhere, from hardware interfaces, networking, file I/O, GUIs, accelerators, GPUs, and that stuff. The standard library has a rich set of concurrency primitives and lower-level building blocks, but they lack a standard vocabulary and framework for asynchronies and parallelism. Right? They have async and future and promise, but they're inefficient and they're hard to use, and they lack genericity. So then they go on to propose a model here with three key abstractions, right? Schedulers, senders, and receivers, and a set of customizable asynchronous algorithms. Now, I would argue that the thing that they missed is the word structured. I don't see it anywhere, but it is structured, actually. The whole proposal is. Now, I won't go into a lot of detail on how senders receivers work, but we're going to discuss some example code that uses them. So a sender would correspond to an asynchronous computation, right? It's something that at some point is going to send a value, or maybe an error, or the fact that it's done canceling. And then correspondingly, there's a receiver that receives that value. Here you see a value sender, which sends a single value of type T. And if you look closely, it's just a struct with that one value. There's no overhead, right? No allocations or other stuff. Then the other part is this connect function that takes a templated receiver and then combines it into this operational state. It's just making yet another struct, right? And then the operational state has everything it needs, right? It has the value that you want to send, plus it has the receiver. So now if you start it, it's going to call set value. And that's pretty much it. So how do we use this? So I made a little helper function, just. It just creates a value sender. And there's sync wait. Oh, that's should be purple boxes there. But, oh well. So what we can do is we can take the sender and we can synchronously wait on it. And then, yeah, lo and behold, the value is 42. So what sync wait does is it calls connect on the just sender, which constructs the operational state. It returns it to sync wait, which then starts it and then calls set value. One important thing is that sync wait and the senders in general, they're lazy, right? They don't do anything until you connect and start them. That also means that sync wait starts and awaits it in one operation, right? So we don't split up things and allow you to forget one or don't know where to put it. It's just one place. That might seem small, but it allows you to reason about the lifetime of a sender. Because you know that after the sync wait, it's done. It's not alive, completely done. Before it hasn't started yet. But then again, you might say that, wait a second, this is not concurrency or parallelism. It's all on the stack. Everything is in line. There's no extra thread involved, nothing. Well, we can change that. We can use the via algorithm, right? So we composed the just42 sender via a thread sender. Now, thread senders are kind of interesting in the sense that they're ultimately going to call that value on the context of a new thread. Ergo, it runs the sender on a different thread. Here's a little representation, right? Sync wait calls thread sender connect, constructs the thread's operational state, starts that, and then the thread is going to call set value on the new thread, right? It's going to call connect on the just42 sender, which is going to construct the operational state for that one, and it's going to start the operational state, and then that's going to call set value on sync wait. So we started up a new thread. We call a function from that thread back into the sync wait. That's nice, but typically we don't use thread sender directly. We would use something like a thread pool, for instance, or more specifically, a scheduler. Right? So we take the just42, the sender, and we schedule it on a scheduler, and then we await the thing. Now this does the same thing, right? Except it runs on a thread pool of 2 threads. So it's going to fire up one thread and do the same thing. And one thing to note here is that the pool is scoped, right? So once it exits the scope, the thread pool is gonna clean up and kill all the threads. But it also means that once you schedule a sender on a thread pool, it's connected to the scope. So you cannot escape it anymore. You cannot return it, you cannot do it somewhere else, right? Thanks to DIP 1000. That's great. Next up is a little quiz. We're going to introduce the when-all algorithm. The when-all just takes 2 or more senders and runs all of them to completion. But the question is, what should happen if either foo or bar sender fails? Throw
Throw an exception out of foobar.
Throw an exception. Okay. I think that's good, but suppose foo failed. What happens with bar? The bar sender. So in normal programming, if we have the foo here, and let's say it throws an exception, bar never gets executed. Essentially, it gets canceled in a way. Although it doesn't really get canceled, but we can look at it from that way. So with a when-all, when we're running multiple senders and one of them has an error, we want to cancel the other one. Because we can no longer run all of them to completion because one of them just failed. So we have to cancel the other one, and then wait until it's done, and only then can we propagate the original error. So this means that even in the presence of exceptions and asserts and all that stuff, we always clean up things. We always keep things scoped. And this is not just with when-all. This is with all the algorithms in the library. All of them follow these rules of structured programming, so that you cannot have leaky tasks or things that are still running which you don't know about, but spooky behavior. That makes things for you as a programmer a lot easier, because you can reason about things a lot more better, because you know both of them are going to be long gone when foobar has returned. There's no surprises there, right? Even if they spin up 100 threads on a different machine. And it's also reflected in the code, right? You can use your normal sequential reasoning. Which brings me to the concept of a narrow waist, right? Instead of writing specialized code for each combination of asynchronous computation and asynchronous algorithm, we want to write the asynchronous, the senders basically, just once, and the algorithms just once. By standardizing on the senders receivers as a sort of a glue layer, we can just write the sender and the algorithm separately. So on the right, you can see a couple of dozen I wrote. So if you write a sender, you can just use those, right? And any ones you add, you can use on existing senders. This is the same with ranges or the STL or Unix pipes or JSON or CSV, right? They connect different parts. Now some of these asynchronous algorithms, they're not easy to write, right? They do all the things that the previous talk said we shouldn't do. And maybe I should use his rocket thing to ensure I'm doing the right thing. But the point is, once we do that, these algorithms are sound, right? We can prove it, and then everyone can use them. instead of everyone rolling out their own thing and hoping for the best. Let's go back a little bit to the foo and bar sender and see if we can compose some more. Suppose we realize that foo sender is a bit flaky. Now, we really don't want flaky things, but suppose it is, and we want to deal with it. It doesn't matter what foo sender does. If it's a whole large thing, we can just add retry. Retry max times 3. And ask the question, what happens if bar sender fails? Well, same thing. If bar sender fails, it means that when all cannot complete successfully, ergo it has to cancel the foo sender. Even if it's in the middle of retrying or doesn't matter, right? Okay, that's great. So now we have a colleague, and he really likes the foo bar function, but sometimes because of the retrying, it takes too long, right? So he wants to add a timeout. Well, here you have a timeout helper that races sender against a delay. A delay is just a timer, right? And what race does is it's going to forward the first one that completes after first canceling and awaiting the other one. So by these simple algorithms, right, it doesn't matter what these senders do, if they get it packet from a socket or they read from a file or whatever, right? We can use these standardized algorithms to compose the behavior that we want. It doesn't stop there. We also have streams. Streams are kind of like asynchronous ranges, and they're built on top of senders and receivers. So a stream has a collect function that you pass a delegate in, and then it becomes a sender. So then you can just sync weight it. And it's going to call the delegate 0 or more times, and then completing the sender. So here it's going to print hello world every second, basically, right? And then never terminate until you press Ctrl-C. And streams, they compose as well, right? We can have the same interval stream. We do a cumulative fold or a scan where we increment a number every time. We can filter it, take 5 to list, which is kind of like a equivalent of an array on a range. And then we can sync weight the whole thing, and then we get all the numbers there. So they compose really, really well. So the conclusion is senders and receivers, as in P2300, they follow the rules of structured concurrency. So that many of the nasty details of concurrency can be hidden away. And we can use these senders to build up large task graphs representing complex concurrency code. There's a link to the repository. I had some fun implementing this. Right, the C++ guys, they did all the hard work for me. I think they worked on it for 10 years or something. So I would just have to implement it. How hard can it be? I really like save and dip1000. I think we need more of it. So senders, because they're just structs, they naturally live on the stack, right? And dip1000 helps them to not escape. Every night before bed, I pray for save by default.
You're not the only one.
But in contrast to ranges, the concurrency library requires all delegates or functions to be passed to be safe. I don't infer safety. And the reason is type erasure. The following code doesn't compile because input range object has to be pessimistic. Because you might have created a range that has a system delegate, ergo, the range object has to assume that it's system as well. So it is. right? This doesn't compile, it's going to give an error. I thought about it a bit, and I decided, you know what? This stuff is as hard as it is. You should probably write safe code anyway, so I'm going to make it mandatory. Any delegate you pass in or function has to be safe. Shared. I like shared, actually, for a change, right? It can be your friend too. It helps you to express to the compiler all the things that can be accessed from multiple threads, multiple execution contexts. And the compiler helps you honor that, right? So every delegate that's passed, the user-supplied delegate that's passed in the concurrency library has to be shared. Why? Well, because we don't really know, and we don't really care either, where that code is going to be run, on which thread it's going to be. So all of them have to be shared. But that's a good thing, right? Because it means we can take any sender and just schedule it anywhere. Inline, on a fiber, on a different thread. Plus it also highlights a lot of places in your code which have to be shared as well, because they are shared, right? And this forces you to think a bit about the possible contention there. So over time, I started to appreciate shared. This is a small example of a multi-producer single consumer queue. Multi-producer, multiple threads can push items, single consumers, or just one can pop them, which obviously means that you want to send it to other threads, right? So here we have a little producer function that returns a producer that has a shared pointer to the queue. So that means that you can just shove the producer somewhere else, and they can just call push on it. No one has to cast anything, no one has to do anything. Plus, they can't move the queue over to another thread and start popping from there, right? So we get a little bit of extra safety. This is another one. You might have seen some web applications where you use the UDA to set up a route and then have a handler function there. But if you run it from a thread pool, it kind of means that the application has to be shared, right? It does. So by enforcing that, it means that if you don't make it shared, it's gonna error. This is pseudocode, by the way. This doesn't actually, it's not implemented yet, but it enforces the shared, right? So if it wouldn't be shared, then it wouldn't run. In the summary of the presentation, I also describe the way how you can get rid of all these synchronization primitives. This is an idea from Theodore, and he introduces the concept of a serializer. So what the serializer does, it's a scheduler that only allows you to run one sender at a time. It's just like a mutex, right? So if you represent your application as a task graph with units of work, right? You can't divide them any further. And then schedule the parts that you want to have exclusive execution on whichever serializer you want. Then you don't have to write any logs. Now you might say, well, this is just the same thing. Well, no, it's not. It's asynchronous, right? It doesn't block any threads. It just keeps running. So if you have enough tasks that you can feed to your CPU, it's going to utilize it a lot. The future. Well, there are some places that require more thread safety. There's also a nasty back pressure problem in nested streams. But those are just things that we have to fix. I want to integrate it with fibers some more. Some people don't really like the nestedness what you get. So by integrating with fibers, you can get the normal flow. Event loops as well, scheduler, asynchronous algorithms. Probably good docs and tutorials on how to write custom senders. They're not simple, but they are in one file. They are in one place, right? So the start, the cancellation, the error handling, it's all in one little place. And then maybe something like a task local garbage collector, right? Because you know how long they run, and after they're done, you can just throw away all the stuff there. That's it.
All right, question times now, and we have one from Discord from Ricky. Do we need an attribute to disable TLS access to allow moving fibers between threads for such a concurrency model?
Yeah, that's a very good question. TLS by default, maybe it was a mistake, I don't know. But it makes it difficult, right? If you're going to move fibers across threads, what do you do with that? I don't know.
All right, well, Walter's got a question.
Well, I think by definition, you cannot move TLS data, a reference to TLS data across thread. That defeats the entire purpose.
Sure. Yeah, in general, I would say don't use thread local data. Don't use globals, don't use thread locals. They're just globals, right? So, yeah.
Generally, you're better off if you stick with pure functions. No globals.
I agree.
Aren't you a bit limited by shared, given its current state in the language?
Not really.
Because it doesn't catch a lot of errors.
Like
currently we do a lot of things in Phobos that are completely unsafe from a concurrency point of view, but we gladly allow it. For example, parallel is terrible.
Yeah. I don't have an answer for that, but I still want to use the keyword, right? And then fix that, all those things. Because I think it makes a lot of sense to have something that indicates, hey, this is shared.
I agree. I was just hoping for a list of issues to fix.
I didn't find many problems though, but maybe those will appear at some point.
This isn't a question, just a comment. But I'm going to repeat myself. I'm going to talk about that tomorrow.
Super. There's one more.
What is the semantics for cancellation? It's at composition points only, like you cannot interrupt regular code, right?
Sorry?
So you have a cancel operation timeout and stuff, so it can interrupt this task graph only at composition points, you cannot interrupt like a regular function.
I didn't talk so much about this, but it has it uses stop tokens, right? So it's a responsibility of the sender to hook into these stop tokens, either by checking them regularly or by setting a callback on them. And a sender should, right? But sometimes it's not possible. Does that answer your question?
Kind of. I mean, I'm not sure what is stop tokens.
It's a stop token. So it's kind of like an object that you can query whenever the task or group of tasks needs to be canceled. It's basically a glorified Boolean, right?
Mm-hmm. But so it means when I'm writing the code, it is getting executed by inside of this framework or run by the scheduler. I have to put special checks that are checking for these stop tokens. In my code.
You can check, but you can also set a callback.
No, okay, kind of get it.
Yeah. So very naive example is while running and then do whatever you want to do, right? But sometimes that's not possible. So that's why there's a callback. So you can register a callback on the stop token whenever part of the thing is going to be canceled, that callback is going to be called. You don't have an obligation to also actually cancel. I mean, there might be a race where you're completing and you're canceling, and it's okay if you just complete regularly. But yeah, if you want prompt shutdown, then you should honor these stop tokens and set up callbacks or query them. Yeah.
My question is kind of similar. I'm not sure I understood, but so you start some task, some code. How do you preempt that code? Let's say you start a function that does a while true do nothing. How do you preempt that?
I don't write those functions.
That was an oversimplified version, but how do you?
Well, you can run it. If it's a CPU intensive task, right? Then you wouldn't run it on the same pool that you would with all the other stuff. You might want to run it on a separate thread or separate thread pool. But you do have to listen to these cancellation points.
Okay. Yeah.
Yeah. Otherwise, how can you cancel it? It's just like a regular programming. You spin up a thread that does something. How do you cancel it?
Well, you could send a message.
You send a message.
Like a signal.
Yeah, exactly. It's the same thing. Yeah. Except it's in the framework, right? So everything has that feature.
Well, if it's in a separate thread, you could kill the thread, and that would kill the process or the function.
Yeah, that's also possible. I wouldn't do it.
All right, I think we've got time for one more question if someone's got a good one. It's got to be a good one. Yeah, Walter's got a hand up. That'd be a good one. Pressure's on, man. Please deliver.
Well, I think the idea of composability seems so obvious. Why did it take, 30 years to come up with composability for multi-threaded code? Do you have any, do you know why it takes so long before this happens? Why are we, or is the computing community as a whole going around the horn and finally coming back to where they should have started from, which was composability?
Yeah, it's a good question. I don't have a good answer to that. I think there have been some competing ways of doing concurrency, right? But we kind of got hooked on the whole threads for some reason, because maybe it's just easier to just spin up a thread and run stuff there. I don't know.
I certainly never thought of it either.
Me neither. And took these guys like 10 years to come up with this. It's actually, once you understand it, it's pretty simple. But yeah. I don't know.
I think it's one of those amazing things where, like, ranges and algorithms, or in the earlier version was iterators and algorithms, is once you see it, it all seems so obvious, but it completely escaped me and most everyone else.
Yeah.
So I think it's brilliant.
Well, all credits go to other people, right? Not me. I just make this presentation. Although I implemented the library, that wasn't certainly wasn't easy. But
since a lot of the C++ work on libraries is done using the Boost license, wouldn't that have made it easier to basically copy the way they did it? Because if it's Boost license, it allows us to do that and save you a lot of grief trying to reinvent it.
Yeah, I'm not sure if it's easy to interface with it. Also, the code is longer. You can compare them side by side and then make up your own mind. Although in C++ they might have a little bit more features in terms of R-value, move semantics, and that kind of stuff. But the D version is surprisingly simpler, I think.
Yeah, well, that's great. I like that.
All right, and we're done here. Give it up again for Sebastian.
Good. Thank you.
All All right, now you have an hour and a half for break because it is lunchtime. So yeah, back here at 1:30 and we'll kick it off. All right, this is what I like to see. People coming up the stairs before I've said to come up the stairs. This is great. Come on. Hello, everybody downstairs that's not coming up. It's time. Can they hear me down there? No? All right. Well, I like talking to myself anyway. It's a good side. You know, you should all try it sometimes. Just get some things out off your chest that you wouldn't talk to about anybody else. You do feel a lot better for it, so highly recommended. How you doing down there, Attila? Eh? Yeah, that's about how I feel too. Yeah. For those that did not hear, the comment was that he would address it in his talk tomorrow. Yeah. All right, how was lunch, everyone? You all good? Full of energy, or are you now in a food coma and need to sleep it off? Both? Yeah, that's what the coffee's for, right? You wake up during the food coma. Cool. All right, well, it looks like we've mostly got everybody back here. Before we kick off for the afternoon, let's talk again about lightning talks. Because it turns out that we have had a couple of submissions now, and there are 2 remaining slots. And I know out there somewhere 2 people want to talk about something cool and have a chance to do the Ali maneuver. So I recommend it. It's fun. See, you know, I've got my stick and it was still fun. So I definitely recommend coming up and doing it. Yeah, just speak to Mike if you've got a suggestion. We've got 2 slots left. So get in quick if you're going to do it. I think that's about it, which means we can start with yet another first-time DConf presenter.
Thank you. Thank you.
Wow. All these new faces, it's great. We should have this more often. Anyway, Mike here is going to talk about ray tracing in less than 1 weekend with D. That sounds cool. Go for it, man.
Thank you. Thanks for having me, everyone. Thanks for joining me for this session. I guess you didn't have a choice either way. Just a quick show of hands. How many people have done graphics programming previously? Okay, so good chunk of the audience. Wow, here. Okay, well, I got to be careful what I say then. Now, this talk is aimed at sort of an introductory audience, so for those folks, I hope they'll appreciate it, and I'll address the experts in a little bit here for what you'll hopefully get out of the talk as well. So slides will be available. Some goals for today, though, just to get us kind of structured. You're going to be learning about building a ray tracer in the D programming language. Again, lots of folks here have some graphics experience. That's awesome. And maybe you can sort of challenge yourself to move on to the next weekend or the rest of your life, the other texts here. But this book here was written by Peter Shirley. He's worked in academia, NVIDIA, various other places. And it's really been a great starter for getting folks introduced to graphics programming or really just creating projects in general and finishing them. So I really, really like this text here. So, you know, to the D experts in the room, which is everyone here, or many folks, I should say, you know, I don't think I have any amazing D language tricks to show you today, actually, because I myself am pretty new to D programming. But, however, you know, I hope this is going to be an inspiration for you, and this can be interactive too. So you can raise your hand in the talk and suggest something, and I'll let you know if I address it later, or you know, secretly, my plan is we have a little hackathon coming up, so I'd like some folks to, if you're not sure what to work on, maybe we can kind of rile things up on Twitter and start posting lots of ray tracers done in a day. But every time I build a ray tracer, I learn something new, and I've done it in a few different languages, so it's kind of a fun way to see how you do things in D versus C++. It's sort of my go-to project when I'm learning a new language, which is nice. So for the experts, you know, sit back, and maybe you'll just enjoy this talk for why you really enjoy the D programming language. And for any beginners, students, folks listening to this in the future, you know, I hope this is just going to serve as an excellent introduction for you to learn D or get excited about this programming language. So again, why ray tracers? They're quite compact. Again, you can finish them actually in a weekend if you follow this text. I know I finished mine. You'll see little hour markers here. Or you can make a career out of it. This is not some, you know, just hobby thing. This is actually a really hot area right now, so I'll talk about that in a moment. And this is also, you know, a good thing to suggest to friends, or if you're involved in teaching or training, when they ask you, hey, what kind of project should I build? I think ray tracer is a good one, because you can focus on performance, software engineering, many different facets, which I'll try to highlight a few of those. And my claim, again, is today I'll show you what I built in well under 24 hours. Now, the slides in the talk probably took more time actually to build than the ray tracer itself. So I'm your guide. Just the highlights here. I'm a teaching faculty. That's my primary focus, but I do consulting and graphics, these kind of things, so you can find more information about me. Primarily, I come from the C++ space, so that's where my influence comes, but that's changing a little bit, I guess. And again, for the folks online who are going to join in the future or later, again, if you go through the D tour on the D programming language page, and just complete the basics, you're good to go. You'll have enough knowledge to complete what's shown in this text. So I hope, again, that's something to motivate you. And again, I'm admitting I'm no D language expert, so please don't ask me to do template metaprogramming live or anything. Although in D, it's actually quite nice, though. So the code for the talk's available, and I've tried to tag as well with the chapters of the book, something reasonable if you want to sort of build up or follow along with how I've done things here. Okay? And the later chapters will probably get cleaned up more and more as time goes on. So again, there's the abstract that brought you here. But getting into it, ray tracing, what does ray tracing produce? And I know I saw a lot of hands go up in the audience that are maybe familiar with this idea or graphics, but let's just get everybody on the same page. And part of the fun is you get to look at some pretty pictures. That's not all of what graphics is about, but it is a fun part. So if you've seen any sort of Pixar animated films, Disney films, cartoons, anything that's sort of digitally created where they're synthesizing images, they're probably using some variation of ray tracing. So this is from Cars, which is a movie that extensively used ray tracing. You could read about the Pixar papers. In fact, for the more advanced students I have here today, that might be a good place to look for some graphics information. But again, you can kind of notice some really nice details in this scene here. Here's just another fun scene, or maybe a little bit scary. But this is actually a real-time ray tracing shot from Epic Games' Unreal Engine, where they're doing some ray tracing in real time to demonstrate some new hardware from NVIDIA. So this is kind of cool to see that. Again, it's not just long ago, ray tracing was this sort of pipe dream of can't we do it real time and simulate, how things actually look. Well, again, today that's why this is a relevant topic and something worth considering starting. And just sort of for fun, for ray tracing, if you play games, Minecraft's a great example. Folks have sort of modded this particular project to use the non-ray trace version here, and then through some graphics code, enhanced it quite a bit. So you get a little bit of a prettier experience if that's what you'd like. So again, what's going on here? Again, just to give a definition, ray tracing is a method of graphics rendering that simulates the behavior, the physical behavior of light. Thought to be decades away from reality, NVIDIA has made, et cetera, et cetera. Great job, NVIDIA. They're really doing some cool hardware stuff here. But really, it's that first sentence here that we're trying to simulate the physical behavior of light. And that sounds kind of cool and a little bit daunting in how we're going to approach it. But that's what we want to think about when building this ray tracer here. So let's go ahead and just take a look at the ray tracing algorithm just at a high level. Again, we want to understand what the problem is, and then we'll try to figure out what the components are, and then we can actually write some code. All right, so again, the cool thing about ray tracing is that sort of, is exactly what it sounds like, something about shooting rays out and casting them into some sort of space. Okay, and that's exactly what it is. So, this diagram captures it pretty well here, where you have some virtual viewpoint, and you can see the laser shooting through here. This is your screen here, or what would be, your monitor, and then you have, in the digital world, some representation of geometry, some objects. You cast out a ray, do a test, and say, did it hit some object? And that's the basic premise here. Okay, did some intersection occur with a ray? Again, just visually, here's another analogy for you. Again, it's exactly like using a laser pointer against a wall here. Although there might be some other nuances too, because the laser is actually going to, again, simulate light and bounce around. And if you look really carefully, we have some different materials here, the wood floor, and you might be able to catch a little bit of the reflection as the cat's chasing the laser there. But that's the goal. So just put yourself in that mindset of holding a laser pointer and kind of shooting it back and forth. Now again, for folks in the graphics world, ray tracing again differs from rasterization, which has been the typical thing that's been used if you're working on interactive applications, games, VR simulations, these types of things. So on the top picture, what we're doing with rasterization, which is real time, is just saying, hey, we have an object here, color in the pixels for those objects, essentially, if they're within the camera view. Okay? And that's a little bit different of a premise versus ray tracing, which what we're talking about today, which is, again, taking our laser pointer and just shooting at different points and seeing if it hits an object. And to even be a little bit more precise in that, we're firing a laser pointer through every pixel, maybe more than one time. So I guess if I gave you a moment here just to look at these pictures, does anything jump out to folks about what's different versus the top or the bottom image? What do they notice? Yeah.
Reflection?
Reflection, yeah. So in the bottom one, I see it here in the teapot. Looks a lot nicer. And that's a big one here. The reflection, I'll just call it a few more. The shadows, the same idea about we're simulating light. So we get some of these things, I won't say for free because there's a cost in terms of the CPU, but as far as the algorithm goes, it's a lot easier than trying to figure out what's going on with rasterization and simulating some of these effects. All right, so let's start making our way towards some code here and building a ray tracer. Okay, just a few examples we can learn from. So, an example in C, and you might use C again for performance. I'm going to show you the performance of D later for the ray tracer that I built. And this one's just a fun one on the back of someone's business card, to generate this Pixar image. And the point, again, is to just show you how compact a ray tracer project could actually be. Now, they're using some cheap tricks here. They're defining, R as return and these kind of things. But the point is, this is a compact and can be a small project here. But again, let's try to figure out some of the key components so we can start architecting our ray tracer. Okay, so here's one that I built in Python not too long ago, again, from Peter Shirley's text. So here's what it looks like. Again, quite beautiful, I guess, for what it is, a few spheres. And again, we're capturing some of these things like reflections, and there's even some shadows. Might be a little bit harder to see on the monitor, but under the spheres, we can see some shadows. So it looks quite nice. But structurally, again, if we're thinking about this as a sort of software engineering problem, what types of things do we have? What types of things might we want to model in our actual code? Well, we have a few objects here, 3 spheres, and this floor on the bottom is actually just a giant sphere, like our Earth. So it looks flat, but it's a sphere. And then each of these objects have different materials. So you'll notice that 2 of these spheres are kind of more reflective or maybe metallic. While up here, this thing that looks like the sun or whatever you want to call it, it's a little bit more of a flat color. Right? It's just sort of emitting almost, or appears to be emitting. It's not quite, but it's just a solid yellow material. So maybe different materials are going to be something we want to keep in mind here. Then we have our camera that's looking out into this world, so we need to sort of keep track of that, what's going on here, this sort of viewpoint. Right? That's our virtual eye into the world. And then this canvas, well, that's going to actually be important too. What are we drawing to? Where is our actual pixel information? So we're going to need to model a canvas in some way. And finally, we're going to need some math. In fact, most of this is math. Now don't worry, I'm not going to get into the scary bits here. And actually, the scary bits aren't that scary. And Shirley does a nice job sort of walking through each of the math bits. And this is actually the exciting part, seeing all the math that you've learned in your past come together in something that you can use. I always tell people I'm in the rare 1% of almost every math thing that I've learned, I actually get to use almost on a daily basis when it comes to graphics. Okay, so again, here's the ray tracer visualized, right? Here's the image that we're trying to produce. Here's our little algorithm where we're thinking about shooting rays and intersecting with these objects here. And again, we could sort of just visualize these things as happening, 1 pixel at a time. So I've sort of visualized this 1 line at a time as this is growing, but you can see the image sort of building and building and building at this point. All right, so here's sample of the Python code, and I don't want you to look at that. It's too small. So here it is blown up just a little bit more. And the real goal here is that we're going to iterate through each pixel. Again, hope that's clear. Cast a ray, that's our laser pointer, out one pixel at a time, and test if that ray hits anything. Okay, and what it's going to hit, well, we'll sort of have to model that as some object in our D code. Okay, and if you want to move things around, like if you want to create a motion picture, you can create another loop that sort of adapts your scene and just repeat this process, right? And this is how motion picture is made. All right, so coming from C++ and Python to D here, it's time to get started here. Now, I really like D because it really is, to me, and I'll try not to repeat myself too many times, but I think it's true, a software engineer's language, for actually getting stuff done. So let's go ahead and dive into this. All right, so beginning our journey here on ray tracing. So this is the first hour of 24, roughly, as I relive this experience here. So the first thing, again, that we need is to generate some sort of image if we're starting with this problem. And this is kind of a cool part because when we're thinking about an image, we're mapping actual hardware, what it's going to do, light up pixels, to our software. So we need some representation of that, right? And typically we can just have that direct mapping, what an LED is, something with a red, green, and a blue light, and represent that as a pixel. And then we'll need to write that information out to some image format. And in this case, it can be an almost raw pixel data, red, green, and blue pixel components, one after the other after the other. Okay, so that's going to be our goal, to generate some image here. And from Shirley on the C++ side, this is our first goal. Just get something up and running, and then we can kind of iterate on it, which is a nice way to approach this if you're just starting some project. So you can literally take this snippet here, and I'll play it here. And I'm going to run it fast, but you can take that code here, right, and this is me doing it in one take. And I'm just going to convert it to D, and you're going to see me get rid of the includes, put in the imports. Let me just speed it up just a little bit here. 2 times. All right, see how it's going to go for right line, etc., etc. Speed it up a little bit more. All right. Get rid of those things. Okay, we're doing things the D way for just writing out some raw pixel data, and then we'll write it out to standard out. Get rid of the static cast. I use toInt here to cast my type here. Oops, one syntax error. Don't worry, D helped. And then we get some image like this. Okay, so not too bad here. We've got our first image, and now we can, we've got a canvas to paint on at this point. All right. Now, again, you might have caught what I did here, casting. I got rid of the static cast from C++ and changed them into the conversions here using the conversion library. And this is actually a pretty important mechanism when it comes to ray tracing, because ray tracers themselves, when you're sort of adding things or subtracting things, are very prone to overflow, because we're essentially accumulating light or accumulating values into something. So I want to know, especially if I'm sort of casting data back and forth, did I do an illegal cast and have something that might overflow? And more than once that happened, even as I've done this many times before. So +1 right there already for using the D language here. Now I know there are some ways to do things kind of statically, and we can get some of these advantages in D as well, but this worked beautifully for me for just getting started. All right, so now let's start to add a little bit of abstraction to our canvas. This is the next few hours here, right? We want to start painting more on this, and maybe even start thinking about some shapes that we can draw. So again, the D language, we have classes, we have a way to build user-defined types, and I'm going to need some way to store pixel information. Okay, so again, as I'm casting rays and seeing if they're interacting with objects in some way, at first, maybe I'm just hitting some object and need to store that information. But again, since we're simulating light, it might bounce around a few times, so we also need to consider modifying different pixel locations, and it's not just a linear one pixel after the other in that way. So, long story short, we need some canvas or essentially an image class to draw to. All right, so here's a class. It's labeled ppm because that's the image format that I'm using, which is essentially, it's almost raw pixels with a little bit of a header describing the magic number for it being text space, the width, the height, and the maximum range, typically 0 to 255. All right, so classes in D, very nice, constructors, name things this, okay, no problem there. No destructors, right, garbage collected by default. It's making our life easy to get up and running. We've got our member variables here. And individually, I can specify the protection level. Again, that's something that I really like doing, sort of as needed basis. Defaults in class are public, which I think, again, the defaults in D are just correct, having defaults. And that's my note about this. But beyond even having the defaults, there's actually properties associated with these. So if I'm using different types like integers or shorts, I can actually know what the minimum or the maximum range is without having to rely on implementations from libraries and such. So again, this is very nice for a clean implementation here. And I can pack everything away into these nice modules, which is what I did in my ray tracer, right? I'm not battling header files or C++ files and worrying about the different compilation and these sort of things. It just packs together nicely in a module. And I can put correlated stuff in the same module and distribute it in that way. All right, and then as far as writing out the actual file, because we want to do this is again going to be very familiar. Again, I know to this audience it will be, but for newcomers, right, if you've worked in Python, C, C++, we have similar file utilities. And more often than once, I'm finding myself converting more of my code from other languages like Python into D because I keep stumbling upon even more useful tools in the standard library in Phobos, like the JSON library most recently. All right, so now that we have our canvas we can paint onto, we're about ready here to start drawing some spheres on our canvas. And we're already getting to hours 4, at least from starting to 10. Uh-oh, what happened? Maybe progress slowed down. But anyways, we want to start drawing some shapes here. And this is where I start to slow down a little bit. I'm like, OK, I got to figure out the math a little bit. And this isn't something that we're going to go through today, but some equation of a sphere, right, to figure out if a point is actually intersecting with a sphere. Right? So again, take your laser pointer out, shine it to some object, pretend it's a sphere, and it's either completely missing the object, that's what it means here. Maybe it's gently grazing just the side of it, so we can count that as hitting the object, or maybe it passes through 2 times. Okay, either way, that's the information that we need to say that we intersected with some object. It's interesting, maybe color that pixel a different color, whatever the object is. Okay, that's the idea here. But we need some, again, math to do this. So the next abstraction to start thinking about is array class. And again, this is how we've been sort of modeling ourselves in the real world, right? Taking out our laser pointer or flashlight or whatever you prefer. And again, definition of a array mathematically, right, is something that has some origin, where we're going to start from, and a direction, right? Some vector, so something that has a direction and a length or magnitude, whichever you prefer. And that's how we'll model array, right? Now, this is probably where I start spending a lot of my time here, where we get that 6-hour or whatever that estimate was time frame here from 4 to 10 hours, is building the actual vector3 class. Okay, so in its simplest form, we need a way to store x, y, and a z value. Okay, so vector, again, I didn't put in too much of a primer here, but that's just something with a direction, right, and a magnitude, so how long it is, that tells you something about it. In 3 dimensions, we need x, y, and z. So something like this is fine as sort of a bare minimum vector, right? And there's a few other things I'm going to add to this. So it just needs to store 3 doubles, right? And oftentimes, we might even be tempted to make this templated. But as a graphics programmer myself, I usually just end up using doubles always, so I never do it. But you could, right? It becomes trivial in D, so I just wanted to show how easy templates are to use, right? You just put the type there, substitute it, and you're done. So I love that, if I want the option to do that later. Now I do have to think a little bit about the types that I build here. Again, what our abstractions are anytime we're building some software. So vec3, it's just a x, y, and a z value. But that's also sort of like a point in space, right? Because we have an origin where we're starting from, so that's really a point in space. Or a color, that's also just sort of 3 values. Usually we'd think R, G, and B here. So what we can do, and this is the same thing I would do in other languages, is just try to provide some sort of alias. So that's what I've done an example up here for different names here. Now, do we get the type safety with this alias? That's actually something I have in my little bullet says that the non-D expert in me wants to ask the audience later if there's a better way to do this. But at least as a library developer, if you're building this type of thing, the context matters, right? When I have a function like cast ray and I have an origin and a direction, that says something to the actual developer, right? And you can see I can get away with actually mixing these up. Which is dangerous. So maybe there's some precondition or some contract or something that can make that a little bit safer. But there's certain rules mathematically, right? Like adding 2 points together doesn't really make sense. But a point and a direction, right? Pretend you have a point and take a slingshot, give it a direction. That makes sense. 2 points together, adding them doesn't work. Okay. So anyways, that's just a little note here, right? I love having these features to easily alias things, without doing sort of type def madness or defines or these kind of things. Now, where this really wins and where D always wins and why probably the next time I teach software engineering, I'm going to use the D language, is the built-in unit testing features. Because this is where I really save myself. Because this vector3 thing, if I'm telling you this whole project's all about math, it has to work, right? I can't mess up here. So this is a huge win here for test-driven development, which is what I'm practicing here, right? Maybe this is where I'm paying my time. A little bit more time up front doing some test-driven development is going to save me later. And I think that's the case here. Okay, so this is very critical that I can just bundle in some unit tests as I implement new functionality into this vector class. Okay, so you can see some examples of just assertions that I have here. And I have many of these, and they're not all just clobbered into one unit test either. So more times than once, just to show you some examples. Again, it doesn't matter how many times I've done this, but I forget to check when I'm doing a divide, is this less than or equal to 0? So I run into it, and then I can make this little amendment here. And again, I love this, that this is caught as a overflow or an underflow, or not a number, or whatever error it gives me. As I'm catching these bugs even and just using different features, I say, okay, it would be really clever if I, maybe I should check if this vector or something is 0. So I sort of add a member function for that, or you could have a free function as well. And you start writing these little functions here, and then I ask myself, while I'm using this language, is, hey, I'm guessing at some magic number here, 0.00001. That's a pretty small number, right? So if it's smaller than that, it must be 0. It's like, oh, well, I could just actually look at the properties here, floating point, and see, hey, there is an epsilon here. And again, there are, min and max values here that could be used in a much cleaner way. Again, I just, you can tell all you folks who are working hard on D are engineers actually using this stuff, which is awesome. So I'm catching bugs using this. Vec3 also tends to be something that lends itself well, a vector class, a matrix class, these types of things for operator overloading. Maybe that's a controversial subject in various domains for code clarity. But I found it well worth implementing, at least for Vec3, to make my life easy. And then I think the final thing I'll say about Vec3, again, just leveraging the uniform function call syntax, because all the time I'm doing stuff like this, where I have some ray here, that's what R is representing, and I'm trying to get the direction, and I also want to convert that to a unit vector, or some form, or maybe grab some other attribute. So these things are kind of stacking on top of each other. And again, it's just a really clean way to program and have this by default. All right, so at this point, once we have a reasonable vector-3 class, I can actually start drawing some spheres now, because we can actually start casting some rays, and, well, that part I skipped over, we can actually model a sphere here. But we're basically just testing if some ray passes within a radius. And for now, this is just centered at 0 to make things easy. Now, folks want to wonder about why the color, why is it sort of this bluish glow? I've got a little footnote here about why that is, and I'm calculating something else called a normal, so I know where rays are bouncing. But the way I'll explain it is, again, take out your laser pointer, shine it on maybe a metallic sphere or something. It's not going to bounce straight back at the same angle unless you hit it right on, right? It's going to bounce on a different angle. And that's essentially what the normal information is giving you. Okay, pretend you have a ball, or pretend you have a porcupine in your hands. Be careful. But it's got a bunch of spikes coming out of it. Those spikes are the normals, right? Telling you if something hits it, roughly what angle is it going to reflect off of. All right, so we finally got our sphere here. And again, I think you folks will be a little bit quicker than me. You know, I think you'll get more than a sphere in 11 or 13 hours. But again, I'm walking through this. I'm exploring D. I'm trying to do a little bit deeper dive. And I think, you know, you folks are sharper than me. And speaking of being sharper, you know, if anybody has 20/20 or better vision here, this still doesn't look quite right to me, this sphere. So I got to take a little zoom in on it. And what we get here is these sort of jaggies. That's one of the technical terms here, I guess, from graphics. But you know, we get this sort of noisy edge, right? This isn't a sphere. This is something that, you know, if you rolled it, it looked like it would stop. You know, a sphere should actually be smooth. Okay, so we can perform this sort of anti-aliasing or denoising of this edge here by essentially just taking more samples of all of our pixels. So again, pretend you're shooting your laser pointer, but you decide, hey, I'm going to shoot it, but just move it just the slightest bit and in a random direction. And maybe do that 100 times and kind of accumulate some color around there. Okay? And that's going to help smooth out the shape here. So when we perceive it, it'll look more round. Okay, so we need a random library. And of course, D has got it built in the Phobos library here. So we've got a lot of different options here for what types of random number generators we want to use. And depending on, you know, what you want to do, you might not want it to be an unpredictable seed. You might want something that you can retest. And again, this is where the unit testing stuff comes in. But you know, I'm able to do this here. So, you know, generate some random numbers here. And you know, maybe a few other helper functions. Again, we can do things like operator overloading, no problem, right? Some things that we can't do in C, but you know, I might want different parameters for a min and a max random number that I generate. So, you know, in my eyes, the left one, well, I guess when it's this zoomed in, it might be a little bit confusing what's going on. But when we zoom out, the left one's going to look a little bit better. Here, let's zoom out a little bit. And I changed the color. This is where we're going here. But that looks a little bit more spherical. And maybe if you have really good vision, you'll still notice, yeah, it's a little bit pixelated, but there's more techniques to improve that. All right, so we're getting to the home stretch here, hours 14 through 18. And at this point, you know, I'm not counting. I don't have a timesheet, so I'm just guessing here. But we do have one sphere here on top of another really big one here. Okay, so now I'm trying to get to 2 objects here. That's what this is sort of building up to. So how do we handle multiple objects? Well, we need some way to sort of manage them here. And you know, usually that means if I'm going to have multiple objects, I need some sort of container, some sort of data structure to start putting things in. Well, D's built-in data structures essentially give us exactly what we'd want, and it's usually a default, you know, a dynamic array is easy enough. So I'm able to just create this dynamic array. I call it hittable. That's the same thing Shirley calls it, some object that if you point a laser to, you can actually hit something. And you know, we can append to this at runtime, again, if we're doing things in real time or whatever, and that works just fine here. Okay, so easily done. Now structurally, again, though, we do want to think a little bit about what we're engineering here. So, you know, again, you know, am I going to have more things than spheres? by now I think you folks are going to get bored of spheres here, right? We want other things, squares, cylinders, other shapes, triangles, triangle meshes. So we are probably going to want some sort of abstraction here. And again, I think this is just comes to the language creators, of making this decision on, supporting interfaces, like many other languages do, like Java has these, right? But this idea that you have a abstract or truly abstract class, right, that you can derive new objects from, but you must implement these member functions, right? That's the rule of the interface. So again, this gives us a common ground and probably the right thing to do, because again, later we're probably going to want things other than spheres and so on. All right, so now we're approaching the grand finale here, hours 19 through 24. Again, I probably lost count, but in reality, this was about 2 full days sittings, okay, just if you're measuring this out. And now we want to get to something a little bit more interesting here, these spheres here, okay? And they're different colors, maybe even different materials. So this part here, again, we're trying to scale up as we go, build something more interesting. We can have more objects now. We have a data structure to store things, so we can sort of check that off. More colors, okay, maybe even different materials, right? Different things are going to happen when we shine our laser pointer on, a wood floor versus a metallic sphere. All right, so same idea. We've already sort of made this design decision, but we can have some interface for different materials. So again, what happens when I shine on some object that's hittable? Is it metal, like I have here on the bottom left, or is it just some solid color that's always going to shine red or gray or whatever the color is? Okay, and again, this helps me in some sense, at least with this current abstraction, try to keep a flat hierarchy, keep the code, tame the complexity a little bit here, and that's sort of the goal here. All right, so here's our final product. Here's where you land, or somewhere where you land after the Shirley book. By the time you read almost all the book, at least through chapter 9 through 5, he goes and does some other stuff. And then there's the next weekend book as well. But I do want to show a few software engineering things along the way here, what I enjoyed with D here and in doing this project. First, the performance here. I'll show you what my debug build is. Now, mind you, I just wanted to show some stats here. I had Chrome running, so this wasn't a clean experiment. But these images do take a lot of time to render. And I'll actually show you which image this was on in a little bit in the bonus section. But it took a little while. And I was actually doing this today, and I was saying, come on, hurry up, I got to give a talk. 20 minutes. So ray tracing can be expensive. Now the release build and some optimizations, right? You can see the time severely cuts down. Maybe there was some caching. Maybe I closed an extra tab. But I mean, in general, it's generated the image faster. Okay, so a loose performance experiment. Now the good news is you get things like parallelism out of the box, which again I think is an excellent thing in D that this has been incorporated so early on. And we've seen a lot of talks today about structured concurrency and making sure we get concurrency right and some of these different things. So parallelism is certainly an option. And that's what I think I'm going to toy around with at this hackathon here that's coming up. And I also have my note here. Most of the time when your program's slow, this is actually a major data structure problem that we could improve on. And maybe I'm seeing a few graphics programmers nod their head and saying, yeah, casting a lot of arrays, you could, you don't have to cast all of them, but, so some things to work on. So debugging, as I was going along with this project, anyone spot the bug? This is in GDB. I'll give you a hint. This is the next thing that's going to execute. Well, I'll just show you because, oops, forgot to, do new here. So I had a segmentation fault. My note here was just that, D, at least the DMD compiler on my Linux machine was working wonderfully on, just integrating with GDB and using all the GDB knowledge that I had previously had. So I really liked that. It made it easy to find and track down bugs and have a sense of what was going on. Okay, I will try on GCC and LDC later. Just to try to track down more bugs. And there's more stuff, more software engineering stuff. Again, that's cool, that's built into these compilers. Things like the code coverage, the build system with Dub, having a package manager. I didn't use any dependencies, so I had this sort of hacked together script here just to make things as bare, minimally simple as possible. But this is a big deal to have a working package manager, Dub, right? And have that be part of the culture here. So overall, it's clear to me lots of software experiences going into these libraries and the thought process. Okay, so some more resources for more ray tracing, because I'm kind of ending you with the image here, and I know you're hungry for more, thinking about the hackathon here. But there are 3 books in this series here. This is book 1, what you get to learn. Then you get to move on to even cooler stuff, textures, and the techniques they use in the movies. A few other guides here, and then general D language stuff here. So Ali's book, Programming in D, and then the D language tour. Those are great resources. I'll point this one out here. This one's particularly great. Ali, since you're in the front row seats, I don't know if you remember this. Let's see here. But just a quick thank you for gifting me a book 5 years ago, and here we are. So I was volunteering at a conference, and you say, here's a book for my, I was doing the time, that was my job. And you gave me a book, and I still have it. That's true, that's true. That's why I'm still here. So thank you for being generous. So I thought that was kind of funny. So anyways, in summary, I hope you've enjoyed this journey, and it's been kind of it's been really refreshing being part of the conference and just refreshing and ramping up on a lot of this D stuff. And I hope you are going to take on the ray tracing challenge here. And tag Peter Shirley. He likes almost every post if you show him a ray tracing thing. And of course, we're going to start using hashtag DLang to promote that. You can tag me if you want. I don't care, but at least these 2. And I do have some bonus content here, which we have like 2 minutes. You got 5 left. 5? Okay. So the first, so I really love teaching. I'm going to be doing more YouTube stuff with DLang because I think that's something needed in the community. So you can click on this video later, or August 13th officially, and you can see me getting surprised at how fast it is. So anyways, just some fun stuff. And one more image, right? We got to end on something fun here. Well, let's see. And see if you find the Easter egg here. Maybe it'll be easier. Let's see here. Does anybody see a cryptic letter here? I couldn't do uppercase. It took too long. Yep, yeah, we see just over here, D. Yeah. And it shows up in the reflection, too. So this was the image that took 20 minutes to render. There were a lot more spheres and reflections and things. So with that said, thank you for hosting me here, and I'm happy to take any questions or comments.
Yeah, Walter had his hand up first.
Well, I thank you for making ray tracing understandable. I didn't really know how it worked before. Now I have a ground level understanding. And I wonder if you could publish the 3D model you made of Ali and ray traced him.
Yeah.
I think that would be pretty cool.
That's going to be the first one, absolutely.
All right, thanks. And first of all, I would like to say, for those trying to get into advanced ray tracing, I would like to voice a strong recommendation for the book Physically Based Rendering, which is also free online, and it has basically all the advanced techniques in it. And second of all, I think everyone here has been waiting to say this to you, but I think you can get a lot of speed for free if you use structs instead of classes for your vectors.
Yeah.
In your slides, you had like 2 questions. The first one was about how do you get a type-safe way of using the alias? One way that I'm aware of is if you use a struct that contains your vector with being double, for example, and then use alias this, then any call to your struct will instead go to the alias member, and then you'll also get type safety. So that's one possible method.
Awesome.
And then you also had a section about operator overloading, where you're overloading the different plus, minus, multiplies.
Yep.
I noticed you were using just a normal if statement, which means it's checking at runtime.
Yep.
But because your first parameter op was a compile time parameter, you can instead use static if, and you can have that decided at compile time so they don't pay the runtime cost of doing that if statement.
Awesome.
Yeah, it's like a better const expression if. So.
Yep.
I would like to add, instead of a struct, there's also a very nice one-liner which I use very often to make type-safe aliases. It's just, instead of alias some type equals another type, you can do like enum some type colon other type, and basically because of the dspec, the enums, they have like inheritance thingies, like you can cast one way implicitly, but not the other way implicitly, and you need to explicitly cast, so you have like basically safety for whatever type. I often use it, for example, for error codes in C APIs. You have like win32 error codes, then you have like enum win32 error colon int, so it extends the int, and then you just cast your win32 functions to return win32 error, like that enum thing you have.
Awesome. I'm going to ask more questions in my slides next time. What problems do I have?
You mentioned that you used a double as the underlying type in the vec3s. So my question is, have you run into some inaccuracies when using single precision? Maybe like errors that accumulate with every bounce, or is it just arbitrary?
I think, for this one, doubles is fine. I actually, I actually wanted to toy around with the half float and see if I could notice a difference, and maybe start from there, and see if I would notice. I guess one of the issues, there's so many rays cast, you do get a little bit of drift in the floating point values, right, as you're multiplying things over time. Nothing that I'm noticing here to my eye.
Okay.
Yeah.
I think half float would kill your performance though, since you have to emulate it. But,
Yeah.
But just to see if there's a precision loss or something that's notable.
Yeah, that would be interesting to see.
Yeah.
Yeah, well, I would think in a scene that small, looking up with singles is fine, but on the surface, when you're doing surface operations, that'd be a perfect domain to do halves.
Mm-hmm. Yep. Other questions?
More questions, come on, this is a fun topic.
Maybe you mentioned, but I didn't catch it, what the compiler were you using, and maybe it's implied, but I'm not sure. Have you used the optimizations?
Yeah, so the DMD compiler is what I was using, version 2, actually I could check here, whatever a very recent one from like the last month. Optimizations, I was just running -o, and that's it, yeah. So I think there's tons more that could be done for the performance. I even maybe hesitate to put numbers in without a controlled study.
Yeah, you might want to try LDC and just see.
Yep, absolutely.
We've got a couple of comments from the live stream. Jez Higgins says that was a really fun talk. Thanks.
Yeah. Thank you.
And Bastian says that standard.typecons.typedef is another alias alternative that makes unique types.
Awesome.
In the standard library.
Awesome.
I have a comment here, and I realized you were creating random number generated objects in every little function there.
Yeah.
That may also add to the slowness. Kick them
Yeah.
out.
Yeah. I noticed it while I was presenting, but you guys are sharp. Like I said, my talk for next year is going to be problems I'm having, and help me.
Yeah, I think honestly we can save time and just put together a hackathon work group for optimizing the ray tracer.
Yeah.
Then we can do one or two more questions. Amory was just stretching.
He does that at every DConf.
Anyone else? No, I guess not. Okay, well, thank you again, Mike.
All right. Thank you, everyone.
All right, we got another 10 minutes, so enjoy it. Guess what time it is, everyone? No one? No one wants to guess? No one? Ah. Yeah, that's the one. It's time to come back upstairs. No, they can't. Like we've established, I do enjoy talking to myself, and I have the mic, so I do have, kind of a control over the proceedings here. But, it's not my job to talk for the next 45 minutes. It is, in fact, Dennis's job to talk for the next 45 minutes. That's right. Not only is he a first-time DConf presenter here, look at him. He's lifting the game. Even Walter looks underdressed.
Thank you.
So, yeah, definitely approve of that. Anyway, take it away, the jack of all trades.
Thank you. Good afternoon, everyone. Today I want to talk about why I use D so much. And after thinking about it, I found out that the reason I like it so much is because it's a jack of all trades. It says it right on the homepage. The best paradigm is not to impose something at the expense of others. And D offers all these kinds of paradigms, such as object-oriented and contract programming, all harmoniously integrated. And, well, the flip side of that is that a jack of all trades is a master of none, as the saying goes. You have all these paradigms, but you don't do any of them, you don't go to the fullest extent for each of them. But the full saying is actually, it adds, but oftentimes better than a master of one. And that's what I'm going to talk about by first kind of going over some of the advantages and disadvantages of D being like this. And I'll also show some of my projects where I use D in some rather esoteric environments and kind of show you can truly use it in any scenario you imagine. So as a first-time speaker, I thought it would be good to kind of introduce my own programming, because it also gives some context to where I'm coming from with my points. I started programming in 2008 in GameMaker. As the name implies, that is a game engine. And I was writing games, also some other things, but primarily games. GameMaker came with its own GML language. Here's a code snippet of it. What I really liked was that all code does something. There's very little boilerplate with class. It just reads almost like English text. If keyword is pressed and you're on the ground, then you can jump and you play a sound. And one thing I also really liked about it is how in the editor you could just compile it to one single executable file, send that file to your friend, he would double-click, and he was running your game. That's pretty good user experience, in my opinion. From 2015 onwards, the next 4 years, I suddenly started using a lot of other languages. What happened here? Well, I started my Bachelor of Computer Science at Delft University of Technology. So they have all kinds of courses there in all kinds of domains, and many of them have a specialized language. Though the main language we used was Java. We used it for basically the basic algorithms and software engineering stuff. In Java, not all code does something. There's a lot of boilerplate and factories and stubs. Here's an example that kind of illustrates the problem. But actually, it wasn't even the language itself that was so, it wasn't that much worse than GML. But it doesn't compile to an executable, but to a jar, and it requires a setup, not just for you, but also for your friends who wants to play it. And at the time, there was, this was what Java setup looked like. It tried to install some crappy toolbar in your web browser, and that is just unacceptable user experience to me. So I always thought I should, for my own project, use C++. It's going to be my favorite language once I learn it. Of course, you find some things that you take for granted in Java. In C++, I got segfaults instead of exception traces when I was dereferencing a null pointer or doing endless recursion. And also, I still had to ship glf3.dll, which is a windowing library, because unlike GameMaker, C++ does not come out of the box with functions to check for keyboard presses and things you need in games. And I wanted to not have, to also send this DLL alongside the executable, but it turned out to be really hard to embed it in C++. One fateful day, I found D on a benchmark site. So I was kind of curious about the performance gap between C++ and Java. And I can't find back the original sites exactly, but I remember seeing a table in there that looked like this. And I was like, they made a sequel to C++? And it's not even that much slower. It's the same performance ballpark. And yeah, after checking out some of the articles, I was kind of convinced, yeah, this is a language with good rationale. They had all these articles saying, oh, this is the clumsy way you do it in C and C++. And here's the obvious way that you do it in D. And yeah, I was sold. Of course, there's also the meta-programming thing, which I wasn't familiar with, but it reduces boilerplate, which harkens back to my point that I like code that does something. And it compiles to .exe, being a native language. And on top of that, on the D idioms block, I found my exact use case of embedding a dynamic library in an executable. And it's as simple as one line of code. You just import, give a file name, and it's as simple as that. And that's kind of the character I give to D. A lot of things that, why doesn't it just work? Well, in D, it does just work. So yeah, afterwards, I didn't, for my personal projects, I kept using D. Here I listed some of them, and I'll cover some of them in my talk. And why didn't I not use specialized languages? I got an introduction to all these languages from my university courses, but still I kept writing code in D in all domains that I ever touched. And it's not so obvious that one language to suit them all is the right choice, because it does result in a lot of complexity in the language, which I'm going to discuss now. First of all, there's some complexity in the specification. So this is the section of the grammar that describes conditional compilation. It includes just version and static if. And this is the entire syntax of Lua. It covers everything. It fits on one page. And D has pages of grammar. And I was so impressed when I saw this, that's it? You don't have to make a complex language. And this manifests as complexity for the user sometimes, because when I need to aggregate two integers, in many languages there's just one sensible option. In C you have a struct. In Java you have a class. In Lua everything is a table. In D, well, you have structs, classes, a Phobos tuple, not to be confused with a compiler tuple, and a static array. And it's great that it has these options if you need them. But when prototyping, I often find myself kind of slowed down by having to consider these options. In these other languages, I just surrender to the fact, well, I have to use a class. But in D, I just always have this idea that I should at least consider all the options. Finally, the complexity also shows in the design of the language. So this is a simple example of string interpolation, where instead of, in the first right line, I have to alternate strings and variables to kind of concatenate them into one. Wouldn't it be nice if you could just put your variable directly into your string literal? This is a feature that exists in other languages. Why don't we just add it to D? There's popularity for it. It's the third item here in the State of D survey from 2018. Well, we tried, but the first dip got rejected, second one got withdrawn, and the third one is still a work in progress. Why can't we just get it in already? Well, D being such a big language comes with its own design challenges. We have not only just runtime parameters, but template parameters to consider. We have add_no_gc, which are functions that don't use the garbage collector, which is a shame because the garbage collector is what makes interpolated strings so easy to work with in scripting languages. We also have the unique challenge of generating code and mixing it in with a string mix-in, which also means that things like using braces to delimit variables is not a good idea because braces also appear in your decode that you want to just mix in. So some people want it to work with printf for some reason, and despite all these challenges, we still want it to be simple and easy to use. We don't want to introduce a bunch of corner cases in the language. And anyone can come up with a complex solution, but it takes a genius to come up with a simple solution. So now the question is it maybe better to not have one language that fits everything, but instead mix languages, for example, write high-level parts in Python and low-level in C, or scripting parts in Lua in an application written in C#? Well, I have had some experiences with that, and this is why I'm going to cover them, and we'll kind of see how that worked out for me. So for one of the university courses, we were programming a quadcopter, and it had a little embedded board, had some embedded code written in C, because it's low level. But our team, we were doing this in a project, in a group of 5. We wanted some extra credit, and we decided to implement a GUI. And for that, we used Python, because it's more high level and has all these libraries for mathematical plotting and such. And the GUI would kind of just show the sensor values and help kind of see why it keeps crashing into the ground. But how do we send the data from C over to the Python GUI? Well, we wrote this awful big printf statement that just generates a big string of JSON and then send it over to Python via a socket. Needless to say, this is kind of hard to maintain. And every time you change or you add a variable, you have to also, don't forget to also update this monstrosity. So that was one example of why it didn't really work to mix those two languages, why it wasn't very ergonomic. Another one is where I got to do some Lua scripting. So who knows this game? Super Mario 64. See some hands? Yeah, I love this game. It was a pioneer of 3D platformers. It was back when these games were still on cartridges, while other consoles moved on to CDs. And while I was coding in GameMaker and struggling with my 2D collision checking code, I always wondered, how do the big guys do it? How did they make all this 3D collision checking? Well, and that's how I kind of got involved with reverse engineering the game, and there's actually a bit of a community around it, because people are to this day still doing all kinds of challenge runs, like speed runs, and trying to beat the game without pressing the jump button, which you might have heard about. It gets very technical. So, but for my reverse engineering efforts, I was using the BizHawk emulator, because, how do you debug this? Well, on a Nintendo 64 console, it's really hard. It wasn't a game that was brought on PC, so I run an emulator on my PC that mimics the Nintendo 64. And with the Lua scripts, you can kind of poke the RAM and print some variables. And it's supposed to be easy, right? Lua scripting, it's a scripting language. You get started very quickly. But what I found there was that small scripts quickly turn into like bigger projects, and the complexity increased, and it's no longer really a script. And it happens always very suddenly. I never noticed that my code has become so large until I found some like runtime nil errors, and I have to kind of backtrack and find like and untangle the spaghetti I just created. So one common problem I got with nils was that some library function said, oh, I don't want to convert a nil to string, but where did the nil originate from? Well, it originated all the way back from my tables, which were missing some entries. So I actually wrote this function, which is a big function, to kind of go over my tables and check the types and print errors if like some field is missing or has the wrong type. But it was like, it's kind of annoying that like my code that actually does something has also this big block of code that just for checking, can't I just reduce it to like some small annotations and then put the checking? Static typing, I just wanted static typing in my language. And I'm glad that there's now some typing information in Lua. At the time, like in this emulator, there's no support for that. So that's why I wasn't very happy with Lua scripting in this emulator, unfortunately. The domain was just a bit, it got just a bit too complex for a script. Meanwhile, the reason why dynamic typing is sometimes praised is that you don't have to type all these types. But like in D, you also don't have to write types, right? It is a static type system. But still, I don't write int here. I just write a generic max function that returns the maximum of 2 numbers. And I just write a t in there. I don't say it's int, but you can instantiate it with int or float or any number type that implements the comparison operator. And then when you call it, it automatically instantiates with 2 integers. And then the variable x is also typed int. It's all inferred. Never did I write int. So in my conclusion, I don't like scripting languages that much. I prefer static typing because it never stays with scripts for me. And I want to highlight one piece of design that I really appreciate and I think is a bit underappreciated in D, and that's the fact that there's just one slice and dynamic array type. And I've heard some people say that it kind of conflates 2 different concepts, slices and dynamic arrays, but for me, I really like how I can write a low-level function that just uses some C function, does some low-level string generation, then easily pass a slice to that to some high-level function and append to it. But this was like stack-allocated data, and I can just append to it. It will not corrupt memory. It will GC allocate, copy it there, manage it, and then you can use it. Nowhere did I have to convert from like the crappy built-in array to the array list or std vector that's actually good. There's just one obvious, simple array type that works with everything. As some user on the forums put it, Mikri, the D2D foreign function interface, as it were, is really good. So now I want to talk about some of the esoteric targets where I ran D code. So going back to Mario 64, I wanted to implement a collision viewer where it kind of shows like how the game internally sees the world and how you collide with it. But yeah, the Lua API was too limited for me. I could maybe draw one triangle, but more than that, it would slow down significantly. So the other option I had was to just hack the game's source code, right? It's very easy. Just write some MIPS assembly, because the Nintendo 64 uses the MIPS architecture, and inject that into the main memory instead. But of course, this led to a lot of bugs because handwriting MIPS assembly isn't very practical. All these instructions, all they do is just generate a pointer into an array. And yeah, you can tell it's a RISC architecture, because in x86 it would just be one instruction probably. But yeah, so an alternative would be to maybe write my own language. I could make a bit of a macro assembler, because the problem with just existing assemblers and programming languages is they usually compile to some binary file, and I want it in a running emulator process. So, and I also just like doing projects even if they aren't the most practical thing. Sometimes it's just fun to code and try some new approach. But I haven't created my own programming language yet. I refrained from it. I found out that the LDC compiler actually has the flags to generate MIPS code. And it also has the output S flag to generate like the assembly code instead of just object code, which I could maybe feed into my own assembler. But I found a bit of a problem with the labels, because sometimes, an instruction says like jump to this label, but the label is defined further down the line, and you don't know the address of that label yet until you get there. So after reading up a bit about solutions, I found out that this is a job that the linker usually does. The linker has this relocation table, which is basically just a list of to-do lists where it says, I wrote 0 for now, but after linking, go back and put in the actual address over there. And it turns out that linkers are actually pretty simple. There's this great quote from Walter. A linker is a very stupid, pedestrian, straightforward program. The tedium in writing a linker is usually all about decoding and generating the usually ridiculously overcomplicated file formats. But if you do that, you don't even need the assembler anymore. You can just write a simple linker. And I can attest to the fact that they are ridiculously overcomplicated. For one, I was using the ELF binary format, but it's also the same with other formats. For one, there's a lot of sections that I just don't need. Like I'm interested in the code, not some kind of meta data. But also, MIPS defines like 100 of these relocation types. I implemented these 4. This was all I really needed. I don't know why there are so many. Like, I know there are some things I didn't use, like thread local storage, but in my opinion, these should just be good enough for all the code, for most code. So the result, I'm actually going to try a little live demo. So let me boot up the emulator. So I'm trying to insert this decode into the emulator. I'm gonna run the game. All right, so I have the game running here. And I would like some input from the audience, because I could have just written this secretly in assembly. Let's add some string. Does anyone know a funny word, funny phrase, something short? Just scream it. D-rocks. All right. Let's try this. Put it a bit lower. Then I'm in my demo 0. Sorry, Roberto, I count from 0. I'm a programmer. OK, so I ran this command over here, just LEC, and I passed this file. Now it's generated this assembly file, as well as the object file that I'm actually going to use, which I can view here. Let's see. Then I added a bit of a map file, because the game has some functions, and I need to tell the linker, like, here is the address of these functions. And it seemed it worked, so let's see if it actually does. Hey, it says D-rocks over there. And above. Thank you. So yeah, and the thing that you already saw probably was a simple A press counter, which you're trying to minimize in certain challenges. Yeah, I can also maybe even show in the hex editor. Let's see if Windows magnifier works. Unfortunate, I cannot enlarge it with the Windows magnifier. But yeah, it's in this is the code it inserted directly into the emulator without, writing to disk. And this was just a toy example. What I actually used this for was like for some actual application. I had this replay. So there's these things that the Mario 64 community does called task competitions, where contestants are given like a week or two to create their own speedrun in an emulator, and they just submit all their runs, collecting some coins and finishing as fast as possible. But all these separate speedruns, I thought it would be really cool if you could actually see like them all in the same time. But the game is not multiplayer, so I wrote D code to actually enable this. And yeah, I wouldn't have want to write this in MIPS assembly ever. So let's see. Let's close the emulator, or else my battery is going to drain before the talk is done. Let's go back. Yeah. So the result was that I wrote these ghost compilation. That's annoying. Did it lose the video connection? Oh, it's back. Nice. So yeah, of course, not the full D feature set is supported. It's a very restricted feature set, basically like better C, but even less than that, because sometimes LDC at the time did not implement everything for MIPS, like passing structs by value, so you sometimes get a cryptic error like that. But still, it's a lot better than assembly, and of course, there are still benefits of using D over C, even in a restricted feature set, like the familiar syntax, reusing your already written D code, and the import statement from before also came in handy here to just include all the replay data. So for my next example, where I ran D on a, well, not that esoteric target, but not very well supported target at the moment in the browser. So usually when you write code for the browser, like your options were for a long time limited to JavaScript, and there were some like options with plugins for Java applets and Flash Player, which are now phased out. But in recent years, browser client-side coding became more accessible with WebAssembly, and in summer of 2018, LDC added this target, and so I wanted to try it out. I could finally write code for the browser now that actually I could use D instead of JavaScript. But it's still very limited. Similar to the Nintendo 64, there's no runtime provided. It's basically just an instruction set. But at the time, I wrote a simple, a decent ultimate tic-tac-toe game, which is like an extension of tic-tac-toe that's a bit more interesting. And this was using better C. But an example that's a bit more impressive was my exact math calculator. So sometimes I want to simplify a formula with variables, like square root of x plus x times x. And you can go to Wolfram Alpha, type it in, and then it takes a while for the server to respond, but eventually it gives you some result. But this is not programmable. You can use Mathematica, but that's not open source. And I was looking for some open source alternatives, but I tried some keywords like, variable math library, exact math library. I found a lot of libraries that work with numbers, but none that could really handle just an x. So I started writing my own, thought it was another fun project. And yeah, I did find out that SymPy exists, which is basically what I was exactly looking for. Turns out the magic words were computer algebra system or symbolic math. But I still kept on going because, this is Python. And second of all, I had some cool ideas you could do with D. For example, using generic number types, because D has operator overloading, you can define your own number types. And I thought it would be cool if I could make a symbolic math number where you could, instead of an integer, you could also have a formula like 3 plus x, and make it a drop-in replacement for float. So here's another generic function. This inverts a 2x2 matrix with a generic number type. And you can instantiate this with float and double. But it would be cool if I didn't have to write a separate matrix inversion logic for my symbolic math number. But the challenge is a float is a value type. So when you assign one float to the other, you get a copy and you can modify it, and the original remains untouched. But when you have a tree data structure, you have indirections to the child nodes. And if you have mutable aliasing, then you may inadvertently also modify the original variable. But D actually has a solution for this, and this was inspired by big integer in the standard library and the invariant strings, the Digital Mars article, which talks about why a string is an immutable char array. By using immutable on the element type, you are guaranteed there's no mutable aliasing. So you can just implicitly convert a const math number to a mutable one. And that helps it really feel like you're just using a simple 32-bit float, but it's actually secretly a big complex tree object. So I wanted to use WebAssembly for this. That's what I started with, using WebAssembly. And normally I use all the attributes in D, like pure, I don't like global variables, safe, I don't like memory corruption. No GC, no throw, it's not per se bad to have allocations and exceptions, but when you run on these esoteric targets, you don't have the runtime available, so it makes your code more reusable if you don't use it. But for this one, I did use a GC because this was one instance where I really didn't want to manually manage the memory in a tree data structure. I was trying to get the math correct. I didn't want to get the memory management also correct at the same time. So my previous WebAssembly example used the better C subset, but this one used the GC. So what happens if I remove the better C flag? Well, the runtime is unfortunately not ready for that yet. Currently, there are a lot of errors because it doesn't define certain C constructs for the WebAssembly target. And the solution to that is you can actually use your own object.d. So object.d is this module that gets imported implicitly into every D module, and it also imports all the things that cause the errors. But if you just pass your own object.d to the command line, then it will use that instead, and you can just implement the parts of the runtime that you actually need. So I took Adam Roop's WebAssembly example, took his object.d, and kind of added the things that I needed for this project to actually work. And yeah, passed that to the compiler. So this was my build command, like it specifies WebAssembly stuff. But also, it lists this on the command line. If you just put it in the root of your directory, it will always use it, which isn't ideal. But this way, when you pass it, D will use your own runtime instead of the installed one. Another quick demo. Let's see. So this was a small web application that I made. And it's very interactive. You can just type formulas, and it just prints the result as you type it. And you can make your formulas very complex. Also, it has a lot of features, like even octoliterals. I can answer Walter's question very easily. It also has binary literals, because I like them. Yeah, so that's pretty neat, I think. So it's almost actually a programming language. I thought if I just add variable assignment and a few statements, it's probably Turing complete, but I refrained. I haven't programmed my own programming language yet. It leaks memory because I haven't implemented actual GC. It just uses the null GC, meaning allocate, never free. And yeah, Sebastian knows more about why it's difficult to implement GC in WebAssembly. So that's an ongoing challenge. But for now, it worked OK. I haven't used it for so long that I got any problems yet. And I could also just occasionally restart it if I really need to. As for the drop-in float, I got very far, but there are a few instances where the D language is not powerful enough to have a truly custom number type, like implicit conversions or construction. if you have an array with number literals, you cannot make it implicitly convert to your custom number type. You have to add like a constructor call for that. But if you take that into account, it is still pretty easy to just write code that works with either a basic number type or your own custom number type, which is really nice. So my final example is running decode on the graphics card, except I didn't actually run decode on the graphics card. But I think it's an interesting case study because it kind of shows what happens when you are using two languages and one of them is D. So the difficulty is that usually what we've done so far is we fed our source code to a decompiler and it generates code for a specific target like x86, your usual, what most desktops use, WebAssembly for the browser, MIPS for my Nintendo 64 emulator. But graphics cards don't have easily defined instruction set like that. Usually what you have is an API like DirectX, OpenGL, or Vulkan that translate your shader code in some shader language to something the GPU understands. And it varies per like GPU vendor from NVIDIA to AMD, and also like older and newer versions, they change a bit. And there are some, there is progress in having something like SpirV, which is kind of like WebAssembly as far as I understand it, that it's like an intermediate thing that compilers can generate, and then it's easily translated to actual GPU instructions. But so far, I stuck to OpenGL. That's what I'm familiar with. So here's how OpenGL works together with D. So let's say we're rendering a simple triangle mesh. We usually make models from triangles. And the corners of these triangles are vertices, and they are an important piece of data that's needed to render these models. So you have defined this structure that, in this example, has two attributes for each vertex, a position in 3D space and a color. And then you have your shader code. This is not D, but GLSL. And it takes some vertices with attributes. And in this case, it multiplies a matrix, which allows you to have some transformations like rotations and scaling, and that gives it its 3D look. And of course, this is just a very simple example. Actual graphics have a lot of more components than just a rotation. But how does GLSL know? Like, it expects these attributes. How does it know our actual struct layout that we use in D and that we and that the data has that we send to it? Well, that's what you do with function calls. So you have to define a vertex attribute array, which describes all the attributes. And you have to kind of tell, like, oh, yeah, this position is float. It has 3 elements. It has stride of 16, because the struct size is 16, and offset. And this is, of course, very brittle, because if you change any of this, you also have to change that, or else it just is a mismatch, and you don't have any type safety at all. I think that OpenGL has the worst type safety I ever experienced, and I've made handwritten MIPS assembly. Because when you fuck up in graphics, you get a black screen, and you don't know what am I supposed to do with this. I can't step through it. I just have to guess what went wrong. Well, occasionally you get lucky and you inadvertently create some abstract art. And from the artifact, then maybe you can backtrack and kind of figure out what went wrong. So let's improve this using D. First step is to avoid the magic numbers and try to document nicely what we're actually passing. So components, we access the length of this static array, and we use size of and offset of, which alleviates some of the magic numbers, but we can do better with D, of course. We can actually just generate all the right calls in one go. So what this little piece of code does is it defines a function, takes a generic vertex struct, so we can pass this to it. Then it iterates over all its fields using tuple of. It queries the array type, it queries the element type, and then based on this inspection, it automatically passes the right constants to the function call. And this is very robust. I can just change my layout however I want, and it just still works. And this is a minimized example, of course. But in my real code, I expanded this to support basically all the other OpenGL types. Like you don't just have float vectors, but also integer vectors. And there's also something I still want to do is support not just an array of structs, but a struct of arrays. And that can be more efficient for cache in certain circumstances. But I've been very happy with the results so far. What I've also done is automatically generate the GLSL code, because like, why do I have to write this if I know, like, if I can give a vertex struct, I can also generate this part of the shader, and I don't have to write that myself. So using D with metaprogramming, it makes interfacing with other languages very ergonomic, but I still prefer to just use D everywhere. It's still not perfect. There is still some friction that I don't know how to get around. An example is in a D struct, Booleans are 1 byte. In GLSL, they are 4 bytes. Another difference is the array syntax is reversed. It uses like the C convention. And also, this is a dynamic array, which is under the hood a pointer and a length. But GPUs don't like pointers at all. What actually happens here is it puts the array in the struct, which is also why it can only appear once at the end of the buffer, because you don't know how large it is, and if you put something after it, you don't know where to put it. And so there's still some mental friction where I have to kind of switch with, oh, right, this is not a D type, this is a GLSL type. Hence, I wish to switch maybe sometime to also write D code in shaders. Wrapping up. So the point of this talk is not that D is a paragon and all the other languages are just that. There's a lot of merit in other programming languages. They're doing really nice things, and I also have a lot of pleasant experiences with other programming languages. But like from my perspective and from my experiences, D was just a really great fit, even if it didn't like have all the support out of the box. I like tinkering with it and doing some things myself and see if I can use it even here, even inside a Nintendo 64 emulator or something. And yeah, the disadvantage is that D is a bit of a complex language. I wish it were a bit simpler. But the reward for it is that if you get things right, like slices and stuff, then you're able to write reusable, robust, and flexible code and run it everywhere, and I don't have to rewrite my algorithms for different languages. And that was my talk. Thank you.
All right, so question time. Who's got a question? Up there.
Have you tried anything with automatic differentiation? Because if you haven't, you might like it if you've enjoyed implementing computer algebra.
Automatic what?
Automatic differentiation.
Differentiation?
Yeah.
I don't know what that is.
You'll like it.
OK, I'll keep it in mind.
And then one other thing is that have a go with dcompute, which for anyone who doesn't know is the D on GPU solution. It's not there yet for graphics shaders, but for compute shaders, it actually works much better than you'd expect.
Yes, I've been meaning to try that out. I was aware of it.
Shout out to Nicholas Wilson.
Yeah, there's another trick, which is you can use GL shader binary, and that will, in AMD GPUs, I think it just spits out an ELF binary, which then you can patch and reload. And that could be another trick to just, with an LVM backend, you could get AMD GPU code out and then patch the ELF file with whatever D code you want, and then reload it.
the thing is, I'm not sure, like, how those like inputs and outputs would work. I've never done that, but there was a pretty cool talk which I'm trying to remember the name of about that, which could be pretty interesting.
All right.
For your use case.
But are you talking about OpenGL using this? Because OpenGL has a way to save binary, but it's not a binary that's portable. It's just for the computer you run it on.
Yes, that's the only disadvantage.
But
for AMD GPUs, pretty much it's always the same, and you would only need to have a small switch depending on the vendor, but it would be mostly portable-ish.
Yeah, I do not recommend that.
No, it's fine.
Any more questions? No, what's that? I made a joke in the chat that I was going to suggest that you put DConf into Mario. And now I'm being reminded that I made a joke into chat. So any chance of a DConf in Mario demo?
Let's see. Here we go.
Yeah, I don't think I'll ask you to replace Mario's voice with DConf, but
Let's repeat it a bunch of times. Let's see. Let's go.
Thank you, Mario. All right, surely somebody there must be nerds in here that like Mario. Any Mario questions? Come on. Nah, I think this looks like a crowd that wants to have a break. All right, well, thank you, Dennis. And yes, that is a reminder that there is a DConf again tonight down at the Fox, just like last night. You know the deal. But yeah, we've got, we're a little bit early here. Yeah, that's a 12-minute break for you guys back here at 3:30. Now, I'm still convinced that I can get people downstairs to listen to me here. So, hello, can you hear me downstairs? It's time to come up. I do get a good echo when I cut my hand over this. That's not too bad. Yeah, hey, you can, here, Amari, tell everybody to get up.
To get up?
Get up the stairs.
Oh.
Everybody get up the stairs!
All right, everybody, we are now at a death metal gig. I hope you don't mind.
Well, that's like the vocals Mike Portnoy did in...
Oh! Comment down there, we cannot spell death metal without D, so I think we found the music of choice for our language. Disco. Ah, where's Walter? Is Walter into disco? That was about his time.
Do you know Battle Beast? They have a few tracks.
Battle Beast, yeah. They're finished. Oh, yeah, I think I came across that the other day. Yeah, Disco Battle Beast. Anyway, it looks like there's a good number of us here, so let's continue this on the road. Now, Max here has done the online DConf before, but this is his first in-person DConf presentation, so yet another first.
Yeah.
Oh, you're not going to applaud Max? Come on. So, well, I mean, his slide is a little bit on the, what's that term, nihilistic side? None of this matters, but a little bit of a scribble out. Some of it matters, so not pure nihilism.
Well, I had to look up what the title was.
Yeah, that's cool. I mean, I don't even know what's going on today. I can't remember this morning, so you're doing better than me. Anyway, take it away for us, please, Max.
Yeah, so there are some things I wanted to talk about computer hardware. And but I'm being deliberately realistic by saying that really none of it actually matters, except that some of it matters when it does, unless you're for example from Weka, in which it matters probably quite a lot. But I'm going to start with this is a kind of contrarian hot take, in that I think like computers are quite important, and that we use them. We use them every day to do our jobs. But do we actually need to understand them? Show of hands who's actually kind of like sat down and read a book about how computers work. Excellent. But there's a kind of Pareto principle in that you don't really actually need to know, say, how to implement a processor, which I actually was going to try and show some Verilog code on the screen. But I realized that would probably be quite a bad idea. But there's also even aside from productivity, it's also just interesting, which is a very like expletive-laden quote by the old editor of New Scientist, where someone asked him, why should we read your magazine? And his quote was basically along the lines of like, science is interesting, and if you disagree, you can something off. Yeah, but then the question then is basically how much to know, which is really like a couple of like key things, which we'll find out later is basically one thing, i.e. memory performance. But there's also for the new programmer or someone new to a given architecture or type of computer. There's also the fact that the hardware is implicitly provides an API, whereas based on kind of the way I'm talking, you probably think it's a performance talk, which it will be. But I also wanted to get this out of the way in that if you're, for example, new to computers entirely, you might be very confused by how floating point works, for example. But there are also systems which have completely different or more subtly different types of floating point, for example. So you have to be kind of aware of what you're actually dealing with. And this talk is also basically a superset of the things I said in the DConf Online talk. So if you want to know about how to profile decode, watch that one, because that's much more of a like, if in this situation, do that kind of methodological talk. So this is mainly things I either was sort of too stupid or too lazy to include in that one. But just kind of setting the stage. If we compile hello world, like the compiler does sort of something, i.e. magic. It's another talk. Turn them into instructions, and it gets loaded into memory, and then we run it, and then something happens. And the temptation would be just to talk about, for example, like the as I mentioned, the AI API. That API also has a layout in memory. So, for example, that's an x86 instruction, which is quite useful to anyone who's ever benchmarked anything on x86, probably. Which is it reads the timestamp counter, and the P means something else. But I'm going to try and avoid talking just about the kind of the semantics of the instruction sets, because it actually doesn't. It's part of the kind of the interesting stuff that comes outside of the 20% that gives you kind of 80% of the useful understanding. And I'm also given that it's a further on the API thing. We've just had Roy's talk, which basically covers everything I could have said about any multi-threaded code, only far better than anything I could have said, because he's a domain expert. Yeah. And there's another reason to not spend too much time talking about different differences between architectures, in that there's basically a handful of instructions that actually do sort of 99% of the work. Only in practice, it's closest sort of like the architecture overall will have maybe somewhere between sort of 50 and 200 instructions, which usually are there for a reason, even though there are some which kind of they're all equal, but some more equal than others. And that, for example, like ARM had an instruction just for accelerating JavaScript relatively recently, and x86 has somewhere between sort of 1,000 instructions, and I think if you include the whole lot, it might be closer to 5,000. It's 5,000 instructions, but it's a lot. So this is. Just a summary of what you actually might be running on, which is hopefully not new to anyone. Has anyone run code on a RISC-V processor in the room? No one. Wow. Yes. But yeah, because it's the kind of the new player. So x86 and ARM, everyone's pretty familiar with, but I think increasingly for geopolitical reasons rather than technical ones, I think RISC-V will be making an increasingly have an increasingly large part of the industry, but it's already quite prevalent and sort of extremely cheap processors. And one thing I've also added right at the last minute, because it's come up a bit today, is that WASM up to this point in the talk is an instruction set. So even though there isn't WASM hardware, you still have the semantics, which are worth paying attention to, and it's also interesting because it's quite different to the way that the other architectures on this slide works. But that's kind of for a different talk. And another thing to be aware of is that if you port code from one architecture to another, there can be either instructions missing. So, for example, if you took like an x86 program and moved it onto a RISC-V processor, you might notice it might not have an integer divide instruction because it might be, it wasn't cost effective then to put it on the processor. Then there are actually some very dead but very interesting architectures that actually had no integer divide entirely. But for anyone who's written SIMD code as well, you can notice there are differences in the instruction sets you have available. And I can't spell. There you go. But yes, if you ever have find a consistent illegal instruction, for example, you might be running like AVX code on a machine that doesn't have AVX, which is an x86 SIMD instruction set. And one thing I think is kind of interesting is that over time the processors that are actually on the market have mostly kind of homogenized. And one thing I found out, I think 6 hours ago, is that Intel actually made a really strange processor in the 80s, which actually had a garbage collector in the in hardware. So that's the way to make everything D-friendly. But then and then Itanium, which came out I think when I was -1 years old, had a very strange, very clever way of thinking about stuff. Only the cleverness was kind of in the completely wrong areas. So this is a good quote. We had a good team on paper, but unfortunately the game was played on grass. So, which is by Brian Clough, who's was a football manager. And the temptation is to kind of think like worse is better, but I think it's more that it's just the design. It just doesn't matter to the designers at all. And in line with the object-oriented part there, where there's a kind of hidden assumption throughout kind of all of this and all modern programming, in that we have virtual memory with a completely flat address space, which actually hasn't always been true, which isn't just in reference to x86 segmented memory, because that was horrible, but there actually have been different takes on it, which are very interesting and are all, I think, all dead, unless you're running mainframe code from like the early 60s. And the thing to be aware of is that the hardware is only as good as we can actually use it, and it's designed around the patterns that are actually in modern code. So there's kind of a lot of literature on how much like kind of in the abstract how much performance you can actually get from a kind of from the typical code that a sort of human being might write. And one thing I noticed when I read this is that if you say sort of for the purposes of this that performance number is 3 performances, the upper bound people estimate it seems to vary from like 3 to like 10 to 500 to 1,000. So maybe it isn't bounded. And this is an important part here, and that if you think about basically any D program, like how many lines of code are there between any given kind of bit of control flow, which is like it boils down to in like the typical numbers that you actually get out of the compiler, instructions. It's basically a handful, which is one of the reasons why architectures like Itanium died, because it was effectively looking for code that's kind of very, very regular and doesn't think much effectively, and that we spend a lot of time in loops. But I mentioned this earlier, but the central kind of thing to be aware of is memory performance. Oh, actually, I forgot to say, please ask questions if you have any. I'd like the distraction. Yeah, but there's a quite famous computer architecture paper called "It's the Memory Stupid," which was published in 1996, where Richard Seitz, who is an architect at DEC, which is the Digital Equipment Corporation, I don't know. He was the architect on the DEC Alpha, which still today is a very, very impressive processor. But he made projections on processor speed and the memory performance, and estimated that effectively no matter how kind of clever the processor is, there just won't be enough memory performance to actually tell it what to do fast enough. And he actually made a fairly conservative estimate, and today is actually worse than the paper, which is quite hard to find because it's in a review paper. So there's lots of people referencing the paper, but actually finding the paper is quite hard. But this is the kind of the key takeaway of kind of the entire talk, or just sort of modern computing in general, which is that memory performance is the performance. And one thing you can do if you go to that link there is you can actually run a memory latency test on your in your browser, because it uses JavaScript. But the thing to kind of be aware of, and we'll talk about why in a little bit, is that can everyone see right at the bottom? You might have to look at the things at the side if you can't. But you have these very, very fast. Wow, that text is terrible. Okay, you have very fast memory up to a certain amount of kind of memory that's currently in play. Then it's okay, and then it's genuinely terrible. And one subtle thing as well is that if you're on either on a phone or writing code for a kind of a bigger than a microcontroller, but not a kind of general purpose chip, is that when you're in kind of this region here, this also the energy usage is also quite high, so you need to kind of pay attention to that. But the ideal way, if you imagine the memory is very slow, so we want to put a cache in front of it, which is obviously this is kind of evidence of that. But ideally we want a cache which is basically infinitely large, can do infinite amounts of stuff at the same time, responds instantly, is persistent, and is very low cost. Now, obviously, intuitively, that we can't have all of this, but you can actually get surprisingly close if you have a kind of somewhat competently designed program, which is actually turns out very few. But if you imagine you can get if I hit the cache on this laptop, I can get it in 20 cycles, which is basically not many nanoseconds, up to something like 12 megabytes, which is just astonishingly good. And one thing we can do is to kind of think about certain, because we can't have, for example, we can't have infinite capacity or infinite bandwidth, but we can find side effects. Find side effects from having finite capacity and how the way the caches are actually designed, and from that we can derive some ways to write code that's aware of that. So if you fall asleep, just locality, that's the word. But if we have it's cut the top off. That's annoying. Yeah, but if we have a large array and then we just walk across it, starting off by just byte by byte by byte, and then we go from maybe for every 4 bytes, every 8 bytes, etc., etc. The thing you notice is that the access time per access as we go across, it isn't flat. In fact, it's actually so much slower that it's cut the bottom of the graph off. But if you imagine down there is where it's supposed to be, and then we hit 128 bytes there, and this is a log scale, bear in mind, so that's really bad. That's the size of the cache line, because you can't if you're going to build a cache, you can't just do it in terms of bytes, because there's just too many of them. So you pick some size in which the cache will kind of, when it moves things around, and that's its kind of unit of granularity. And the conclusion is that when we get to a certain size, we're on this side, and the kind of like the happy bit, we're accessing one cache line. So we're still in the same cache line for every stride, but then on, past here, we're hitting the next cache line, which is why it's significantly slower. Although one thing to keep in mind with the cache lines is that if something is actually in the cache, it's actually unless you're doing this and kind of deliberately being irritating, you can it won't just be like this is in the cache and then the ones adjacent to it won't be. It's actually normally it will fetch like something on the order of like 10 at a time. And let's cut the bottom of that one as well. So I apologize for the diagrams, but back to this like memory latency graph, we can see the cache has multiple layers, and that if you see there's 256K there, that kind of just beginning of the spike is just there's a spike, which is where the working set gets too large for the level 1 cache. So we're now starting to hit the level 2, and then these curves. The reason why it's a curve is a combination of some of the memory being in one level and the other, and I think there's also some interaction with the TLB that I don't understand, but more on TLB. Yeah. When you do memory accesses, the CPU is actually constantly looking for patterns that it can exploit. So for example, in this strided example, the CPU will have spotted the stride with something called a stride predictor, and then it will start prefetching further and further and further ahead. The more confident it is, but you can actually do this. You can force it, because we have prefetching intrinsics in core.sim field. I'd recommend thinking quite hard before using them. And as I mentioned earlier, if we have virtual memory, we have to have a way of mapping the virtual memory that we access to the physical memory that's actually installed in the RAM. There's actually the RAM that actually exists in reality, which is all dictated by the OS. But the thing kind of the implication of this is that the CPU has to be just constantly walking and basically just keeping track on the mapping from X to Y all the time, which is why one thing I'd just like to note on a lot of systems is still basically for a 4 kilobyte page, which if you imagine I think like an iPhone, the top of the line iPhone has 6 gigabytes of RAM. That's like millions of pages, which is why huge pages were invented. So you have a larger page size. But the reason why the reason why I'm noting this now is that normally you can have a transparent huge page, which in theory will just be handled by the operating system. You just magically get a sort of more efficient page tables, but that actually isn't always true. So if you're like writing a memory allocator, you can actually specifically ask for certain types of pages. And then, as I said earlier, this is all really expensive. So you have a cache inside the processor, which keeps track of all of this. Called a translation look-aside buffer, which is actually that's actually the first cache ever to be implemented in hardware. I think is the first thing that you recognize as a modern cache. Was on a computer called Atlas II, which I think was it was a British computer from the 1960s, built by Ferranti. And this is what that should say, because I suspect you can't read it, is the textbook cache-aware transformation AOS to SOA, i.e., so we're going from an array of structs to a structure array, and like Dennis mentioned this right at the end, where if you imagine we have some kind of data that we want to store, but we know that we're again I can't spell. But we know the access patterns, and we know that we're going to access, say, all of the x's, then all of the y's in one go, then all of the z's, also z's. It can be very profitable to transform this to this form underneath, where if you imagine rather than hitting, say, like one byte in every whatever the overall size is when we've laid them out, we're now accessing 100% of the cache line every time, which is much more efficient. And this part of the talk was originally going to be kind of more on like how bits of this kind of the back end of the processor actually works. But I've kind of decided against it because it basically doesn't matter relative to all the memory stuff I've mentioned. Because if you notice here, this has however many 10 approaching 20 pipelines here. So each one of these does some tasks. We have arithmetic logic units that do maths. Then for example, AGU is an address generation unit. This is all very wide at the back, whereas the thing which they struggle with is actually just keeping it fed with actually stuff to do. And the thing to Google for is how they work is I think it's restricted data flow, which is the kind of the academic term for going from a kind of like ideal parallel execution of the available work you have, and then condensing that into something which you can actually turn into a chip. And as I said earlier, the average length of a basic block, i.e. between the if and the do something else, is very small. And the solution is to just guess, i.e. it does branch prediction, which if you imagine you have a loop, for example, the kind of static branch prediction, so it has no knowledge of it doesn't acquire any knowledge about the program at runtime. Where, for example, if the branch is going back up the code, then you guess that it's going to, and then if it's going forward, then you guess it's not. That's enough to get something like 75%, get it right 75% of the time on kind of standard benchmarks. And one thing, just because I've had arguments with this about people, is that like static branch prediction doesn't actually really exist in the wild anymore on kind of modern like top-of-the-line processors. So you can see a lot of arguments where people are talking about like the pipeline when that pipeline doesn't actually exist, because it's just sort of made up. Because so just kind of be careful about that, because the reason why is that the static branch prediction actually would have to happen far too late in that pipeline, which is why the dynamic approach is preferred, because you can guess much more aggressively if you actually just don't pay any attention to what the branch actually is in how it's written down. And the way to get the extra kind of 25% is to learn at runtime. And I actually checked this earlier, and I think the current AMD branch predictor that they're shipping in their current processors is getting like something like high 90% now on things like kind of compression benchmarks and things like that. So it's extremely impressive, because if they effectively have what's a little bit like a neural network inside, which I wanted to cover, but I don't understand it. So yeah. But the far like nastier, the kind of like the insidious type of branching is anything any kind of like chasing around indirections. It's like function pointers and virtual calls, etc., etc. Where there's actually an entirely separate set of caches called branch target buffers, which also have their own kind of specific structure, like the data caches, where the idea is to say if you have like an interface which is then implemented by 3 different classes, there'll be 3 different places that it can jump to. So it can store the locations of the various foos in the executable, and then make a guess which one, and then start executing it before it actually happens. Which brings me on to like Spectre and Meltdown are the reasons why everyone's computers got slower 4 years ago, and that because everything's dominated by memory performance. If you want to speculate anything, you have to be able to do speculative memory accesses. Which means that there's some researchers actually discovered that you can use some clever side channel attacks to effectively extract data from the program based on code that is never actually run, because you can just trick the processor into running it. So Spectre will be with us for many years, Whereas Meltdown, which is the really bad one, was where Intel basically forgot to implement the check, where they would speculatively make memory accesses to locations that weren't actually part of the program's memory. So it's the equivalent of like just letting you read anywhere in the address, but the physical address space is memory. So you could just extract all of the encryption keys in the system, for example, which is why kind of people were panicking. But we kind of got away with it in the end. Yeah, but one thing that is actually kind of exciting at the moment is that now kind of like everyone's on the AI gravy train. It's a workload that's extremely well suited to basically new types of computer architectures. So, for example, like actually, does anyone use a Google TPU to do machine learning? No. But they had they've designed these tensor processing units, which are effectively AI accelerators, and you can rent them on from Google's cloud, which is a basically completely bespoke architecture. And then because of that, we now have new types of instruction sets being implemented. So, for example, Intel have these vector neural network instructions, and Apple have some things as well. And these all work like fairly trivially from D, even before the compilers actually know they exist, because you can, like, one of the nice things you can do with it, you can just generate the assembly using CTFE, and it just sort of works, which is nice. And speaking of which, we have GPUs, which I wanted to talk about, but I didn't know how to make it flow. Yeah. But the thing there is decompute, where at some point we need to kind of re-implement PyTorch with D, because yeah. See and that's it. So, but I think I'm massively under time, so you get to have a longer break. So yeah, any questions?
Cheers. So a few years ago, there was this promise that we were going to be scaling up multiprocessors and just go up to like thousands of cores and all that crazy stuff. And then that sort of died by virtue of we had absolutely no way to keep those cores fed to some extent, and we also didn't have any applications that could really profit from that. So I think a lot of that went into GPUs. And as someone who is a fan of ray tracing, like GPUs are good for ray tracing now that they have hardware support, but like if you wanted really symbolic ray tracing with like not very many triangles and so, but you have a lot of branches, then you're again out of the field that GPUs are suitable for. So do you think there's any architecture where we're ever going to see that sort of like highly branching code on lots of small cores operating on small data sets?
Well, I won't say no in case I'm wrong, but there, I mean, there was a DARPA-funded RISC-V processor, which is in the kind of like thousands of cores model. But the thing is, with these kind of bespoke systems, a lot of the time they're basically built for a specific use case. So, I don't know. Specifically with ray tracing, I've written a ray tracer, but I've never written a good ray tracer, so I couldn't say.
A few years ago, I was listening to a lecture. I'm not sure who it was by, but I think it's one of the famous computer science professors who said that from the 60s to the late 2010s, a processor could touch all of memory in about a second. And this relationship had held since the 60s to the 2010s. So I wonder if this is still true. And does it scale across all devices? So, for example,
I don't know. We can find out later by just writing a program. But the thing is, it's not so much touching the memory is actually because as I said, if you have a well-written program, you can actually fit in the cache relatively easy. So it's a common thing if you really performance tuning something to just measure the working set. but it's just you have these. There's the kind of like the happy period of the happy part of the graph, and then when you leave that, that's sort of like things get really horrible. But I don't know. But like the thing with memory, it's not so much actually like hitting it as much as the power consumption from having lots of memory is quite terrible. So actually one thing is kind of interesting is that in this. If you imagine in like a CPU, you have like say like like 8 or what 8 like 16 of these, they all have to be connected over an interconnect, and the interconnect is usually just like some kind of or like 1 pixel line on the diagram, but the interconnect itself is actually where a huge amount of the power consumption of the processor comes from. So what we'll probably see. Or at least a lot of people want to see it. I have no idea whether it's going to happen or not. Is sort of in or near memory computing. So you actually have sort of dumb processing outside the CPU, but closer to the memory, which is would be nice to see. But you have had the opposite approach as well, and that just because it helps them scale. Like this is a like M1 processor, and it has all the memory on die. Shared between. Actually, no, sorry, it's not on die. The memory is very nearby to the CPU, and it's shared with the GPU as well. Yeah. But in response to the original thing, I assume it hasn't changed too much to the how long it would take to walk all the memory, because memory bandwidth has actually kept going. It's memory latency that's particularly terrible.
Yeah, and I think also that the problem in modern processors is that the clock tree is, if you want to try to make something synchronous, then it takes like 60 to 70% of the power. Yeah. So in principle, you don't want to make synchronous big processors. You want to make something like network on chip or something, right? And I also think that processors tend, if you want, as he said, if you want to have thousands of processors, you will probably have a process which is more simple, and then have many of them, and then clock them at a lower frequency, because, yeah, the power is to the square of the frequency, right? So you will probably just reduce speed and have many of them. So you will also reduce the problem with the dark silicon problem. So.
Yep. One more question?
Well, we can take a few more than one.
Well, so. No, so I said, as in there didn't seem to be many before.
Yeah, one thing that actually surprised me earlier, like a few years ago when I found out about this, is that we are now at a speed of a system where the physical distance between the processor and the memory actually has a significant impact on performance. Like you can sort of, if you look at the units of light spreading, and it's not even at light speed, it's lower than light speed, but like in a modern clock cycle, like the actual electrical signal can actually not get that fast. And so like I've been waiting for a long time, and they're now starting to do stuff like stacking memory on top of processors. But how far do you think they can practically go? Like how many slices can we get up?
Well, I think that's a question for people who like work for who actually work kind of on have the kind of skin in the game, rather than me. But like I think AMD is supposed to be shipping the vertical cache thing soon, which should be a nice increase. But I think the it's gonna have to happen. But like it's the way the fabrication processes are already like just unbelievably complicated at the moment. So I don't even want to know what it would be like with like three-dimensional chips. But yeah, maybe ask me in 10 years. I don't know.
So what would be some ways that programmers can avoid all these traps and
watch my talk from DConf Online, because like this is kind of the kind of more like kind of waffly bits that I kind of forgot to mention. But I gave like specific examples of spotting how to. Specific examples of spotting kind of particularly bad kind of like cache access patterns with like VTune, for example, or like AMD have a sort of a crap version of VTune called MicroProf. So if you're on AMD, you have to use that. But like it's better than nothing. Or on Linux, you can use perf, which is supposed to be architecture independent.
But some obvious wrong things, like you mentioned interfaces and pointers and indirections, that kind of stuff.
Well, not really, because it's the same. It's kind of like where's my structure arrays bit? Oh, did I go past it? Yeah. So with this kind of thing, like you might think, like it's automatically going to be faster, because it's a popular thing. A lot of people are aware of the transformation. But like if you do access them all at the same, this is actually probably why X, Y, and Z is probably quite a bad example, because you probably do access them quite regularly if you imagine their coordinates. Like if you are going to access them together, then you're not going to see the speed up. So like it's a question where it has to be like dictated relative to the program that you're actually writing, rather than kind of just like if this do that, because otherwise there'd be no need for programmers.
Thank you. Mine is a very silly question. What does it mean static in the static jump prediction?
It just means that the rule is independent of any of the previous behavior in the program. So there's no so if you have a dynamic one, it has basically a cache of let's say like counters where it can either sort of add one or subtract one depending on what's happened before in the past, and it will keep track of the history as well. Whereas with a static predictor, it's just a rule that the processor designer chose that could be sort of simply implemented without having to keep track of any history.
But it keeps track at least of the last jump, probably.
But no, the static is solely dependent on where the branch is to, and where it is in the program.
Oh, so it doesn't consider even the last.
No.
Oh, okay.
But like doing like whatever you did last is very, very effective as well.
I didn't know it
like dynamic
ever
prediction.
existed. That's
yeah.
Yeah. What static branches did was, since most branches are for loops, most branches are jumping backwards. And so the prediction was the jump would go backwards, and that's what static branching is.
Yep.
All right, I think we can do one more question. One more question. There we go.
So you mentioned that some programmers, try to optimize their code based on some incorrect, intuition of how the CPU pipeline works. Do you think there's actually like a better mental model, like an intuition of the modern pipeline that is useful when writing performance-sensitive code, or should we just pretend it's magic and not try to understand it?
Well, firstly, you have to actually profile it and make measurements, like controversially. Intel have either Intel or someone who works for Intel has a acronym called TMAM, which I think is top-down microarchitecture analysis methodology, and that's basically a graphical representation of where the process is spending its time. So again, watch my previous talk, because I spoke about it a bit in that, because like VTune will actually, rather than just showing you a bunch of just like throwing data at you, VTune will actually basically draw a pretty picture of where the process is spending its time and where it's bottlenecked. In fact, if you've read Andre's blog post from I think 2000 18, which is the Lomuto's comeback about partitioning in quicksort. The diagram from VTune that he uses there is from that methodology. So that's a kind of practical example combined with some sort of smart algorithm stuff.
Yeah, I remember reading that, but it's been a while, so maybe we should revisit it. Thank you.
Yeah.
Okay, and that's it for question time. Thank you again, Max. All right, we've got one last break before the last segment of the day, which is the language design panel. So get back here for 4:30. You guys want to do the walk of honor up on stage? Sit down before. Sit down before. All right. Guys, we're starting. All right. We're all back upstairs, I hope, because I've honestly had enough of singing the upstairs song by now, and I'm sure you have too. So anyway, let's get right on to the language design panel with a bunch of industry legends here.
And me.
And you. Now, for those watching at home, I am keeping an eye on Discord down here, so if you have any questions for the panel, please go ahead. We also have guys with microphones around the room. You guys know the drill. You've been doing it for 2 days now. But let's kick off this panel with a bit of a fun question for language design. Why does everything look like C?
It doesn't.
Well, not everything, but let's say a lot of systems programming languages do, for example. So why does everything that I use look like C?
Oh, that's an easy one, because everybody thinks they can replace C, and nobody's going to touch anything that doesn't look like what they're used to.
Yeah, basically people are used to it, and so it's an obvious choice for the next language design. People are familiar with it, and yeah, it works despite its inconsistencies and things like that. It's still comfortable. It works. You don't really have to spend a lot of time documenting it or explaining it to people. So yeah, it's just easy.
I guess it's why does everything look like algol, really? Some things don't, you know. Lisp is still alive, so.
Well, I mean, let's follow that through. Like with Lua, why did you choose a different syntax to C then?
Exactly, because not everything looks like C. And back then, Lua, it's very old. Well, back then, more than today, a lot of things didn't look like C. For instance, I think I mentioned that, for instance, that thing about the one indexing, that famous one indexing, that most of our users were Fortran programmers, and for them, nothing looks like C.
Well, I never liked the begin end of Pascal. It just seems silly to be typing all those letters for the opening and close brace.
Yeah, I mean, I guess you have bash scripts as well, where like branches are like if this, and then to end the branch it's fi, like it's in reverse. Like, why? I don't get that myself. Why would anybody design it like that? Sure, it's cute, but it's like, why bother?
Yeah, but ESSEC is even worse.
I was going to say the same thing.
Surely we must have an audience question by now, I guess, unless you guys want to rant about something along those lines. Oh, we have one audience question over here.
For anyone on the panel, what's a language that you really admire that you don't work on?
Oh, what a great question.
Common Lisp.
I would disagree. Scheme.
Sure, okay, scheme is simpler, fair enough. Also, question marks are a lot better than a stupid P to signify a question, predicate. I mean, that makes no sense. Okay, fine, scheme.
And another that I admire, I work a little, but not much, is Haskell. I am a big admirer of Haskell.
I have to say I like assembly language, but it's just...
Which one?
Which one? My favorite was always the PDP-11. PDP-11 always had just the nicest instruction syntax, very orthogonal. A lot of fun to write code in PDP-11 assembler. But I don't do it anymore because, well, PDP-11's long since passed into history.
Yeah, the PDP-11 don't do it anymore as well.
Yeah. I mean, you can see its influence on the x86 instruction set. There's a lot of 11-like stuff in there, but they got a lot of it wrong. Like the x86 superficially looks like it, but they didn't get the idea of an orthogonal register set. Every register has custom instructions for it.
Yeah, I mean, I guess slightly related to that, like an old programming teacher was writing his own scripting language, and he loved the idea of reverse Polish notation. So have you guys ever actually considered doing something like that, or do you think anybody might ever be interested in something like that?
No.
What do you mean, a programming language?
Yeah, he had a full scripting language where you'd push arguments to the stack and then operators and then pop things from the stack, and yeah.
Like forth. I think
I'm not actually sure.
Yeah, fourth is like that. I like that.
Okay.
I think it's for what it is. It's very interesting. It's ridiculously small, much smaller than Lua, and it has its uses. I think it's.
Well, when I was in college, the calculators had just come out, and there was a great debate between the HP35, which had RPN notation for entering, and the TI, which used infix notation, and there were adherents to both parties, to both forms, always arguing about which one was superior, and nobody was ever converted from one to the other.
Are we ever going to see dependent typing and proof assistance in mainstream languages, or do you think it's overhyped?
Well, I can't predict the future, but probably not, just given how complicated it is. I mean, Haskell's simpler than that, and people do use it in industry, but it's not, widespread. And I think a good part of the reason why is because it's complicated.
I think I'm going to quote someone I know in Tel Aviv University, that it's going to be the future, and it's always going to be the future.
I kind of agree, yes. Even Java, the generic stuff in Java, I think it's already too complex for a lot of people. I think you have to change a lot the industry to make those things important.
I have a question. At DConf 2017 on a panel, Walter predicted that the lack of memory safety is going to kill C. And I'm curious, Roberto, what you think about that. Do you think that's true? Will C die because of a lack of memory safety, or is it going to stick around and persist forever?
I don't think C will stick around, but also I don't think that the problem is memory safety. I think there are some other problems, but memory safety, it's still. I would like to believe that memory safety would be solved by languages, but I don't think this is a real trend currently. I think still people believe in memory safety by hardware. But I mean, just you have isolation, and then inside your process, it's your problem. If you don't bother with the memory of other processes. So I think, I mean, it's good. I am big in favor of memory safety in languages, but I think that that's not a crucial property of, unfortunately. I mean, it should be, but I don't think any language will die because of that.
When I look at lists of security vulnerabilities, buffer overflow is always number one by a large margin.
It is, yes.
And C doesn't have buffer overflow protection.
No, I agree, completely agrees. But my point is that, unfortunately, correctness and things like that are not top priorities in software development, I think. Security, etc. It should be. That's what I mean. It should be, but it's not. It's not. I don't think it's, even today, it's still not economically a good thing to do very good software. It's much cheaper to do bad software. I mean, not bad, but reasonable good software, and that's enough. It doesn't pay off to do software above certain level of quality. The software engineering always says about quality, etc., but the economics of software development nowadays, it still doesn't pay that. Now, if all those data breaches and things like that, it's becoming more expensive to have bugs, etc. But it's still, the balance is still, I think for most kind of softwares, it's still much cheaper to do something reasonable and faster than to waste a lot of resources trying to cover all bugs, etc. The cost, it's very low for bad software.
The interesting thing about that is, when NASA puts code on a rover, that software is ridiculously expensive to write.
Yes, but that's not 90%
sure, of course.
Of all software you write.
But
yes, there are some very specific cases that it pays, but for most software that people write every day, it pays even to write in Lua. That's why people use.
Right, but even in the NASA case, they don't change languages. So even though in their case it costs so much, they just have procedures around writing the code, which I find interesting.
Well, no, because there is this difference. Once I think someone asked, it was fun. I think it was a panel whether I would fly in a plane using Lua in the system. I would be crazy. I mean, I would not fly it in any plane of a company that uses the Lua, even in another different airplane. Because, I mean, come on, that's not the goal. But I think that in general, the economics are most software. It still doesn't deserve, it doesn't pay to be well tested and etc. It's much, as they say, just turn off, turn on again, and keeps going. And I think it's a little better now, but it's still, most software, it's still cheaper. It's better to do it cheap.
Well, adding memory protection is not expensive, and the idea is that you don't have to test it to not have security vulnerabilities, because the compiler will ensure it for you for memory safety.
I don't know, maybe, but the types might not be expensive, but it demands more. I mean, more thinking about it. Yeah.
Oh, that's true.
And you still have logic bugs that the type system can't protect you from. So.
Yeah. Well, I'm mainly talking about security vulnerabilities, and people trying to stop that from happening is a very expensive industry. And when you do have a security vulnerability and you get some ransomware, and you've got to pay a ton of money to the ransomware people, that's a very costly thing to have a buffer overflow bug.
Yes, that's what I tried to mention, that data breaches and etc. That's exactly. I think it's changing the balance, but I think it's still, people still didn't get that. Exactly how much expensive a bug can be, because a bug in the wild, it's still very cheap, but when someone gets the bug and explores, that can be very expensive. So that's for those that like quality, it's a hope that may put more pressure on good software, but I think it's still, most people still do not get it.
I just wanted to add that you can also add some form of mitigations at hardware level instead of changing the language itself. You can do things like pointer authentication and just preventing. I mean, there's many mitigations, and that's easier than changing a language or changing the way we make software. At a global scale, it feels cheaper to change the underlying hardware if that has no consequences on how software is written. So I think that adds to what you're saying, that might not, software bugs might not have consequences that might drive us to another language.
Yeah, I think that's the trend, that really is the trend, but I don't like that. I mean, I agree with it. I mean, it should be cheaper and more and better to solve that in software. Because in hardware, sometimes you get to the restriction. For instance, one common problem we have all the time is that you restrict that you cannot change the code. For instance, you cannot change the code is static, and then, for instance, you cannot do JIT compilation in the machines because of that kind of restriction. So there, I think when you do impose in their hardware, you end up restricting sometimes much more than you wanted. It's that kind of solution that it's a poorest man's solution, because it's a kind of, okay, nobody's going to do anything better, so that's the least we can do. But so I agree. I think that the trend is that. I think that's what's going to happen. That's what I said about memory safety, that you have the hardware impose limits. So you can blow up your own process, but as long as you are isolated from other processes, it doesn't matter. But it's in an ideal world, maybe you shouldn't even need memory protection, because if the languages ensure everything, there are some dreams about that. For instance, with Oberon and languages like that in the past. But
well, I see a definite trend in modern languages over the years of replacing error-prone constructs, or things that are shown to be error-prone, with less error-prone constructs. And I see that in every language except C, which resists these kinds of changes. I've proposed a way to do buffer overflow checking in C, and it generates just simply zero interest from the C community. But I also see C being used less and less, because people are drifting away to more advanced languages and languages with safer features in them. I think eventually all that'll be left of C is, that's how languages will communicate with each other, is through the C ABI, but nothing will actually be implemented in C. But even simple things like the talk earlier today about changing the way we do concurrent programming, so it's composable. And I mean, that's a big advance in reducing the errors in concurrent programming. And I think, that's a very exciting development. Structured programming that replaced go-to programming was all in an effort to reduce very error-prone constructs and replace them with things that are less, more human-friendly, I guess, so people make less mistakes. And some people don't like me making these analogies, but it's a lot like airplane cockpit design. It's evolved over the years, and it's evolved not because cockpit designers are getting smarter. It's because the aviation industry has learned from the mistakes. Every accident and crash and everything like that goes back to, how can we prevent this from happening? And often it means altering the design of the way the instruments and the controls work in the cockpit to minimize the human error component, because you can't really fix people, but you can fix their human interfaces so they're less likely to make mistakes. And as a result, flying airplanes is incredibly safe today, but that's been an evolution over 120 years of continual refinement based on making mistakes, and then don't want to make those mistakes anymore.
Yeah, I mean, I guess slightly related to this, we've got two languages here on the stage that have garbage collection in them. And they're both for very different domains, but they seem to have the same usage here. But D being a systems language, like, for example, the last DConf, we had, what was that talk about getting D into the Linux kernel? And that basically needed to run with better C, just to avoid garbage collector and a bunch of the other runtime stuff. So, yeah, I mean, there's case to be made for having garbage collection in a systems language, but then you have things like a Linux kernel, which can have uptimes of years that a garbage collector might not work so well. So, how well do you think a garbage collector actually fits into a systems language, for example?
You want to take that first? Okay. Well, D is a multi-paradigm language, and the advantage of the garbage collector, and it's been brought up in a couple of the talks just today, is if you just want to write code and get it to work, the garbage collector is your friend, because you just don't want to be bothered with trying to figure out what is the exact lifetime of this piece of memory I'm allocating. I just want to get my program to work and get it done and out the door. And the garbage collector or garbage collected language is very efficient at minimizing the time you spend programming, because you just don't have to worry about the memory allocation on it. You just allocate memory and use it and don't worry about it. But if you're writing code that's going to be long-lived and you want to guarantee it, all garbage collectors have a possibility of wedging themselves. You never want that to happen. You don't have to use the garbage collector. You can do stack allocation. You can do chain allocation, those other schemes I mentioned. You can write your own storage allocator and use it. It's all there, but it all comes at an additional effort in programming on it. So with D, you can do it either way, or do it like what most people do with D, is they do a mixture of the two. Usually I'll use the garbage collector if I don't really want to be concerned with the lifetime of it, but if I know the lifetime, I'll use explicit allocation for it.
I think this is akin to saying, yeah, this fancy new language C, this sounds great, but in my embedded system, I'm not allowed to do dynamic memory allocation. So how does a language with malloc and free fit into this? Don't do it.
All right. We actually have a question from Steven Schweighofer. I might have mispronounced that too. What is a feature that you love in a different language that you wish you could bring into your favorite language?
I know one that will never, there is no way that it could come into Lua, which is pattern matching from functional languages. But that needs a good type system, etc. That it's everything that Lua lacks. So I don't think any way to put that in. But I think that's very, very interesting that you have cases and you have structs all in one construction. It's really nice.
Well, I'd like to simply be able to import C. We've been successful at importing C code directly, and I'd love to be able to import C++ code directly and interface to it in such an easy way, easy and painless way. So I think interactivity between D and C++ would be a really nice feature to have, but technically it's quite a challenge to make it work.
Yeah, I mean that's definitely a goal, but I think the spirit of the question is like a C++ feature instead of just interacting with the code. So what kind of a feature is kind of missing from D, I guess, that you would really like in?
Well, I think pattern matching and tuples are kind of high on the list of features D ought to have.
Probably something like traits for compile time interfaces, so that you can say that, accept this. I mean, we got the ifs after the function to say if is input range, but basically it's so far away removed from where the template argument is. It would be nice that you could specify, I take a T that is for instance, forward range of int, because or even constant, even better, or yeah, something like that. I think that would be cool.
No, it's a hard question because most of my problems with D are things that are not misfeatures, but like bad use cases or stuff that are hard. But I guess interfacing with C++ would have made my life a lot more easier in a recent project I had. And being able to avoid the runtime completely and use C++ templated structures instead would have made my life easier instead of implementing everything from scratch.
Yeah, I mean, me personally, I would like to see first-class types in CTFE code because that would eliminate virtually 90% of my templates. And I actually have a theory that it would make metaprogramming an easier entry point for most people because they just need to be writing D code instead of learning how to write templates.
I want to go back in time and steal your thing. Me and Manu were talking about it yesterday.
We got a couple of questions down the front here, and we do have a confirmation from Ian that fourth is RPN, and it's kind of closer to assembly than C. So yes, you were correct.
Kind of a bit of background. So the thing that attracted me to D was metaprogramming, and then I was kind of sad to discover that most of metaprogramming you do is by constructing strings. So my question is basically, what is your view on kind of modern static metaprogramming with types and specifically like multi-staged macros where you can have types on different stages and guarantee that you are building kind of correct sound code, even your generated code will be sound. Like, do you see any like possibility D getting modern metaprogramming like that?
The only way I can think of to do more metaprogramming like that without using strings is doing macros. And I guess most people know my opposition to macros and in the language and why. So I'm not sure I see that happening with D unless another way is found to do it. I will point out that, are you familiar with expression templates in C++? Yeah, well, you can actually do that in D. I tried it out just to see if D templates were powerful enough to do expression templates, and they are. But I don't recommend doing expression templates, but as something to play with and investigate, I think it would be interesting and illuminating. But I don't really want to go to macros because a bitter experience with what happens eventually always with macros is very discouraging.
I'm not sure most metaprogramming D is done with strings anyway. At least for me, most of mine is done with static map and static filter and basically, you know, template meta functions. What makes it harder there is you don't have template lambdas, so you have to give it a name first, define it out of band, and then use it later. And then there's some issues with compile times and symbols being generated. So yeah, it depends on who's doing the metaprogramming, I guess. But what would make that a lot simpler is what we were talking about before with types being first class, and you just write regular D code instead of writing functions instead of meta functions.
All right, we're about halfway through the panel. How's it feeling, guys? Enjoying it?
Yeah, it's fun.
Cool.
Just having a chat.
So far, so good.
One of the most successful features of D is unit tests being made first class and known to the compiler. Do you think there are other kind of annotation that programmers use that could be made first class in a similar positive way?
I don't know. I never thought about that, but you're right that building in unit tests and it's and the documentation generator have been transformative in how D programs were how D programming is done. Before we had the built-in documentation generator, the documentation phobos was 100% wrong, misleading, or completely missing. There was even documentation for functions that were applied to the wrong function. You know, somehow they would get disconnected from each other. building the documentation generator into the language itself completely fixed all that. And unit testing, the built-in unit test has been maligned for not being powerful enough, but it's like going from a horse and buggy to a propeller airplane. Sure, jets are better, but still, the propeller airplane is infinitely better than going cross-country by horse and buggy. But I'm not really sure what other feature would fit in with that as a built-in. But if you have any ideas on that, I'm interested.
Oh, hey, we've got a question from the bot here. With the rise of popularity of Rust, where do you see the future of D? Despite the missing garbage collector and Rust, both kind of target the same audience.
Well, that is a great question, and Rust has seen a lot of popularity. One thing that, D has a prototype borrow checker in it, and the memory safety is a goal. We're not as far along as Rust is, but one thing D has going for it is the familiar syntax. It's very easy to transition from C to D or from C++ to D because the syntax is so familiar.
Well, my biased opinion, obviously, is that it's easier to write D code because you don't need to worry about lifetimes if you have a GC. It's just simpler. I mean, there's a reason why there's blog posts about how to, I think, write a linked list in Rust because it's a lot harder. And whereas if you have a GC, it's easier. Also, concurrent algorithms become a lot easier if you have a GC because you don't need to worry about that or cycles. So I think that they're very good at what they're doing, which is to provide memory safety without a GC. I would say that I'm not entirely sure that that is, that useful because in most cases when people think they can't afford a GC, they can. Yes, there are cases in which you can't, but then there are ways around that as well. So I guess that's how I view us there. Simpler to use for most cases, and we can also, bypass a GC. But we got some work to do there too.
I'll just extend that similarly to the question I've been asked about lockless data structures. Basically, what happens is that when you don't have a GC, you're going to have a lot of pain trying to figure out when should things be deleted, because somebody still might own a pointer to that structure, and you're going to have to figure out when you are able to delete it safely without breaking everything. So a garbage collector really helps there.
One of the troubles with Rust is if you want to convert your program to Rust, you cannot just transliterate it. You often have to redesign your algorithms and data structures to be compatible with the borrow checker, and that imposes a large transition cost. I've converted a lot of C and C++ code to D, and it actually goes very quickly.
Yeah, let's do your question, Amory, and then I got another one from the chat.
Yeah, so I was wondering, it seems to me we are in an industry that does a lot of cargo cult more than, actually verifying, if the good practice are actually good. And a few remarks that you made, all of you, not someone in particular, earlier, kind of reminded me of that. So I was wondering, what do you think is actually a bad practice that the industry in general considers as some best practice or something that we should all be doing?
Well, one practice I've started adopting in my own code is single assignment. Normally, out of a long-standing habit, I would tend to recycle variables. Like I need a new variable to hold an integer. Oh, look, I've already declared I. I'm not using it anymore, so I'll just reuse I over here. I think that's I've come around to the conclusion that that's an execrable practice. And if you can rewrite your code or just do a minor refactor and so that you're only assigning a variable once, not multiple times, I think your code is much more readable, more understandable, and less error prone if you do that. So although that's it's kind of a little thing, if you tend to write complicated code, I think it's kind of a big deal to do this.
I fully agree. And anyway, SSA will do that anyway,
Yeah,
so it's very
it's
easy the job of it.
It's SSA, single static assignment. It's a good idea, and it's one that never occurred to me years ago.
I'm trying to think it's something that's industry-wide, but the only thing I'm thinking of that is common in some code bases and rules is, one return per function, which is just incredibly stupid.
Sorry,
one return per function, only one return. Yeah.
Thankfully, I've never seen it. But regarding the SSA, I do have one problem trying to write like this, which is the fact that I can't reuse the names, and then, I have X and X1 and X11, X1111, and it doesn't really scale like that. And the practice that I think that is forbidden go-to, where it actually has some really nice use case when you need to jump out of multiple loops.
Yeah, I sometimes still use goto for that.
We know.
Do you have a better way to do it?
I'd have to look at the code right now. Not really.
Yeah, one time a long time ago when I was working for a company, we had a code review meeting, and one of the other people had done a grep for all the goto in the code I'd written, and then just showed it as a list printed it out. And it was a list on a piece of paper of all these goto things, and he basically said, "You're a bad programmer. You're using all sorts of gotos." And one of my friends says, "Yeah, but by definition, you took all of these gotos out of context." You don't know why the goto was there or what problem it was solving.
I think cargo culting in general is problematic. Just always think about what you're doing. Don't blindly follow any rule, including the ones you wrote yourself. It's like saying goto is always bad, never use goto, but you're in a C code base and you're trying to clean up. Well, the easiest way you can do that is by doing a goto.
A lot of people ask me for lists of principles on how to write code, and I'll write a list of principles, and then one of two things will happen. They'll tell me I'm violating these principles, or they will follow the principles without thinking about it and drive off a cliff with it, and then say that the principle is bad. And one thing I always, and I admit a lot of the principles are contradictory. And so I guess I try to impress upon people to don't blindly follow any programming style rules or anything like that. It's those are guidelines, and use your best judgment on this. Don't let the rule override your judgment, because you'll just drive it off a cliff if you do that.
My favorite example is I worked on a project that was called SLA. It doesn't really matter what it was doing or what it stands for, but that was the name of the project, and this is important because in the code base they had a hash define SLA underscore TWO to the number 2. Because they used the number 2 somewhere, and in code review somebody went, magic number, define SLA 2, 2. Because that obviously solves the problem.
Exactly what I'm talking about. Blind adherence to programming style guidelines.
They also define SLA new line to, \n, just in case that changed.
And that passed code review?
Somehow, yes. It's the blind leading the blind. I mean, you know, somebody's driving off the cliff, the other one's there too. It's like, GPS says this way. Okay, woo!
I think good rules are the ones that that give you reason to think about why you are breaking them. So you can break them, but you have to. I mean, you really think, no, this sounds good. Why I'm not following it? And then it forces you to think about. And sometimes you can break, but it forces you to understand really what's going on. And sometimes even you decide, oh, I don't need to break that rule. Actually, I just can solve the problem in a better way. But if you break, at least it forces you to think more about what you're doing. But those are the good rules that are not that common.
Well, it sort of is like the rules of how you learn things. The newbie follows the rules because he's told to. The master follows the rules because he understands the point of the rules. And the guru breaks all the rules because he understands that the rules don't apply. He transcends the rules. So
yeah, I think the best rule is just think.
Yeah, well, it's like, you know, when I was, teaching somebody to drive, and they said, well, what do I do in this situation? Because avoiding the accident would break the law. And I said, if you're avoiding the accident, break the law. You know, the law is a law. The law doesn't provide exceptions for this. It's like if I see 3 people walking abreast, sticking into my lane, if the other lane is clear, I will move all the way over into opposing traffic to not hit them because, you know, I'm breaking the law doing that. But, you know, I'd much rather break the law than, run somebody over. And it's the same in programming.
Yeah, that's the weirdest take on the trolley problem I've ever heard. All right, so this is a question going back to the macros. AST macros instead of text-based macros, do you still feel those are harmful?
Yes, and as an example, I give expression templates, which are basically AST macros. And one of my favorite bad examples of that is a boost example, which turns C++ into a regex language. And the problem with it, and the authors were very proud of this, is you couldn't tell what was C++ and what was regex. So what happens when you have AST macros is, you wind up inventing your own language. And when you wind up inventing your own language, people don't document it. So what happens is, and I've seen this effect many times, is people invent their own language, they write their program in their own undocumented, quirky language, then they leave the company, and this is dropped into the lap of some poor schlub who's supposed to try to figure out and fix bugs with it, and what happens is they wind up throwing it in the trash and starting over. My favorite story on this was a friend of mine worked at Microsoft, and he was given this job of fixing a bug in a 50K executable. And the executable was all written in Microsoft Assembler, and the programmer had invented his own macro language, and the whole thing was written in this macro language. And programmer after programmer had been assigned to fix this bug in it, and after 6 weeks of trying to figure it out, they'd give up. And so he was telling this to my friend. My friend goes, oh, I can fix it. So he hands it to him, and then 2 hours later, he had it fixed and the source code checked in. And he goes, well, how did you figure out his macro language? And he said, I didn't. I assembled it, I ran it through a disassembler that generated source code, I found the bug, fixed it, and checked in the disassembled code as the new source code for the project. So this is one of the pivotal moments in my evolution to disliking macro languages. And And I've seen that story repeat itself again and again in various contexts with the macros in different languages. It's even in my own code. I used to use lots of very clever macros in it, and in the process of transitioning it to D, the first step was to get rid of the macros because macros don't translate very well. So I rewrote in ordinary C code instead of using the macros, and I had the epiphany that my code was a lot more readable and understandable when I didn't use clever macros in it. So that added to it too. So yeah, my position on macros is getting harder.
I don't know. I find that people just invent their own language anyway if you don't have macros, but it just happens to have the same syntax.
But that makes a big difference.
Sure.
Yeah.
Well,
when you're at least you can read the syntax. I mean, it's when you cannot not even parse someone else's program, it's much worse. I think that's a big problem with macros that you cannot even parse the.
Yeah, I mean, it's not exactly macro related, but thanks to op dispatch in D, one of the things that we blow people's minds with is like, here, we've integrated Lua, and then you can just write out a Lua function in D code, and then it interprets that string at compile time and calls into your Lua function. So, yeah, it's kind of unrelated, but kind of cool.
Well, one thing I have found is people find ways to do it anyway, but by not allowing a macro processor in there, I make it difficult for them to do and try to discourage them from doing it.
Life finds a way.
And you always have the option of using a M4 as a preprocessor.
The old just use M4 trope, yeah.
M4 is fabulous.
For those who don't know the M4 trope, people would complain that the C macro processor was primitive, and the reply always was, well, if you don't like it, just use M4. M4 was an advanced text processing processor on Linux, or on Unix, yeah.
Was? AutoTools is still being run.
I'm sure M4 is still being run, but I never hear about it anymore, so.
Anybody who has to deal with AutoTools does, unfortunately for them.
Oh, yeah.
I had to read the documentation for that once. Ain't nobody got time for that.
All right, we have another question from the chat. I have no idea how to pronounce that one, but have you guys ever tried the HAXE language, H-A-X-E? It has much to do with what both D and Lua's capabilities are, such as metaprogramming, portability, garbage collection. You have direct access to the AST using only language constructs, which are on its standard library. And how do you think that would help or break languages into people having their own feature without directly needing to deal with the interpreter or compiler?
I read about it once and I've forgotten it since.
What's the name of the language? HAXE, H-A-X-E. I'm going to guess that's a no if you've...
I read about it once, like I said, I've forgotten about it already, so I have no opinion.
I've heard of it, and that's about the extent of my knowledge of it, so I can't say anything intelligent about it.
Same.
Yep, nobody
Sorry.
knows this language, so... All right, do we have some questions from the audience here?
Come on, you know you want to.
Yeah, down the front.
Yeah.
Oh, you've got the mic. Excellent.
Typically, language designers try to avoid complexity, both when users use their language or inside the language implementation. However, sometimes you are forced to make a compromise, and I'm curious, from your past experiences, if you, at what point, or if you have an example where you needed to sacrifice simplicity, both in the implementation or in the user-facing code, just to implement a feature that was maybe needed. So more exactly, where do you draw the line between having a feature and sacrificing simplicity?
Oh boy, that's one of those, everything is a judgment call. It's like if you're designing a house and you have an envelope for the house and you want to make the closet bigger, well, which room do you make smaller? If you look at the dwelling that you all live in, you'll realize that everything in it is a compromise. Everything in it. And everything in a programming language is a compromise between what you're getting and what you're giving up. And complexity is as a problem I've really tried to fight against, but it's kind of a losing battle. Every new feature adds complexity and interactions. It's a very difficult problem to deal with. You've done a great job with Lua in reducing this problem.
But we do sacrifice complexity, simplicity a lot of times. For instance, in Lua, in interpreted languages in general, there is a big problem in the implementation for optimizations. So sometimes we have to, something is just slow and you have to implement some more complex data structures and things like that. And it's, for instance, all those stuff about tables, it's very nice, but all the algorithms to keep the table and the array part inside, etc., all that. You could have a much simpler implementation of Lua, but actually, we did start the very first Lua version. It was not even a version at the time. Tables were actually linked lists with linear search. And that was good enough for what we had in mind at that time. So it was just, you have to access field X, you just look for that. And then I think in version 2 or somewhere, there is a big optimization. We get the element that was accessed, you move it to the front of the list because there is a good chance that you are going to access that again. And it was good in that, but then after just, 2 months, people starting writing more complex stuff, and then suddenly, you need a hash table. Okay, so let's do a hash table. But then things, and then, you need something else. And so I always, but in the design of the language is the same. The simplicity, I always talk about simplicity, but you cannot beat lambda calculus. Just, if you want a real simple language, just do all your programs in lambda calculus. You cannot beat that in simplicity. The programs won't be that simple, but the language cannot be simpler than that.
Or it's another example, a language that starts with brain and ends with CK, so programs in that are simple. The language is very simple. However, it's always a trade-off and it's always a compromise, and it depends on the guiding principles, right? What are the goals of this particular language? What is its philosophy? And then the bias of the person making the decisions, It depends on what mistakes they've made in the past, so they want to avoid those and then disconsider mistakes that other people might make because that's not how their brain operates. And also simplicity in the eyes of whom? Arch Linux is supposedly a very simple distribution in a certain sense, but setting it up isn't, because the simplicity they're looking for is not trying to make it simple for a user to install it. So that's a set of trade-offs that's completely different from Ubuntu, which is very easy to set up, but doesn't have the simplicity that Arch is looking for in other terms. So it depends.
Well, there's also a trade-off. If you make the language too simple, what happens is the code you write in that language turns out to be very complicated. The language, so there's a trade-off. Adding complicated-looking features to the language may make the user code actually much simpler.
The overall complexity of the program can be lower if the language is a little less simple than, or much more less simple than.
You have to compare the complexity somewhere. So it basically depends on how much it's going to get used and how much it's going to save for the user, pretty much.
Yeah, that's why sometimes you want to wire a feature into the language with special syntax. It's worthwhile, and sometimes it should be pushed into the library, like the octal numbers. I didn't, and thought its complexity wasn't worth wiring it into the language, but it was certainly worth putting into the runtime library.
And you have a complexity budget just like money, right? And people have different priorities with how they want to spend money. Some people want to buy fancy cars, some people want to go to fancy dinners. You can't do both, probably. So it was what you spend the language complexity on. What do you consider important? Economy or business?
All right, I think we'll take one more audience question before we start winding down. So does anybody have a good one? A good question. Specifically, this is going to be a good question, right? Don't let me down, man.
I can't necessarily say good, but I think it's important. Is that D is a very powerful language and offers a lot of benefits, but for years now it's struggled with kind of popularity and growth, and it's been over a long time. I think D was created in 2001, and there's been entire languages created since then, and even then, I know D doesn't have a corporate sponsor, but like take for example the Dart programming language. Dart did have a corporate sponsor. It was developed at Google. But then no one really heard or cared about it until it started being used in the Flutter framework for mobile app development. It seems as if more important than a corporate backer, some flagship project that most people get involved with seems to pull a lot of interest. Do you have any thoughts on could something similar be done with D? Some important area, domain, or flagship project to pull people's interest in?
Well,
Could
that's,
it? Yes.
Yeah, go ahead.
Could it? Yes. What is it? I don't know. One of you might write that project. I have no idea. Like, what's going to garner interest? Right, well, at the hackathon, come up with something awesome. It's your responsibility now because you brought it up.
Hey, Attila, surely you're talking about this magic project in your talk tomorrow, right?
Sure. I was literally thinking 30 seconds ago how I managed to be here this whole panel without saying, I'll talk about it tomorrow. And you go and ruin it.
Well, Roberto mentioned some killer applications we're working with Lua that drove its popularity. So.
Yeah, but we didn't write that.
Right, you didn't write them. It has to be the users that come up with it.
Yeah, but I mean, that framework wasn't written by the authors of Dart either, I think is the point. So,
yeah, like you said, when it was, I think, adopted by NASA, it would Lua. It saw a surge in popularity.
No, it was not adopted by NASA. I mean, there was some guy in NASA that used Lua for some project.
Okay, I misunderstood.
And someone said it was adopted by NASA. It sounds so impressive, but there was some guy working on NASA he did some, I don't know what software he did, and he wrote in that Lua.
Okay,
but it's a good publicity.
Roberto, where do you use D? In what context?
I don't use D.
May I ask why not?
Why not? I always use only C in Lua. That's and everything else. Well, I use Haskell in teaching, and the language that it's not a programming language, but what I'm writing more now is Coq. So I don't think I could change Coq for D.
Talk to Walter about better C. Maybe you will have less bugs in your implementation of Lua.
For what I do, I think C is still a very good language. I like it. There is a lot of problems, but that I'm well aware of. But one thing is portability, for instance. That's really, really. I mean, any machine. I think no one builds any kind of CPU without a C compiler. It's like so. It's there from the start. But other than that, it's just it would be a big change. But I think portability it's really the killer thing of C, and it's simple. I mean, if you know what you're doing, it can be completely crazy, but if you can keep things reasonably simple, I like that.
I'd like to add on the question and ask, how do you actually manage to write portable C with all the undefined behavior and implementation defined behavior and make sure it's going to be correct everywhere?
Pardon me, what's the question?
With all the undefined behavior and implementation defined behaviors in C, how do you actually manage to write correct portable code that is going to conform to the spec?
Well, we try to avoid undefined behavior, but I think I didn't understand exactly the
basically that maybe some of the code is dependent on implementation defined things, and if somebody's gonna make an obscure C compiler for obscure hardware, and it might actually break.
Yeah, but we try not to. We do now with the several compilers have the GCC, Clang. They have those. They have a lot of detectors, for instance, for undefined stuff, and we use all of these tests. For instance, there is some that are completely crazy. You cannot believe that it's undefined. For instance, you have a memory address, and you deallocate the address. You cannot use I mean, it's not that you cannot access the address anymore. You cannot use the address anymore. So, for instance, we used to have code in Lua that we had an address, and then we allocate a new one. We moved. It's like a realloc, but manually done. So we are sure we are changing the memory. So we changed that, and then there are some pointers to the old structure, and so we did that. We subtract the address from the base and add to the new base to correct the address. This is undefined behavior, because you cannot use the old address once you deallocated the old block. So you can, you cannot do that with realloc. Exactly, we have to change to do the both. So you correct the addresses before deallocating the old structure, and then you deallocate the old structure. Because if you use realloc may change and deallocate the old one, and so it's. And it's hard sometimes to find those. I mean, it's not even a bug. No one ever complained, but we became very strict. I mean, we became religious. Like like it says it's that, so we are going to follow that. The only thing that we are not strict, that we explicitly assume, is that machines are to complement the representation of integers, but that's not because C, it allows 3 different representations for integers. That can be signal magnitude, can be complement 1, and can be 1 complement, and can be 2 complement, and we assume it's 2 complement. Otherwise, it doesn't work. But otherwise, almost we did some very strange changes to the language, because it is unbelievable how many everything is undefined behaviors. Things that could be just, for instance, if you pass invalid arguments to a lot of functions, for instance, f open, you have a string that says whether you're open for write, for read, etc. And if it's some letter that it doesn't know, it could be okay. It's an undefined result for the fun. No, it's undefined behavior. Everything can go wrong if you open a file for X instead of reading or writing. So we have to filter, because we just, in Lua, you just get that and pass along to C. Now we have to filter the parameter. We cannot pass that to see what people wrote in Lua. It's a lot of trouble. It's really a lot of work, but it's just mindset, I think, that you're convinced that.
Well, obviously it works.
Yeah.
I think your
it's-
attention to this level of detail
No,
has
and
made
now
you very
people
successful.
really do testings a lot of. I mean, I only do on my Linux, but then once you release some alpha version, people using all kinds of the different machines, and then exactly anything people report, we go there and see what's happening, etc. And sometimes we try to, it's the problem of the, we found a lot of bugs in compilers because, but then sometimes depending who is the compiler, if that's Microsoft, we just, okay, it's the bug, we have to live, it's our, we will have to correct that. It's their bug, but it's our problem. But if it's, but we did find many bugs in C compilers along the years.
It's not just us. It's not just us.
Yeah, but interesting. You said when you have you find a bug in Microsoft's compiler, it's your problem. But when you find a bug in some minor outfit's compiler, it's their problem.
That's life.
That's the state of the industry.
Yeah, we try to make the Microsoft problem too, but it's unbelievable that some horrible bugs there.
I used to have a C compiler.
And then stupid ones. I mean, they could fix that in 3 minutes, but.
Well, I used to sell a C compiler, and I would get this all the time. People go, well, your compiler has a bug in it. You got to fix the compiler right away. And I go, well, what do you do if you find a bug in Microsoft's compiler? Oh, we work around it. That's just the way things work.
Yeah, life is not fair.
All right, we got to start wrapping up here, so let's end it on a fun, easy question. So if you didn't get into language design and language authorship, how do you think your professional life might have gone, or I guess in Walter's case, your retirement?
Oh, well, D started because I retired, and 6 weeks of watching TV, I was done with that. I was going back to work.
There was really nothing else you would have done in retirement, like get into cars or something, or
maybe car racing. another interest of mine.
I have no idea. I never planned to be a language designer. I never planned to work with programming languages. I think I mostly never planned anything in my life for more than like.
Yeah, that's
2
how
months in advance, I was just following the flow and things.
Yeah, I mean, that's how I wound up in Europe myself, so...
So it's difficult to... I didn't think the first option is you were asking for a second option. That's too...
Oh, weirdly enough, if I had enough money to retire tomorrow, I'd design my own language. That's what I would do. That's how I keep, spend my time. I'd probably like work half time with D and half time creating this new thing, which would probably have macros, by the way.
Well,
by probably I mean definitely.
We'll make sure you can't retire, Attila.
Oh no! I thought somebody's gonna give me an anonymous donation of 10 million Swiss francs so I could retire. Darn it! I don't want to leave Switzerland. You get to be picky when you live in Switzerland.
Yeah, so same as Roberto, I didn't really choose it and just ended up there, so that's life.
All right, so, we've got the right people for the job. All they ever want to do is design languages. All right, yeah, I guess, we've got 5:45, which is great time to finish it up. So thank you, Walter, Roberto, Attila, and I'm still going to pronounce it wrong, Uroy. Yeah, it's closer than I have been. Give it up for these guys. All right, and that is the end of day 2 of DConf 2022, and that means after you've eaten, BeerConf starts. BeerConf. So same deal as yesterday, up at the Fox's BeerConf. You all know the deal. You all want to drink beer. Guess we'll see you there.